Hey everyone! Welcome to our exciting course on modern computer vision with PyTorch. In this course, you'll get hands-on experience with some cutting-edge techniques in image classification, object detection, and even generating videos from text prompts. We've packed this course with engaging coding exercises, and you can check out all the code in the GitHub repository linked in the description below. So make sure to stick around until the end, where you'll tackle a final project that tests everything you've learned. So grab your coding gear and let's dive right in. Let's get started. An artificial neural network, or ANN, is a powerful supervised learning algorithm designed to analyze data in a way that's reminiscent of how our own. An artificial neural network, or ANN, is a powerful supervised learning algorithm designed to analyze data in a way that's reminiscent of how our own brains operate. As we dive deeper into this fascinating realm of technology, we'll explore its fundamentals, we'll look into how it functions, and what's super exciting is how you can implement your very own ANN using Python. So let's get started, shall we? Understanding the structure and workings of an ANN can open up a whole new world of possibilities in data analysis and machine learning. You'll see that the principles are not only intuitive, but also incredibly powerful when applied correctly. So, are you ready to unlock the secrets of this transformative technology? Let's go. To grasp the essence of neural networks, it's essential to understand the architecture of an artificial neural network, or ANN. At its core, an ANN consists of interconnected nodes, or neurons, organized into layers: the input layer, hidden layers, and the output layer. When data is fed into the network, it flows through these layers, allowing the network to learn complex patterns, much like how our brain processes information. An ANN adjusts the weights of its connections based on the input it receives. This adjustment is guided by a process known as backpropagation, which fine-tunes the network's performance over time. Now, to illustrate this concept, let's imagine developing an ANN that recognizes handwritten digits from 0 to 9. The input layer of our network accepts pixel values from images of the digits, while the output layer consists of 10 neurons, each corresponding to a digit. As the ANN trains on these images, it learns to associate specific patterns of pixel values with their corresponding digit. Isn't that fascinating? We're essentially teaching a machine to interpret visual information just like we do. Now, let's implement the necessary steps to prepare our environment and the dataset for our digit recognition task. First, we need to make sure TensorFlow is installed in our Python environment. This is super important because TensorFlow provides the tools we need to build and train our neural network, and we install it using pip, the package manager for Python. Now, once TensorFlow is up and running, we'll import TensorFlow itself, along with some Keras modules that help simplify the process of building those neural networks. Specifically, we'll bring in layers and modules, which will help us create the structure of our artificial neural network. Plus, we can't forget about the MNIST dataset, which contains images of handwritten digits and is conveniently split into training and testing sets. So after we've got all the necessary libraries imported, it's time to load up the MNIST dataset. This will give us the training and testing data we need. Now, it's crucial that we normalize the pixel values of these images to a range between 0 and 1. Why, you ask? Well, normalizing helps improve the efficiency of our model during training and allows it to converge faster, which is vital for effective learning. By converting our data to float32 and dividing by 255.0, we're ensuring that those values are in an optimal format for processing. Next, we're going to construct the architecture of our artificial neural network, or ANN, specifically designed for digit classification. So let's jump right in with a sequential model using the TensorFlow Keras API. The first layer we're going to implement is a flatten layer. This layer is crucial because it transforms our input images, which are in a 2D format of 28 by 28 pixels, into a 1D vector of 784 elements. This step is super important as it allows the data to be seamlessly processed by the layers that follow. Now, after we've added the flattened layer, we proceed with a dense layer that has 128 neurons, and we're going to employ the ReLU activation function here. This hidden layer is where our ANN really starts to learn to identify complex patterns and features within those digit images. The ReLU function introduces nonlinearity, which is key, allowing our model to capture intricate relationships between the inputs and outputs. Finally, we'll include another dense layer, but this one will consist of 10 neurons and utilize the softmax activation function. This output layer will generate a probability distribution across the 10 classes, representing the digits from 0 to 9. By implementing this architecture, we're laying down a solid foundation for training our ANN on the MNIST handwritten digits dataset. Next, we will compile our model to prepare it for training. This step is super crucial because it involves defining the optimizer, the loss function, and the metrics we'll use to evaluate the model's performance. In our case, we're going with the Atom optimizer. It's known for its efficiency in handling those tricky gradient updates. Now, the loss function we've chosen is sparse categorical cross-entropy, which is really well suited for multi-class classification problems where our labels are integers. Finally, we'll specify accuracy as our evaluation metric, which will let us keep an eye on how well the model is doing during training. Now, let's dive into training the model with our dataset. We'll be using the fit function, which in a nutshell will adjust the weights of our network based on the input data over a specified number of epochs. By setting the batch size to 32, we control the number of samples processed in each iteration, leading to manageable updates to the model's weights. Less noise is always a good thing in this process. Running for 5 epochs will give us some insights into how well the model is learning. While we do this, it's important to carefully observe the output, as it can provide valuable feedback on its learning trajectory. Now, let's evaluate how well our trained ANN model performs on unseen data by using the evaluate function. This step is crucial, as it helps us ensure that our model generalizes well and hasn't just memorized the training data. When we call the evaluate method with our test dataset, it computes the loss and accuracy, allowing us to understand our model's effectiveness on previously unseen samples. The results will be output, giving us the test accuracy formatted to 4 decimal places. Next, to visualize the model's performance, we can plot some predictions alongside their actual labels. This not only helps in assessing how well the network predicts digits, but also provides an intuitive understanding of its decision-making process. We'll begin by importing the matplot library for plotting, and then obtain predictions for the first 10 images from our test dataset. By using tf.argmax, we can extract the predicted labels for these images based on the model's output. Finally, we create a visually appealing display where each subplot shows an image along with the model's predicted label, making it clear how accurately the ANN recognizes the handwritten digits. The displayed figure is a line chart titled Classification Error Rate in ImageNet over the years, and it visualizes some really interesting data. On the x-axis, we have the years, from 2010 to 2016, and on the y-axis, we see the error rate, represented in percentages. Now, let's dive into the plotted values. Starting with 2010, we see an error rate of 28.2%. It then goes down to 25.8% in 2011, which isn't much of a dip, but hold on. Things get exciting in 2012, where the rate drops dramatically to 6.7%. That's a whopping decrease of 19.1 percentage points, making it the most significant change in this entire period. After that, from 2012 to 2013, we see a smaller decrease of just 1.6 points. Then it goes down by 1.5 points from 2013 to 2014, by 0.4 from 2014 to 2015, and finally just 0.1 points from 2015 to 2016. So, while the overall trend is a strong downward trajectory across these years, moving from 28.2% in 2010 to just 3.1% in 2016, a total reduction of 25.1 percentage points, you can notice that the pace of improvement really slows down after that initial leap. The markers on this line chart highlight each annual measurement, and the dashed grid lines help us read those exact values and make comparisons between years a lot easier. So, what can we conclude from this chart? Well, the most dramatic improvements seem to happen in those first couple of years, while later years show these diminishing returns when it comes to further reducing the classification error. Fascinating stuff, right? Next, we're going to delve into a crucial aspect of training our neural network, weight adjustment using the backpropagation algorithm. The line of code we'll write will show how we tweak the weights based on computed gradients. Specifically, we're going to subtract the product of the learning rate and the gradient from the current weights. This means we're effectively making a step that should bring us closer to reducing the error in our predictions. Now, the term learning rate is really important here. It determines how big that update step is. If we go with a smaller learning rate, we make more gradual changes, which can help us fine-tune our model. But keep in mind, it might also increase our training time. On the flip side, a larger learning rate can speed things up, but runs the risk of overshooting optimal weight settings, which could lead to divergence and instability. So this line is a fundamental building block for training our artificial neural network. It encapsulates the essential process of weight optimization, and getting this right will empower you to understand how neural networks improve their predictive ability over time through repeated exposure to training data and careful parameter refinement. Now let's implement a basic convolutional neural network, or CNN architecture, for our digit recognition model. And don't worry, it's going to be quite manageable. We'll kick this off by using the models.sequential class, which is perfect for building our model layer by layer. The very first layer is a conv2D layer that has 32 filters, with each filter sized at 3 by 3. This layer is super important because it applies convolution operations to extract essential features from our input images. And we'll use the ReLU activation function here to introduce some nonlinearity, which helps in learning complex patterns. Next up, we'll add a max pooling 2D layer with a pool size of 2 by 2. This pooling layer is great because it reduces the spatial dimensions of our feature maps, focusing the model on the most significant features while cutting down on any unnecessary noise. Following that, we add a second conv2D layer with 64 filters. This layer really digs in, refining those extracted features by applying even more convolutions. Then we have another max pooling 2D layer that further downsamples our feature maps. It's like giving our model a clearer view. After that, we encounter the flatten layer, which is crucial as it converts our 2D feature maps into a 1D vector. This flattened output then flows into a fully connected dense layer with 128 neurons, also using the ReLU activation. Finally, we cap it off with another dense layer, featuring 10 neurons and a softmax activation function. This setup provides output probabilities for each digit class from 0 to 9, and the best part? This architecture is crafted to significantly boost our image classification performance. After adjusting our model to a CNN, don't forget to compile and train it just like we did before. You can expect better performance from this elegant approach the CNN leverages for image data. Also, remember to keep track of your accuracy after each epoch. I know, it's easy to get caught up in the excitement, but monitoring those performance metrics is so important for understanding how well your model is really learning. Now, while we've covered a lot, the frameworks and techniques available for developing ANNs are quite extensive. Techniques like regularization, dropout layers, and data augmentation, they can all help us boost model performance and combat that pesky overfitting. You know, that's when a model learns too much from the training data and then performs poorly on unseen data. So keep these techniques in your toolkit as we work to enhance our models together. In summary, artificial neural networks, or ANNs, represent a fascinating intersection of biology and technology, enabling significant advancements in fields ranging from image recognition to natural language processing. By understanding the fundamental components of ANNs, one can leverage their power to solve intricate problems in various domains. Now, you've been introduced to the basics of building an ANN using Python and TensorFlow, along with some key techniques for improving model performance. Remember, as you dive deeper into machine learning, don't hesitate to experiment with different architectures, optimizers, and hyperparameters. The world of neural networks is vast, and creativity is your best ally in this exciting journey. Let's dive into the fascinating world of feed-forward propagation and backpropagation in artificial neural networks. These two processes are crucial to training a neural network efficiently. So let's break it down step by step. First up, feed-forward propagation. This is where data travels through the network, layer by layer, from input all the way to output. Imagine it like a line of kids passing a ball down the line, each one getting the ball, doing something with it, and then passing it on. So during this process, each neuron in a layer takes inputs, applies weights and biases, and then with an activation function, it decides whether to pass the information forward. Sounds simple, right? Well, it gets a bit more intricate, as we'll soon see. Now let's talk about backpropagation. This is like a guide helping the network learn from its mistakes. When the network makes a prediction, it checks how far off it was from the actual result, like a teacher giving feedback on a test. The error travels back through the network, adjusting those weights and biases to improve the model for the next time. It's a vital feedback loop that keeps on fine-tuning the network's performance. Now, as we explore these mechanisms further, I'll also provide some code examples to illustrate these concepts in action. You'll see how straightforward it can be to implement these ideas in programming. So stay tuned, because we're just getting started. So far, we've explored artificial neural networks, or ANNs, as a supervised learning algorithm that mimics brain function through their architecture, which consists of interconnected layers of neurons. We've also discussed the training process using backpropagation and even implemented a simple digit recognition ANN with Python and TensorFlow, making good use of the MNIST dataset. Then we took it a step further by transitioning from a basic ANN to a convolutional neural network, or CNN, to really enhance image classification. Finally, we touched on various techniques to boost model performance, highlighting the importance of experimentation in neural network development. Now, we're diving into the intricacies of how data flows through neurons by means of feed-forward propagation, and how our network learns through backpropagation. Let's break it down. When we talk about feed-forward propagation, we're referring to the way input data moves through the network from the input layer through the various hidden layers and finally to the output layer. At each neuron, the input is multiplied by weights, summed up, and passed through an activation function, which decides whether the neuron should fire. It's like the network is making decisions at every layer based on what it learned during training. And that brings us to backpropagation, which is where the magic really happens. After a forward pass is completed, the network compares the output to the expected result and calculates the error. This error then travels back through the network, adjusting the weights of the neurons to minimize that error. Essentially, it's the network learning from its mistakes. So, through these two processes, feed-forward and backpropagation, our neural network is constantly evolving, improving its ability to predict and classify data. Pretty cool, right? Let's keep unraveling this fascinating journey through neural networks. The process of feed-forward propagation, let's dive right in, begins when we input data into the neural network. Picture this. Each layer of neurons, it's like they're processing data and then passing it along to the next layer, just like sending something through a series of doors. Each door, or neuron, it applies a specific question. Think of it as an activation function to decide whether to open and let the data through. Now, mathematically speaking, when data travels from one layer to the next, we apply a linear transformation first, followed by a nonlinear activation function. For example, using the popular ReLU, which stands for rectified linear unit, it introduces that important nonlinearity that we need to model more complex relationships. So, by leveraging these layers and functions, we can really get into the intricacies of how neural networks work. Now, let's take a look at how we can implement a simple feed-forward propagation using a single-layer perceptron. We start by importing NumPy, which is essential for mathematical operations in Python. First, we're going to define the rectified linear unit, or ReLU, activation function, which will help us introduce nonlinearity to our model. The next step involves setting up our weights and biases. Here, we've chosen specific values for the weights as a two-dimensional NumPy array and initialized the bias as a one-dimensional array. With our input data prepared, we then define the feedforward function, which computes the output of the neuron. This function performs a linear transformation by calculating the dot product between the input data and the weights, followed by adding the bias. After obtaining this combined value, we apply the ReLU activation function to determine the final output. Finally, we test our implementation by running the feedforward function with submitted input and printing the output. This straightforward code structure effectively illustrates the core principles of how data flows through a single-layer perceptron and feedforward propagation. In this code, we're going to define the ReLU function, which is essential for calculating the output of each neuron. To start, we initialize a random set of weights and biases. Next, we define our input data. Now, the magic happens in the feedforward function, which computes the network's output. It does this by performing a linear transformation. Think of it as taking the dot product of our input data and these weights, and then we add the bias. Finally, we apply the ReLU activation function. It's a smooth and effective way to introduce nonlinearity into our model, allowing it to learn from the data. So let's move forward with coding this up. Now that we understand how feed-forward propagation works, let's shift our focus to backpropagation. Backpropagation is really the heart of neural network training. Its main purpose is to minimize the loss function, which quantifies how far off our predictions are from the actual labels. You can think of it as a feedback loop. After making a prediction, we need to know how to adjust our weights to improve future predictions. So during backpropagation, we calculate the gradient of the loss function with respect to each weight by applying the chain rule of calculus. This is essential because it helps us understand both the direction and the magnitude of the weight updates we need to reduce our prediction error. All right, let me walk you through a simple example of this process. You'll see how exciting it is. Now, let's dive into a straightforward example of backpropagation, following our exploration of feedforward propagation. The target variable, if you recall, represents our expected output, or true labels, super important for figuring out how much our predictions deviate from reality. Next, we're going to define a simple loss function. In our case, that's the mean squared error between the model's output and the target. This function helps us quantify how well the model is performing. When we compute the loss with this function, it shows us how well the model predicts those target values, and basically a lower loss is a sign of better performance. Now, on to backpropagation. In this process, we first compute the error by subtracting the target from the output. This gives us a peek into our prediction accuracy. Then we calculate the derivative of the loss, keeping in mind the properties of the activation function we used in our model. After that, we compute the gradients necessary to adjust our weights, using both our input data and the error from the model's output. Finally, we update those weights based on the gradients we just computed and a defined learning rate. This step is crucial because it ensures our model learns and improves its predictions with each iteration. This entire cycle, my friends, allows our neural network to refine its weight adjustments, ultimately boosting its predictive capabilities. Here, we're going to define a simple loss function to measure the error between the model's predictions and the actual labels. In the backpropagation function, we'll compute the derivative of the loss with respect to the output. This step helps us determine how to adjust the weights that our model is using. Now, once we've got those adjustments figured out, we update the weights according to a learning rate. The learning rate is crucial because it controls how much we change those weights during each update. It's like setting the pace for learning, ensuring our model improves without overcorrecting. So to recap, we define our loss function, calculate the derivative, and then adjust the weights based on that learning rate. Simple, but effective. At this stage, our neural network is equipped to learn from its mistakes. However, real-world training can get a bit messy, especially when we dive into multi-layered networks. So let's explore the ins and outs of backpropagation in a multi-layer neural network. In a more complex architecture with those extra layers, the process remains fundamentally similar, but there are a few additional steps we need to consider. Each layer's weights must be adjusted based on the gradient calculated for that specific layer. This means we need to. At this stage, our neural network is equipped to learn from its mistakes. However, real-world training can get a bit messy, especially when we dive into multi-layered networks. So let's explore the ins and outs of backpropagation in a multi-layer neural network. In a more complex architecture with those extra layers, the process remains fundamentally similar, but there are a few additional steps we need to consider. Each layer's weights must be adjusted based on the gradient calculated for that specific layer. This means we need to propagate the error backwards through each layer of the network. Let's break this down with an example. A neural network featuring an extra hidden layer. First things first, we have to tweak the feedforward step to account for this hidden layer. So imagine this. You're passing information from the input layer through to the hidden layer, making calculations along the way, and ultimately reaching the output layer. As we calculate the output, we also need to keep track of how the weights in each layer relate to the error that we observe. Whoa! This means recalculating gradients at each layer, working back from the output, adjusting the weights, and ensuring the model learns effectively. Isn't that fascinating? So now let's put this into practice and visualize how these intricate adjustments come together.
Now, let's take a look at how we can implement feed-forward propagation in a multi-layer neural network. In this code snippet, we begin by defining the weights for two separate layers, the weights from the input layer to the hidden layer and from the hidden layer to the output layer. Here, we initialize these weights using random values, establishing the essential parameters that will determine how our input data flows through the model. Next, we define a function called feedforward multilayer, which takes the input data along with our weights for both layers. Inside this function, we first compute the activation of the hidden layer by performing a dot product of the input data and the weights leading to the hidden layer, followed by applying the ReLU activation function to introduce the necessary nonlinearity. This output is then passed as input to the next layer, where we again apply the dot product with the output layer weights and the ReLU function to compute the final output. Finally, the function returns both the hidden layer's output and the final output, allowing us to inspect the flow of data through the network and see how the model transforms the input into various representations across layers. This structured approach not only highlights the computations made within the network, but also emphasizes the importance of layer-wise transformations in the learning process.
In this snippet, we're diving into the world of neural networks, specifically focusing on how we set up the weights for two layers, from the input layer to the hidden layer, and from the hidden layer to the output layer. Now, we'll adjust our feedforward function, not only to compute the output for that final layer, but also to take into account the hidden layer. This is crucial because it allows us to really understand how data moves through multiple neuron layers, capturing the intricacies of data flow. So, as we make these adjustments, think about how each layer interacts. It's like building a bridge, where every component has to work together to ensure smooth passage. Let's visualize this process as we go along, and I'll guide you through each step to make sure everything connects. Next, we need to implement backpropagation for this multi-layer structure. So, backpropagation basically involves calculating gradients, right? We do this layer by layer, moving backwards from the output layer to the input layer. Now, it's important to note that the weight updates for the hidden layers and the output layers are going to differ, because each layer has its own gradients to work with. So keep that in mind as we tackle this, yeah?
Now, let's take a moment to dive into the backpropagation process for a multi-layer neural network. The backpropagate multi-layer function is built to adjust the weights for both the hidden and output layers, and it does this based on calculated errors. First off, we calculate the error at the output layer by subtracting the target values from what our model predicted. Then we apply a derivative calculation, which uses the unique properties of the activation function to figure out how to adjust those weights. Next up, we compute the gradient for the weights that connect the hidden layer to the output. This is key, as it allows us to update these weights using a defined learning rate, making sure they align better with our predictions. Now, the process moves backward as we start propagating that error back to the hidden layer. By applying the derivative of the activation function again, we can calculate how much each weight in that hidden layer should be adjusted. It's like fine-tuning a musical instrument. Finally, we update those hidden layer weights in a similar fashion. This iterative adjustment process is super crucial for minimizing prediction errors, as it ensures our network becomes better at making accurate predictions over time. After that, the updated weights are printed out, which illustrates the learned modifications after just one step of backpropagation, a fundamental aspect in the training of neural networks.
In the backpropagation function for our multilayer network, we start by computing the error and gradients for the output layer. Now, don't worry if that sounds a bit technical. Let's break it down. Once we have those computed, we apply the same process to the hidden layer. This is crucial because it allows the network to learn from its mistakes, Next, we update the weights for both the hidden and output layers accordingly. This updating step is what helps our network refine its predictions, improving over time as it learns from the data it processes. So, step by step, we're guiding our model closer to accuracy. And that's essentially how we enhance our network's performance through backpropagation. So, why do we keep repeating feedforward and backpropagation during training? It's all about gradually improving our model's accuracy through many iterations. Each cycle adjusts the weights based on the latest prediction errors, pushing the loss down towards zero. This repetitive process, it's often encapsulated in what we call an epoch. In practice, we set the training to run over several epochs, allowing the model to learn incrementally. It's like a gradual refinement, where each round builds on the last, steadily optimizing the model. When training your neural network, it's really important to keep an eye on your loss after each epoch to make sure your model is actually learning. Now, if you notice the loss plateaus, this might be a sign to adjust your learning rate, or maybe even increase the number of layers, or try out some different activation functions. As you work through this process, you'll begin to develop a keen eye for the right hyperparameters that help your model converge to something more accurate. So keep experimenting and pay close attention to those loss values. It's all part of the journey to building a better model.
The plotted figure displays loss value over epochs during training, with epochs on the x-axis from 1 to 100 and loss values on the y-axis. Now, let's take a closer look at the main pattern here. It shows a clear exponential-like decay of loss as the training progresses. We start with a relatively higher loss value in the early epochs, and it drops sharply during that initial phase. You'll notice that steep slope in the first tens of epochs. After that, it transitions into a slower decline and approaches a low asymptotic value as we move to the later epochs. Each epoch is marked with a green circular marker connected by a green line labeled loss value. These markers reveal small random fluctuations around the overall downward trend, which indicates some noise or variability at each epoch. This aligns with a small Gaussian perturbation. Now, the grid and axis tick spacing make it clear that most of the meaningful decrease happens before roughly epoch 30. From around epoch 30 to 100, you can see the curve flattens, suggesting diminishing returns for further epochs. So, what can we conclude from this visualization? Well, it implies that the training process is converging effectively. The rapid early reduction signals effective initial learning. This suggests a suitable learning rate and model capacity, while that later plateau indicates the model is getting closer to an approximation of the minimum loss given the current hyperparameters. Those small oscillations around the trend hint at low-level stochastic updates. Keep in mind, the noise magnitude is relatively small compared to the overall drop. So if you're looking for faster convergence or a lower final loss, you might want to focus your tuning efforts on those earlier epochs, like adjusting the learning rate schedule, incorporating more data, or applying stronger regularization. Importantly, though, this figure shows only the training loss. It confirms the internal convergence behavior, but doesn't speak to generalization without a separate validation curve.
The excitement of neural networks lies in experimentation and discovery. Whether you're implementing advanced optimizations like momentum or the autumn optimizer, or using techniques such as dropout and batch normalization to prevent overfitting, there's always something new to learn and discover. It's like every time you dive deeper, you uncover a new tool or tweak that can enhance your model. So for instance, when you're playing around with the autumn optimizer, you might notice how it adjusts the learning rate dynamically, adopting as it goes. That alone can lead to some significant improvements in performance. And don't get me started on dropout. It's such a game changer for regularization. It helps you avoid that pesky overfitting by randomly dropping units during training. Batch normalization is another fascinating technique. It allows for faster training and can even provide some regularization benefits, which means you're less likely to see your model getting stuck in local minima. So the more you explore these components, the more tools you have at your disposal to tackle complex problems. Isn't that just incredible?
Now that you've got a grip on feedforward and backpropagation, you're well on your way to developing robust neural networks. But the journey doesn't end here. As you advance, you'll uncover even more sophisticated methods and practices, things that can really take your models to the next level. And hey, never underestimate the power of community and resources in this field. Online platforms, forums, and open source libraries, they can provide unparalleled insights and tools that will aid your learning and projects. And above all, remember that persistence is key. Neural networks can be intricate, but with practice, you can harness their potential to create transformative applications. So keep pushing forward.
In summary, mastering feed-forward propagation and backpropagation is a significant milestone in your machine learning journey. You now possess the fundamental tools to build and train effective neural networks from scratch. Keep experimenting and keep learning. Because as always, it's about pushing the limits of what artificial intelligence can achieve. So, dive in, get your hands dirty, and let's see where your creativity takes you next. Now, let's dive into building the components of a neural network. Understanding how these foundational elements come together is crucial for developing efficient and effective machine learning models. So far, we've learned about feed-forward propagation and backpropagation in artificial neural networks, which are essential for training efficiency. We explored how data flows through layers using activation functions like ReLU, and we even implemented a simple multi-layer perceptron. Remember, we discussed the importance of updating weights based on prediction errors through the backpropagation process. Lastly, we highlighted the significance of monitoring loss during training to really optimize model performance over multiple epochs. Now, we'll talk about how all these processes can be integrated to build a complete neural network and how Python can help us implement these components seamlessly.
Now, let's see how we can implement a simple neural network using Python. We'll start by importing the NumPy library, which is super essential for all our numerical operations. Our neural network class will really encapsulate all the functionalities of the neural network. In the constructor, we define the weights between the input to hidden and hidden to output layers. These weights are initialized with random values to help break symmetry, and we also include biases for both layers. This randomness is actually quite crucial. It helps us avoid some common issues during training. Next, we'll implement the feed-forward function, which is responsible for processing the input data through our network. It computes the activations for the hidden layer by taking the dot product of the inputs and the weights, adding in those biases, and then applying the ReLU activation function. This entire process continues on to the output layer, where we calculate the final activations and return them. Let's take a closer look at the ReLU method, which is where we implement the ReLU activation function. This method returns the maximum of 0 or the input value, ensuring that only positive activations are passed forward. So you can see how this structure forms the backbone of our neural network, allowing it to learn from the incoming data and make predictions effectively.
Next, we will implement the mean squared error function, which is essential for calculating the training loss during the model's learning process. This function takes two parameters, the true values and the predicted values, and it returns the average of the squared differences between them. This provides a clear measure of how well our model is predicting the target values. Following that, we'll define the backpropagation method, which performs the critical task of updating the model's weights based on the calculated errors. Here, we first compute the output errors by subtracting the predicted outputs from the actual target values. These output errors are then used to calculate the. Next, we will implement the mean squared error function, which is essential for calculating the training loss during the model's learning process. This function takes two parameters, the true values and the predicted values, and it returns the average of the squared differences between them. This provides a clear measure of how well our model is predicting the target values. Following that, we'll define the backpropagation method, which performs the critical task of updating the model's weights based on the calculated errors. Here, we first compute the output errors by subtracting the predicted outputs from the actual target values. These output errors are then used to calculate the hidden layer errors, taking into account the weights and the derivative of the ReLU activation function to adjust back through the network. In the weight update step, we adjust the weights for both the hidden to output and input to hidden layers by applying the learning rate. This learning rate is essential as it determines the magnitude of the updates. Finding that careful balance is crucial as it influences both the convergence speed and stability of the learning process. Additionally, we will implement the ReLU derivative function, which helps derive the gradient needed for backpropagation by returning an array indicating where the neuron's input exceeded 0.
Next, we're going to implement the train method for our neural network class, which is super important for training the model over multiple epochs. This function takes four parameters, our input features x, the target values y, the number of epochs for training, and the learning rate. Inside this method, we use a for loop that iterates through each epoch. So during each iteration, what's happening is our model makes predictions by running the Feedforward method, which processes the input and calculates the output based on the weights we've initialized. After we get those predictions, we compute the loss using the mean squared error function. This is essential for measuring how close our predicted values are to the actual targets, so quite critical for understanding our model's performance. Then we perform backpropagation via the backpropagation method, which adjusts the weights to minimize errors based on that calculated loss. Oh, and here's an important point. We include a logging mechanism that outputs the loss every 100 epochs. This little feedback loop helps us keep an eye on the training progress, allowing us to make any necessary adjustments to the learning rate or our model's structure if we need to. By regularly evaluating the loss, we gain valuable insights into how effectively our model is learning over time.
The figure titled Loss Variation over Increasing Epochs displays our per epoch loss values, where the x-axis represents epochs and the y-axis shows loss value. It uses a blue line with circular markers at each epoch, all laid out on a helpful grid for readability. So, what we've got here is a clear pattern, an initial rapid decline in loss during those early epochs, followed by a leveling off. This is significant because it indicates that the model is learning quickly at first. Those parameters are really finding their footing in the better regions of the loss surface. But then, as training goes on, we hit those diminishing returns. You'll see that superimposed on this downward trend are little erratic ups and downs at individual epochs. These fluctuations, they reflect noise in the loss signal and suggest some stochastic variation in updates. Think of it as simulated measurement noise. Now, as we move toward the right side of the plot, the curve starts to approach a shallow plateau with only minor oscillations. This implies that the model is converging, and as we go through more epochs, we're really seeing those incremental improvements become smaller and smaller. So what can we conclude from this visualization? Well, first, it tells us that the training process is effectively reducing loss overall. Second, most of the progress happens early on, while later epochs tend to offer these smaller gains. And third, those occasional spikes or rebounds in loss signal that we might be dealing with noise or perhaps a learning rate that's too large.
Based on these observed patterns, actions like reducing the learning rate, applying some smoothing techniques like moving averages for monitoring, or even considering early stopping when the curve plateaus can really be warranted. Now, let's implement a simple dataset generation and neural network training process. We'll start by using NumPy to create a synthetic dataset that embodies a linear relationship, which will help our model learn effectively. Here, we set a random seed to ensure reproducibility, and then we generate 100 random input values. Our output values are computed based on a linear equation with some added Gaussian noise, introducing variability that mimics real-world data. Next, we normalize both our input and output values. Normalization is super important. It standardizes the data range, which really helps with efficient training, as it ensures that our neural network can converge faster. Following this, we'll initialize our neural network class, specifying the architecture with one input node, 5 hidden nodes, and one output node. This structure allows the model to learn the complexities of the data effectively. Finally, we initiate the training process for 1,000 epochs with a specified learning rate. During training, the model will iterate through the dataset, refining its parameters to minimize prediction errors gradually. This setup really lays down the groundwork for a robust model capable of approximating the underlying linear relationship in our synthetic data.
Now, let's implement the plotting functionality to visualize our neural network's predictions. First, we're going to use the feedforward method of our neural network to make predictions on our input data, which, if you're with me, computes the output based on the trained model's weights. This gives us our predicted linear trend line. Next up, we'll plot the original noisy data points as blue dots. Think of these as representing the actual observations. Then we're going to overlay that predicted line on our scatter plot in red. This way, we can visually assess just how well our neural network has learned the underlying pattern. Now, we'll include a legend to clarify which color is which, blue for the original data and red for our model's fit. Finally, we'll display the result with plt.show, which, you guessed it, will render the plot for us to analyze. Now, ideally, after training, we want to see that red line aligning closely with the general trend of those blue points, which indicates that our model has effectively captured the relationship in the data. This visualization not only confirms the efficacy of our neural network, but also enhances our understanding of its performance in a tangible way.
Remember, this is just the tip of the iceberg when it comes to building neural networks. The potential for improvement is virtually limitless, from experimenting with different architectures and activation functions to incorporating advanced techniques like dropout for regularization. As you explore this field more, you'll discover techniques such as convolutional neural networks, which are fantastic for image-related tasks, or recurrent neural networks that excel with sequential data. Each method has its own unique components and nuances, but at the heart of it all, the core principles of feedforward, backpropagation, and weight optimization remain key. So as we wrap up this segment, keep in mind the building blocks we've assembled here, the ways we can take in data, how we process it through layers, and how we learn from our mistakes. Each of these segments is paramount in training a successful neural network, and with tools like Python at our disposal, we can continue to iterate and innovate.
Thank you for joining me in this exploration of neural networks. I hope you're feeling more confident in your ability to build and train these models. Because whether you're diving into this for academic reasons, kind of dabbling as a hobby, or even looking at it as a stepping stone into a career in AI, the skills you're honing here are truly invaluable. So let's keep pushing the boundaries of our understanding as we dive even deeper into the fascinating world of machine learning.
Neural networks are incredibly powerful tools for solving complex problems in machine learning, but training them effectively is crucial for optimal performance. In this lesson, we'll dive into the essential process of training neural networks using gradient descent, where our goal is to minimize the loss during the training phase. Today, we'll explore how feedforward propagation and backpropagation work together. They refine our model iteratively to achieve minimal loss. So let's break it down step by step, starting with feedforward propagation, which is essentially how our input data makes its way through the network. Imagine we're feeding data in, layer by layer, and this produces an output. Now, this output isn't perfect, right? And that's where backpropagation comes in. It's like the network's way of learning from its mistakes.
By calculating the error and pushing that information back through the network, it helps adjust the weights to improve performance. So with each iteration, both feedforward and backpropagation work hand in hand, enabling us to refine our model inch by inch. Remember, effective training requires patience and practice, so don't rush the process. In upcoming lessons, we'll delve deeper into these concepts, equipping you with the knowledge to train your neural network successfully. So far, we've learned about the key components involved in building a neural network, including the input layer, hidden layers, and the output layer. We also covered how to initialize weights and biases. We explored the processes of feed-forward propagation and backpropagation, focusing, of course, on the importance of weight updates and monitoring loss for effective training. Additionally, we implemented a training method that allows us to iteratively improve our model's performance using a synthetic dataset. Overall, these foundational elements are essential for developing and refining machine learning models. Now, let's explore gradient descent, the backbone of the training process for neural networks. So, simply put, gradient descent is an optimization algorithm used to minimize the loss function. It does this by iteratively adjusting weights in the opposite direction of the gradient of the loss function. Now, what do we mean by gradient? Well, the gradient tells us the direction in which the loss is increasing most steeply, and by moving in the opposite direction, we aim to decrease the loss. It's all about finding the most efficient path to improve our model's performance. Now, let's implement the mean squared error function, which is crucial for calculating our loss during training. This function takes two parameters, yTrue, which contains the actual labels from our dataset, and yPred, the predictions that our model outputs after a feed-forward pass. So what does this function actually do? Well, it computes the mean of the squared differences between these two sets of values, giving us a scalar loss value that indicates how well our model's predictions align with the true labels. By minimizing this loss, we can iteratively update our weights, which helps improve our model's performance during training. This straightforward definition captures the essence of loss calculation that drives the gradient descent process. Smaller loss values mean more accurate predictions. In essence, this function serves as the foundation for our gradient descent approach, enabling us to evaluate the accuracy of our model effectively and guiding our weight adjustments in the subsequent training steps. Thoughtful pause. Understanding and implementing this function equips us with a key tool for refining our neural network and achieving our optimization goals.
Now, let's take a look at how we can implement the backpropagation method within our neural network class. The first step in this process, super important by the way, is to compute the output errors. These errors represent the difference between the actual target values and the predictions we've made with our model. This calculation is crucial as it highlights just how far off our predictions are, which really guides us on where to adjust the model. Next up, we need to calculate the hidden layer errors derived from those output errors. This is done by performing a dot product with the transposed weights connecting the hidden layer to the output layer. And let me tell you, this step is essential. It informs us of how significant the output errors were on the hidden layer neurons, enabling effective error propagation. Once we have both error values sorted out, the next part of the code updates the weights using the gradients computed from these errors. We scale these gradients by the learning rate, which is key. We're adjusting the weights between the hidden and output layers, as well as between the input and hidden layers. This application of gradients really reinforces our understanding of gradient descent, which, as you may know, minimizes loss by guiding weight updates in the direction that decreases error. So, this backpropagation method, it plays a pivotal role in refining our neural network's performance through those repeated learning cycles.
Now, let's take a look at a function designed to visualize the training loss over epochs, which is super important for assessing the model's learning process. This function is called plot loss, and it takes one parameter, loss history, which is a list of loss values collected during training. Inside this function, we're going to use matplotlib to create a plot that shows how the loss decreases over time, giving us a nice representation of each epoch. We start by plotting the loss history against epochs using a blue line, which gives us a clear visual of the model's performance throughout the training iterations. The title, Loss Reduction over Epochs, gives context to what we're looking at, and the x-axis, labeled epochs, helps us see the progression of training. On the y-axis, we have loss, which shows the magnitude of loss, helping us evaluate changes in model performance. By adding a grid to the plot, we make it easier to read, allowing us to pinpoint specific values with a glance. Finally, we call plt.show to render the plot, letting us visually assess how well the model is learning, whether it's reaching a stable low loss or oscillating wildly. This visualization is really key in determining optimal learning rates in fine-tuning our training process.
The displayed figure titled Effect of Learning Rates on Loss over Epochs illustrates the changes in loss values over 100 epochs for 3 different learning rates. Each learning rate is represented with a distinct marker and color: blue circles for learning rate 0.01, green squares for learning rate 0.1, and red X's for learning rate 0.5. If we take a closer look, all 3 curves trend downward overall, meaning that as the epochs increase, the loss decreases, which indicates that the model is learning in every case. However, there are some notable differences in speed and stability among them. The blue curve, representing a learning rate of 0.01, displays a gradual and relatively smooth exponential-like decay and loss, coupled with small point-to-point variance. This means we have slow but stable convergence here. Now, the green curve at 0.1 descends more quickly than the blue one, reaching those low loss values earlier with some modest fluctuations. This suggests a good balance between convergence speed and stability. But let's check out the red curve, which corresponds to a learning rate of 0.5. It drops steeply at first, indicating a very rapid initial reduction in loss. But it exhibits larger fluctuations and noisier behavior across epochs, sometimes oscillating rather than steadily decreasing. This pattern hints at instability and the risk of overshooting the minima. So, from these patterns, we conclude that a very small learning rate gives us stable but slow training, whereas a very large learning rate can deliver rapid initial improvements at the cost of unstable convergence. Meanwhile, that mid-range learning rate, like our example of 0.1, often strikes a practical balance between speed and stability for this setup. Lastly, the legend, axis labels, those include epochs and loss value, and the grid all help to clarify these comparative trends across the full range of 1 to 100 epochs.
Now, let's dive into implementing the training method for our neural network, allowing it to learn and adopt over multiple epochs. We'll kick things off by initializing an empty list called loss history. This is where we're going to track the loss at each training epoch, and it's super important for our analysis later on. As we work through the specified number of epochs, the network is going to generate predictions using the Feedforward method. Now, at this point, we'll compute the error using the mean squared error function. This will help us understand how well our model's predictions are matching up with the true labels. Each time we calculate the loss, we'll append that value to our loss history, capturing the model's performance over time. This historical data, let me tell you, is going to be crucial for analyzing the training process. It also allows us to visualize the learning curve, which is really helpful. After calculating the loss, we'll call the backpropagation function. This is where the magic happens, adjusting the model's weights based on the gradients derived from that loss. To keep track of how we're doing, we'll provide feedback every 100 epochs. That's right, we'll log the current epoch along with the associated loss. This feedback loop not only helps us monitor progress, but also aids in fine-tuning the model's hyperparameters. Finally, once all the training is done, we'll return the loss history. This step is essential because it allows us to visualize how the loss has evolved throughout training. So, let's get into it. Now, let's implement dropout, a really useful technique that helps prevent overfitting by randomly disabling a fraction of neurons during the training process. In the dropout function, we first check if the specified dropout rate is less than 1. This indicates that yes, we want to apply dropout. If that's the case, we create a mask using a binomial distribution to randomly select which neurons will stay active. Each neuron has a probability of remaining active that's based on the dropout rate we provide. Following this, we multiply the layer's output by the mask, effectively setting the outputs of the dropped neurons to 0. But to maintain the scale of the output, we also divide by 1 minus the dropout rate. This scaling ensures that the expected sum of the outputs remains unchanged, allowing the model to generalize better during training. Now, if the dropout rate is set to 1 or greater, we simply return the original layer output with any modifications. This function, you see, not only enhances the robustness of our model, but also contributes significantly to improving its generalization to unseen data, making it a really valuable addition to our neural network training process. As we wrap up our discussion on training neural networks with gradient descent, I want to emphasize just how crucial each concept we've explored today really is. Understanding how to propagate errors and adjust weights is fundamental for improving your model's performance. The iterative process of gradient descent allows us to refine our model, inching ever closer to that optimal state. With this strong foundation, you're now much better equipped to tackle more complex architectures and datasets. Sure, training neural networks can take time and patience, but by applying these principles, you're on a solid path to mastering this essential element of machine learning. Thank you for joining me in this exploration. Stay curious and keep experimenting.
Activation functions play a crucial role in the performance of neural networks, acting as gatekeepers of information. By introducing nonlinearity, they help the network learn complex patterns in the data. In this lesson, we will take a deep dive into activation functions, why they are necessary, and how they influence the capabilities of neural networks. So far, we learned about the importance of training neural networks using gradient descent to minimize loss effectively. We explored how to calculate and use gradients to adjust weights during the backpropagation process, ensuring optimal model performance. Additionally, we discussed the significance of choosing an appropriate learning rate and its impact on training stability and convergence speed. Finally, we touched on techniques like dropout to enhance model robustness and prevent overfitting during the training process. Now we will focus on understanding activation functions and their impact on neural networks. Now let's take a look at a simple implementation of a neuron in Python. The code begins by importing the NumPy library, which is essential for efficient numerical computations. We define a class called neuron to encapsulate the behavior of our neuron model. In the constructor method init, we initialize the neuron's weights and bias, allowing for customizable parameters that influence the neuron's output. Next, we implement the forward method, which performs the key operation of the neuron, computing the output. It takes an array of inputs, calculates the dot product with the weights, adds the bias, and returns the resulting output. This straightforward calculation demonstrates how the neuron processes the inputs linearly. In the example usage section, we instantiate a neuron with predefined weights and bias. By passing a sample input through our neuron's forward method, we can observe the output produced without any activation function applied. This example emphasizes the linear nature of the neuron and sets the stage for understanding how activation functions will later transform this output and introduce nonlinearity into the model. Now let's implement the ReLU activation function in Python. We first define a function called ReLU, which takes an input x. Within this function, we utilize NumPy's maximum method to effectively apply the ReLU operation, returning the maximum between 0 and the input value. This means that any negative output from a neuron will be set to 0, while positive outputs remain unchanged. This characteristic is particularly important as it helps avoid the vanishing gradient problem that can affect other activation functions, particularly in deep networks. After defining the ReLU function, we apply it to the neuron's output, which we assume has already been calculated. This is done by calling ReLU output, and the result is stored in a variable named output ReLU. Finally, we print the transformed output using a descriptive message, showcasing the effectiveness of the ReLU activation function in converting raw neuron outputs into actionable values for training our neural network. By using this simple yet powerful activation function, we enhance the model's ability to learn complex patterns and improve its training efficiency. Now let's implement the sigmoid activation function in Python. The sigmoid function is defined as 1 divided by 1 plus the exponential function of the negative input. This mathematical formulation allows the function to map any real-valued number into the range between 0 and 1, which is particularly useful when dealing with binary classification tasks in neural networks. In the code, we define a function called sigmoid that takes an input array x. Inside this function, we utilize NumPy's exp method, which efficiently computes the exponential of each element in the input array. The formula is then applied to transform these values accordingly. Next, once we've defined our sigmoid function, we can apply it to the outputs obtained from our previous layer. By calling this function with the variable output, we obtain the output sigmoid, which represents the activation resulting from the sigmoid function. Finally, we print the output to see the transformed values after applying the sigmoid activation. This demonstrates how we can incorporate nonlinearity into our model's predictions, essential for improving learning capabilities in neural networks. Now let's see how we can implement the tan activation function in our neural network. This function is crucial for introducing nonlinearity, allowing the network to learn complex patterns more effectively. In the code, we define a function named tan, which takes an input x and applies numpy's built-in np-tan function. This efficiently computes the hyperbolic tangent of the input values, ensuring that the output is bounded between -1 and 1. Next, we apply this activation function by calling tan with the calculated output from a previous layer or a neuron. The resulting output tan will contain the transformed values, and then we print these values to observe the effect of the activation. By centering the data around 0, the tan function helps facilitate better convergence during training, enhancing the learning process. This implementation demonstrates how nonlinear transformations significantly contribute to the depth and capability of neural networks in capturing intricate relationships within the data. The plotted figure displays the three activation functions over the input range from -10 to 10 with the horizontal and vertical axes marked at 0, and each curve labeled ReLU in blue, sigmoid in red, and tan in green. Visually, ReLU is flat at 0 for all negative inputs and transitions to a straight line with slope 1 for positive inputs, producing a distinct kink at the origin. This indicates no output or gradient for negative inputs and a constant unit gradient for positive inputs. The sigmoid curve is an S-shaped function that smoothly rises from near 0 for large negative inputs to near 1 for large positive inputs, passing through 0.5 at x equals 0. Its slope is shallow in the tails, showing saturation where gradients become very small. The derivative at x equals 0 is 0.25, and it declines rapidly away from the origin. The tan curve is also S-shaped but centered around 0, rising from -1 to 1 and passing through 0 at x equals 0 with a steeper slope near the origin than sigmoid. Its derivative at 0 is 1. This symmetry means outputs are 0-centered, which reduces bias shifts in the next layer. From these patterns we can conclude, ReLU preserves gradients for positive activations and avoids saturation on that side but yields 0 gradients for negative inputs, risking inactive neurons. Sigmoid suffers from saturation in both tails, which promotes vanishing gradients in deep networks, and tan mitigates some vanishing gradient effects by being 0-centered and steeper around the origin while still saturating at extremes. This visual comparison directly supports why ReLU is often chosen for deep hidden layers, why tan can be preferable to sigmoid in hidden layers due to centering, and why sigmoid remains common at outputs for probabilities despite its gradient limitations. Now let's see how we can implement a simple neural network with one hidden layer using the ReLU activation function for nonlinearity, followed by a sigmoid function at the output layer for binary classification. We start by defining a class called SimpleNN, which will encapsulate our network's architecture. In the init method, we initialize two sets of weights and biases, one set for the hidden layer and another for the output layer. The weights are randomly generated to break the symmetry, ensuring diverse learning in the network. In the forward method, we compute the output of the network by first calculating the hidden layer's values using the ReLU activation function. This allows us to introduce nonlinearity, enabling the network to learn more complex relationships. We then pass the activated hidden layer output to the sigmoid function to generate the final output, which predicts probabilities for binary classification tasks. Finally, we demonstrate how to use our SimpleNN class by initializing it with specific input, hidden, and output sizes, feeding in some example data, and then printing the final output. This showcases the fundamental concept of how neural networks process and learn from data through layered activations. Now let's implement the leaky ReLU activation function, a popular variant of the standard ReLU. This function addresses the issue of the dying ReLU, where neurons can become inactive and stop learning when they predominantly output 0. The leaky ReLU allows for small, non-zero gradient when the input is negative by introducing a small slope, controlled by a parameter \\alpha\. In our implementation, we define a function called leaky_ReLU that takes an input \x_ and an optional \\alpha_ value which defaults to 0.01. The function utilizes numpy's where method to efficiently assess each element in the input array. If the element is greater than 0, it retains the original value. If it is less than or equal to 0, it multiplies the input by \\alpha\. By applying this modified activation function to our neural network's output, we ensure that even negative inputs contribute to learning, potentially improving performance in deeper models. We can see the result printed out, showing the new outputs after the leaky RayLU activation has been applied, emphasizing the importance of maintaining neuron activity across all input ranges. In conclusion, activation functions are fundamental to the functioning of neural networks. They enable learning through nonlinear transformations, allowing networks with multiple layers to approximate and model complex relationships. Without them, no matter how deep your network is, it would fall flat on its face like a pancake, essentially only performing linear operations. Moving forward, understanding the strengths and weaknesses of various activation functions will empower you to choose wisely when designing your neural networks. So in the upcoming lessons, we'll dive further into how to fine-tune these networks and explore some advanced techniques for optimization. Always remember, in the world of neural networks, the choice of activation function can make all the difference. Now let's implement the mean squared error (MSE) function to evaluate the performance of our neural network. We start by importing the NumPy library, which provides essential functions for numerical operations. The mean squared error function is defined to take two parameters, ytrue, the actual output values, and ypred, the predicted output values from our model. Inside this function, we compute the MSE by utilizing NumPy's mean function to calculate the average of the squared differences between the true and predicted values. This straightforward calculation provides a single metric that reflects how well our neural network is performing. After defining the MSE function, we demonstrate its usage by creating example arrays for true and predicted values. With those arrays in place, we call the mean squared error function and print the result, showcasing how the function effectively computes the loss. This loss value is crucial as it informs us how far off our predictions are from the actual outputs, guiding subsequent adjustments during backpropagation. By integrating this function into our workflow, we lay the groundwork for optimizing our neural network through continuous learning. Now let's implement the following code for our simple neuron class, which encapsulates the core functionalities of a single neuron in our neural network. The init method initializes the weights and bias for the neuron, employing random values to break symmetry. In the forward method, we take the inputs and compute the neuron's output by calculating the weighted sum of the inputs plus the bias, followed by passing that sum through the sigmoid activation function to introduce nonlinearity into the model. Next, we define the sigmoid method, which implements the sigmoid function itself. This function is crucial for ensuring that the output of our neuron remains between 0 and 1, enabling us to interpret the output as a probability. Moving on to the backward method, this is where backpropagation occurs. The method takes the true labels and the learning rate as input. It computes the gradients necessary for updating the weights and bias, calculating how the loss with respect to the predicted output changes through the gradients derived from the activation function. Finally, we adjust the weights and bias using these gradients scaled by the learning rate, effectively allowing the neuron to learn from the errors in its predictions and improve its performance over time. Now let's see how we can implement backpropagation in action with a simple training routine using our previously defined simple neuron class. We begin by creating some sample input data and the corresponding expected output. This setup is crucial as it enables the neuron to learn the relationship between the inputs and the expected outputs during the training phase. Next, we initialize an instance of the simple neuron, specifying the input size and setting a learning rate for weight updates. The learning rate controls how much to adjust the weights with respect to the calculated gradients during backpropagation. Following this, we establish a training loop that iterates for 1,000 epochs, allowing our model ample opportunities to learn. Within each epoch, we conduct a forward pass through the neuron for each input in our dataset, gathering the predictions. These predictions help us determine how well our neuron is performing compared to the expected outputs. After gathering predictions, we perform the backward pass utilizing the true labels, which computes the gradients and updates the neuron's weights and bias. Finally, we display the final predictions after training, enabling us to evaluate the effectiveness of our implementation of backpropagation and the adjustments made throughout the training process. The displayed training curves summarize model behavior across 10 epochs. In the top subplot, loss versus epochs, the training loss blue steadily decreases from 0.6 down to 0.1 over the epochs, indicating the model is fitting the training data progressively better. The validation loss orange initially decreases from 0.65 to a minimum near 0.48 at epoch 4, then reverses and increases to about 0.65 by epoch 10. This divergence, monotonic decrease in training loss alongside rising validation loss after epoch 4, is a clear sign that the model begins to overfit the training data shortly after that point. In the bottom subplot accuracy versus epochs, the training accuracy green climbs continuously from 0.6 to 0.97, while validation accuracy red rises early to a peak around 0.76 at epoch 7 and then declines to 0.7 by epoch 10. Note the mismatch between the epoch with minimum validation loss, around epoch 4, and the epoch with maximum validation accuracy, epoch 7. Different metrics can suggest different optimal stopping points, so the choice of validation criterion depends on whether minimizing error or maximizing accuracy is the priority. Taken together, these curves show a model that has sufficient capacity to drive training metrics to near-perfect values, but begins to generalize worse after a few epochs. Practical remedies suggested by these patterns include selecting an early stopping point between epochs 4-7 based on your chosen metric, applying regularization, weight decay, dropout, or increasing validation data to improve generalization. Now let's take a look at how we can extend our implementation to create a multi-layer perceptron MLP. In this code snippet, we define a class called MLP which takes three parameters: input size, hidden size, and output size. This design allows us to specify the number of neurons that will be present in the hidden and output layers. Within the init method, we instantiate two simple neuron objects, one representing the hidden layer and another representing the output layer. This structure enables us to build a network that can process inputs through multiple layers, enhancing its ability to learn complex functions. Next, we implement the forward method, which handles the forward pass of the network. This method takes an array of inputs, processes them through the hidden layer first, and then passes the output from that layer to the output layer. The final output is then returned. For backpropagation, the backward method is responsible for adjusting the network's weights based on the errors in predictions. It first adjusts the weights of the output layer using the true labels, and then propagates the error back to the hidden layer to fine-tune its weights accordingly. Through this structure and method, the MLP can effectively learn from the data over multiple layers. Now let's implement the MLP to train on our sample data, further demonstrating the power of backpropagation across layers. We start by initializing our MLP with two input features, two hidden neurons, and one output neuron. A learning rate is set to manage the adjustments during training. The core of the training process is structured in a loop that iterates 1,000 times, representing epochs of training, allowing the model to gradually learn from the inputs. Within this training loop, we take each input sample in turn. During the forward pass, we compute predictions by passing the input through the layers of the MLP. This process utilizes the weights and biases defined within the model to produce an output prediction. Following the forward pass, we perform the backward pass, where we compute the error gradient using the true labels. This step includes updating the weights of the MLP based on the calculated gradients, allowing the model to learn from its mistakes. Finally, after training, we evaluate our MLP by passing the sample data through it once more to show its learned predictions. This code exemplifies how backpropagation effectively optimizes a multi-layer neural network for improved predictive performance. In conclusion, mastering backpropagation in Python is fundamental for anyone looking to delve deep into neural networks. This algorithm not only optimizes model performance, but also fundamentally enhances your understanding of how neural networks learn. As we develop more intricate architectures, the principles of backpropagation and the chain rule will continually serve as the backbone of effective neural network training. Moving forward, you will now have the foundational skills to explore more advanced topics in deep learning, such as optimization techniques, regularization strategies, and handling various data types. So keep the momentum going, and let's continue to push the boundaries of what you can achieve with neural networks. Neural networks have transformed the landscape of technology, enabling us to generate content in innovative ways. Today, we'll be diving into the practical applications of neural networks, specifically through the lens of generative AI. So far, we learned about the significance of backpropagation in training neural networks, focusing on its two phases, the forward pass and backward pass, which adjust weights based on errors. We discussed loss functions like mean-squared error and implemented it in Python, alongside deriving gradients using the chain rule to update weights effectively. Additionally, we explored the concept of a simple neuron and then progressed to a multi-layer perceptron MLP structure, demonstrating how backpropagation can operate across multiple layers for enhanced learning. Finally, we emphasize the importance of understanding these foundations as we delve deeper into advanced deep learning topics. Now we will talk about how neural networks, especially in the context of generative AI, are applied to create content across various mediums. Now let's implement the following code to create our generator model for the GAN. We start by importing necessary libraries like NumPy, Matplotlib, and the TensorFlow Keras components needed to build our neural network. After loading the MNIST dataset, we normalize the images to ensure that the pixel values are between 0 and 1, making it easier for the model to learn. The images are then flattened to a 784-dimensional vector, since our generator will output 28x28 images. Next, we define the generator model using a sequential architecture. The generator consists of two dense layers. The first layer has 128 neurons with RayLU activation, followed by a second layer that outputs 784 values with sigmoid activation. This transforms the input noise into a format suitable for reshaping into the desired image dimensions. Now let's see how we can create a function called GenerateImages to sample random noise and produce images using our generator. This function generates a specified number of noise samples and uses the generator to create images from that noise. Finally, we visualize the generated images in a grid format, showcasing the patterns learned by the model. The figure titled Impact of Number of Training Samples on Model Accuracy plots accuracy on the vertical axis, range 0 to 1, against the number of training samples on the horizontal axis with discrete values 500, 1000, 2000, 4000, and 8000. Two series are shown, training accuracy blue and validation accuracy red. Both curves increase monotonically as the number of samples grows, indicating that adding data improves model performance on both training and held-out validation sets. The training accuracy remains higher than validation at every point, revealing a persistent train-validation gap, but that gap generally narrows as sample size increases, approximately a 0.1 gap at smaller sizes down to around 0.050, 0.7 at larger sizes, signaling reduced overfitting with more data. Notably, the largest jump in validation accuracy occurs between 1,000 and 2,000 samples, 0.6 right arrow 0.75, suggesting a threshold where additional data yields substantial generalization gains. Beyond that, improvements continue but with smaller increments, consistent with diminishing returns. By 8,000 samples, both training and validation accuracies approach the high 0.80-9 range, demonstrating that sufficient data volume can yield strong performance and bring validation accuracy much closer to training accuracy. The figure therefore supports the practical conclusion that increasing dataset size is an effective strategy to improve generalization and reduce the train-validation gap for models. Now let's take a look at how to implement a variational autoencoder VAE using Keras. We begin by defining the encoder, which accepts the input data shape of 28 by 28 pixels flattened into a single dimension. It then creates a hidden layer with 128 neurons activated by the RayLU function. The encoder outputs two latent variables, the mean and log variance, which represent the learned distribution of the input data in the latent space. Next, we define a sampling function that utilizes these latent variables to generate random points in the latent space. This function uses the epsilon value generated from a normal distribution, adjusted by the mean and log variance, allowing for variability in the sampled outputs. By employing a lambda layer, we integrate this sampling function into our model architecture. Following this, we construct the decoder, which mirrors the encoder's structure, first processing the sampled latent representation before producing the final output. The decoder outputs a reconstructed image, also using a sigmoid activation function to ensure that pixel values are scaled between 0 and 1. Finally, we compile the entire VAE model with the atom optimizer and a binary cross-entropy loss, setting the stage for training this generative model to produce coherent samples that capture the essence of the original input data. Now let's see how we can implement a simple long short-term memory LSTM model for text generation. First, we start by preparing our text data. We use the tokenizer from Keras, which converts our text corpus into sequences of integers, making it easier for the model to process. By fitting the tokenizer on the corpus, we build a vocabulary of unique words and determine the total number of words. Next, we create input sequences by iterating through each line of the corpus, breaking it down into n-grams. This allows us to prepare sequences of words for the model to learn from. After forming these sequences, we pad them to ensure uniformity in input size, maintaining compatibility with the LSTM layers. Moving forward, we segment the input sequences into features X and labels Y, where the labels represent the next word in the sequence. We then categorize these labels with one-hot encoding using Kira's utilities. Finally, we construct the LSTM model. First, an embedding layer that transforms integer-encoded data into dense vectors, followed by two stacked LSTM layers for capturing temporal dependencies, culminating in a dense layer that predicts the probabilities of the next word in the sequence. The model is compiled with a categorical cross-entropy loss function and atom optimizer, making it ready for training. Now let's see how we can implement a function to generate text using our trained LSTM model. The generateText function takes an initial seed phrase and a specified number of words to generate. Within the function, we iterate for the number of words we want to predict. For each iteration, we first convert the seed text into a sequence of integers using the tokenizer, which maps words to their respective unique indices. Then we use padding to ensure the input sequence matches the expected length required by the model. The model is utilized to predict the next word's index through its predict method. An important aspect of this function is how it searches through the tokenizer's word index to retrieve the actual word corresponding to the predicted index, appending it to the seed text. This iterative process continues, allowing the model to generate a coherent phrase based on the initial input. Finally, the complete seed text, now augmented with the generated words, is returned. This implementation highlights the effective use of the trained model to dynamically create text that can take different directions based on the initial input, showcasing LSTM's capability in text generation. Now let's see how we can implement a neural network for music generation using the Music21 library. We start by loading a MIDI file with the converterParse method, which allows us to analyze and manipulate the musical data. Once the MIDI file is loaded, we create an empty list called notes to store the distinct pitches we extract from the musical stream. The code iterates through each element in the stream, specifically examining the notes. If the element is a note, we append its pitch to our notes list, effectively creating a dataset of musical notes. Once we have our dataset, we shift our focus to training a recurrent neural network RNN on the notes we extracted. While the RNN architecture is not defined in the code snippet, it should follow similar principles as prior examples. With the trained model, we can then generate a sequence of notes by calling a generateMusic function, which uses a seed note and specifies the number of notes to produce. Each note in the generated sequence is instantiated as a note. Note object and appended to the musical stream. Finally, we call stream show MIDI to play the generated music, allowing us to hear the creative output of our neural network. In conclusion, the practical applications of neural networks showcase their versatility across domains. From image and text generation to music composition, generative models like GANs, VAEs, LSTMs, and RNNs enable creativity that reflects the learned data. Today, we explored how to implement these models and generate various types of content, providing a glimpse into the power of neural networks in reshaping industries. As technology advances, these neural networks will continue to evolve, leading to even more sophisticated applications in generative AI. A world where machines can create art, music, and literature tailored to our tastes isn't just a dream, it's happening today. So put on your thinking caps and dive into the fascinating universe of generative AI, where the possibilities are as endless as your imagination. Welcome. Today we are going to explore the implementation of neural networks using PyTorch, one of the most popular deep learning frameworks in the industry. By the end of this session, you'll have a solid understanding of how to set up, train, and evaluate a neural network in PyTorch. So far, we learned about the transformative role of neural networks in technology, particularly in generative AI. We explored foundational concepts like backpropagation and its application in multi-layer perceptrons, followed by the innovative architectures of GANs and VAEs for content generation. We also discussed the use of LSTMs for text generation and RNNs for music composition, showcasing the versatility of neural networks across various creative domains. These insights underline the potential of neural networks to reshape industries and create tailored artistic outputs. Now, let's dive into the implementation realm. Now let's implement the necessary transformations for our dataset using PyTorch's TorchVision library. We start by defining a sequence of operations to prepare our data for training. The transforms compose method allows us to chain multiple transformations together. In our case, we first convert each image to a tensor using transforms to tensor, which also scales the pixel values to the range 0, 1. Following that, we standardize the images by normalizing them to have a mean and standard deviation of 0.5, making the training process more efficient. Next, we create the training and testing datasets using the datasets MNIST class, specifying parameters like the dataset's storage location and whether it should be downloaded if not already present. Once we have our datasets, we use Torch Utils data loader to facilitate efficient batching and shuffling of the training data, which enhances the training process by providing random samples that help the model generalize better. Now let's visualize some of the downloaded MNIST examples. We define a function that fetches a batch from our training loader, uses Torch Vision Utils, make grid to arrange the images in a grid, and then displays them using matplotlib. This visualization helps us understand what our input data looks like before feeding it into the neural network, setting a solid foundation for our training process. Now let's implement our data transformations for the MNIST dataset. We begin by using transforms composed to create a sequence of data preprocessing steps. The first transformation, transforms to tensor, converts the images into PyTorch tensors, which is necessary for the model to process them. Next, we normalize these tensors using transforms normalize, setting both the mean and standard deviation to 0.5. This normalization helps improve model performance and stability during training by standardizing the input data. Following this, we define our training and testing datasets using datasets, MNIST, where we specify the root directory for data storage, indicate whether it is the training set or the test set, and set the download parameter to true to automatically download the dataset if it's not already present. Afterward, we utilize data loader to create iterable loaders for both datasets. The batch size parameter is set to 64, allowing the model to process 64 samples at a time, while the shuffle parameter ensures that the training data is randomized each epoch, promoting better learning. Next, we will visualize a batch of the data we just loaded to gain insights into our handwritten digit images. Now let's implement our neural network by defining a simple feedforward model using PyTorch. We begin by creating a class called SimpleNN that inherits from NN module, which is essential for all neural network modules in PyTorch. Inside the constructor, we initialize 3 fully connected layers, where the first layer transforms the 28x28 input images into a hidden layer with 128 neurons, followed by another layer reducing it to 64. The final layer outputs 10 values corresponding to the classes of the MNIST digits. Next, we define the forward method, which outlines the flow of input through these layers, starting by flattening the input images. Then we apply the RayLU activation function to the first 2 layers, adding nonlinearity to the model before reaching the output layer. Finally, we employ the log_softmax activation, making it suitable for multi-class classification tasks. After we define our model, it's important to specify a loss function and an optimizer. Here, we use negative log likelihood loss, NLL loss, suitable for training with log_softmax outputs, and the atom optimizer, known for its efficiency in handling weight updates. Next, we will write the code for training our model. The training process consists of looping through a set number of epochs, where during each epoch we iterate through batches of training data. Inside this loop, we first reset the gradients for the optimizer to ensure that we don't accumulate gradients from previous batches. Then we perform a forward pass through the model to obtain predictions for the input images. The next step involves calculating the loss, which measures how well the model's predictions align with the actual labels. Following this, we execute the backward pass to compute gradients with respect to the loss. Finally, we update the model's weights using the optimizer. After processing all batches in an epoch, we print out the loss to monitor the model's learning progress. A decreasing loss value over epochs indicates that our model is improving its performance on the training data. Now let's see how we can evaluate the model's performance after training. We will implement a function to calculate the accuracy of our model on the test set. By setting the model to evaluation mode, we ensure that no gradients are tracked, thus optimizing memory usage. While iterating through the test dataset, we will generate predictions and compare them with the true labels to count the number of correct predictions. Finally, we compute the overall accuracy percentage and display it, providing insight into how well our model generalizes to unseen data. Now let's take a look at how we can visualize the training process by tracking the loss over epochs. We start by initializing an empty list called train losses to store the average loss for each epoch. As we enter the training loop, we iterate through each epoch, and for every batch of images and labels retrieved from the train loader, we carry out the standard training steps, zeroing the gradients, passing the images through the model, calculating the loss, and performing backpropagation. After processing all batches in the epoch, we compute the average epoch loss by dividing the total loss by the number of batches. This average loss is then appended to our train losses list for future visualization. After all epochs have been processed, we use matplotlib to plot the recorded losses against the epoch numbers. This graphical representation allows us to observe how the model's loss decreases over time, providing valuable feedback on the training process. The desired outcome is a curve that steadily trends downward, indicating that the model is effectively learning from the training data. The figure titled Effective Training Sample Size on Model Accuracy directly compares training accuracy green line and validation accuracy orange line as the number of training samples increases across 4 points: 500, 2000, 4000, and 8000. Key patterns are clear. Both training and validation accuracies steadily increase with more data. Training accuracy rises from 0.6 at 500 samples to 0.92 at 8000 samples, while validation accuracy moves from 0.55 to 0.88 over the same range. The gap between training and validation accuracy is small throughout, about 0.05 at 500 samples and about 0.04 at 8000 samples, indicating the model generalizes reasonably well and does not exhibit severe overfitting as data grows. The largest improvement occurs between 500 and 2000 samples, a 0.15 jump in training accuracy and 0.15 in validation, after which gains continue but with diminishing returns. Improvements from 4,000 to 8,000 samples are smaller: 0.07 training, 0.08 validation. From these observations, we conclude that increasing training sample size yields consistent and meaningful accuracy improvements, with early samples delivering the most significant marginal benefit and larger datasets still improving generalization, albeit more gradually. This underscores the practical importance of collecting more labeled data to boost both training performance and validation generalization. Now let's implement a straightforward convolutional neural network (CNN) to process our MNIST dataset. We start by defining a class called CNN, which inherits from NN module. Within the constructor init, we establish our network's architecture beginning with 2 convolutional layers. The first layer, conv1, transforms the single-channel input into 32 feature maps using a 3x3 kernel while applying padding to maintain dimensions. The second layer, conv2, increases the feature maps to 64, again with similar properties. After the convolutional layers, we integrate 2 fully connected layers to handle the output. The first fully connected layer, FC1, takes the flattened output from the convolutions, which must be reshaped appropriately, and projects it to 128 neurons. Finally, our output layer, FC2, maps these 128 neurons to the 10 classes of digits we are trying to predict. In the forward method, we define the flow of our data through the network. The input passes through both convolutional layers with ReLU activations and undergoes max pooling to reduce dimensionality, allowing the network to learn important features efficiently. After flattening, it proceeds through the fully connected layers, with the final output representing a log softmax for multi-class classification. Now let's create an instance of our CNN model and print its structure to confirm everything is set up correctly. Now let's take a moment to discuss the significance of hyperparameter tuning. Hyperparameters include things like learning rate, batch size, number of layers, and the number of neurons in each layer. Fine-tuning these can dramatically influence your model's performance. In practice, one might use techniques such as grid search or more advanced optimization methods to find the best combination. For example, if your learning rate is too high, the model might never converge, while if it's too low, it could take an eternity to learn. It's crucial to experiment and monitor these parameters along your training journey. Now let's implement a dropout layer to help mitigate overfitting in our CNN. In the context of neural networks, overfitting occurs when a model learns the training data too well by capturing noise and specific patterns, which can degrade its performance on unseen data. To address this, we can utilize a dropout layer, which randomly disables a fraction of neurons during the training phase, encouraging the model to rely on multiple paths to make decisions rather than overfitting to particular neurons. In our code, we specify the dropout probability using the NN dropout class, where p equals 0.5 indicates that we will randomly set 50% of the neurons to 0 during training. This technique reduces the model's complexity and helps improve its generalization capabilities on the validation and test sets. By integrating this dropout layer right after a fully connected layer, we strategically introduce randomness that fosters a more robust learning process. This addition is critical as we aim to enhance our model's resilience against overfitting, while maintaining performance accuracy on unseen data. Next, we'll look at how to save and load our trained models, which is essential for preserving our work and enabling future use of the model. To save the model, we'll use torch save, along with the model's state dictionary, which contains all the learned weights and biases. We're saving this dictionary to a file named CNN model, PTH. This will allow us to keep the model's parameters and configurations safely stored for later access. Now that we've saved our model, we must understand how to reload it. To do this, we first need to reinstantiate the model class, which creates a fresh model object. Then we load the saved weights into this new model using load_state_dict. It's crucial to call CNN model eval afterward to set the model to evaluation mode, ensuring that it behaves correctly when making predictions. This approach streamlines the process of continuing training or deploying the model in real-world applications. By following these steps, you can effectively manage your models and make the most out of the progress you've achieved in your training efforts. To conclude, we've journeyed through the implementation of neural networks in PyTorch. We started by setting up our environment, loading our data, and building our first models. Next, we explored training, evaluating, and optimizing these models, including the use of convolutions for image data. You now have the foundational knowledge to set up your neural networks and make substantial contributions to the world of deep learning. As you delve deeper into PyTorch, you'll come to appreciate its flexibility and power. Keep experimenting, keep learning, and most importantly, enjoy the process, because in the end, it's about transforming ideas into reality with the hands of technology. Thank you for joining me today, and happy coding. To truly grasp the full power of neural networks, it's essential to understand how feedforward and backpropagation work together. These two processes play crucial roles in training a neural network, allowing it to learn from data and improve its predictions. In this exploration, we will dive deep into both concepts and how they interrelate, paving the way to optimize weight values in a neural network. Now let's take a look at how we can implement a simple feedforward neural network using Python. The feedforward network class serves as the foundation for our model, where we begin by initializing the weights that connect the input layer to the hidden layer and the hidden layer to the output layer. These weights are assigned random values, allowing the network to start its learning process from various starting points. In the feedforward method, we compute the output of the network by applying a series of transformations to the input data. First, we calculate the weighted sum of the inputs and pass it through a nonlinear activation function, the sigmoid function, to produce the outputs for the hidden layer. This step introduces the necessary nonlinearity to our model, enabling it to learn more complex patterns in the data. We then repeat a similar process to produce the final output of the network by taking the hidden layer's outputs, applying the weights connecting to the output layer, and again using the sigmoid function. This structure allows us to effectively propagate data through the network, setting the stage for the backpropagation process to optimize weights based on prediction errors. Now let's implement the mean squared error (MSE) loss function and a method to calculate this loss for our network. First, we define the mean squared error function, which takes predictions and target values as inputs. It computes the mean of the squares of the differences between these predictions and targets, providing a quantifiable measure of how well our model's predictions align with the actual values. Next, we create the calculate loss function, which integrates the feedforward process into the loss calculation. This function uses the feedforward method of the network, passing in the input data to obtain the predictions. It then calls the mean squared error function, using the predictions and the true target data to compute the loss value. This structure allows us to seamlessly assess the performance of our neural network after passing the input data through it. By combining these two functions, we set a foundation for the network's learning process, as they will feed directly into our backpropagation step, where we will adjust the weights based on the computed loss. Now let's implement the backpropagation method, a crucial step in the training process of our neural network. This function begins by performing a feedforward pass where it computes the network's predictions based on the input data. After obtaining the predictions, we evaluate the output layer's error by subtracting the target data from these predictions. This gives us insight into how far off our predictions are from the actual values. Next, we calculate the hidden layer's error by propagating the output layer error backward through the weights, using the derivative of the sigmoid function. This is where the chain rule from calculus comes into play, enabling us to determine how much to adjust the weights connected to the hidden layer. With both errors computed, we proceed to update the network's weights. Specifically, we modify the weights connecting the hidden layer to the output layer and those connecting the input layer to the hidden layer. The adjustments are made in the opposite direction of the errors and are scaled by a learning rate to control the size of the step taken towards minimizing the loss. This method of updating weights is fundamental to the learning process, allowing the network to gradually improve its predictions as it trains. Next, we will write the training function that encapsulates the training loop of our feedforward neural network, integrating both the feedforward and backpropagation processes. The train function takes in the network training data, target labels, the number of epochs, and the learning rate as parameters. Within this function, we iterate over the specified number of epochs, where each iteration begins by calculating the loss using our previously defined method. This provides us with a measure of how well the network performs against the training data. Within the same loop, we perform backpropagation to adjust the weights based on the calculated loss, thus refining the model. We print the epoch number and loss every 100 epochs to monitor the training progress and check whether our adjustments yield a decrease in loss over time. Finally, using the if_name=main block, we define the structure of our XOR problem, initializing the network with specified input, hidden, and output layer sizes. We then generate the training data, which consists of inputs and corresponding targets, and invoke the training function. This connection of the components comprehensively illustrates how the network learns to solve the XOR problem through iterations. The figure presents two epochwise diagnostic plots side by side for 20 training epochs. The left panel, training loss over epochs, shows blue circle markers connected by a line and reveals a clear, roughly exponential decay in loss from around 0.9 at epoch 1 down toward approximately 0.13 by epoch 20, with only small random fluctuations. This indicates consistent optimization of the training objective as epochs progress and weights are updated. The right panel, validation accuracy over epochs, uses red X markers to show validation accuracy oscillating around a baseline of about 0.8 with periodic peaks and troughs, roughly plus or minus 0.1, producing values mainly between 0.7 and 0.9 under the 0.1 axis limit. This pattern reflects a sinusoidal component plus noise, so accuracy improves on some epochs and dips on others rather than increasing monotonically. Comparing both plots, the steady fall in training loss alongside a non-monotonic validation accuracy implies that reducing training loss does not guarantee steady improvement in the validation metric. Validation performance shows variance in short-term peaks where generalization is better and troughs where it is worse. Because epoch ticks are shown explicitly, one can identify specific epochs where accuracy peaks coincide or fail to coincide with lower loss. These alignments, or lack thereof, suggest practical actions such as selecting the best model checkpoint based on validation metrics and monitoring validation fluctuations across epochs rather than relying on loss reduction alone. Now let's implement a function to evaluate the performance of our trained neural network model by calculating its accuracy on a test dataset. The accuracy function begins by using the Feedforward method to generate predictions from the test data. These predictions are then rounded to the nearest integer, converting the continuous output from the neural network into binary values, essentially classifying the outputs as either 0 or 1, which is suitable for binary classification tasks. Next, we compare these rounded predictions with the actual test labels to determine the number of correct predictions. This is done using the NP-sum function, which counts how many times the predicted outputs match the true labels. Finally, we return the proportion of correct predictions by dividing the number of correct results by the total number of test labels. This straightforward yet crucial step provides important insight into the model's ability to generalize to unseen data, allowing us to evaluate the effectiveness of the training process. After defining the accuracy function, we proceed to evaluate the model's performance using a predefined test dataset, essential for understanding how well our network has learned the underlying patterns from the training data. Ultimately, understanding how feedforward and backpropagation work together is essential for grasping the mechanics of neural networks. By feeding inputs through the network, we generate predictions which are evaluated against actual outputs. The discrepancies between these predictions and the actual data motivate weight adjustments through the backpropagation process. Mastering this cycle not only helps in training effective models, but also equips you with the intuition necessary for advancing in machine learning and deep learning. To summarize our journey today, we covered how the feedforward process calculates predictions, the essence of loss functions, and how backpropagation adjusts weights based upon those losses. These principles are the bedrock for developing and fine-tuning neural networks, especially as we delve into more complex architectures. In our next session, we will discuss advanced topics such as optimizers, regularization techniques, and how to handle overfitting for robust model development. This will empower us to build even more effective neural networks capable of tackling complex real-world problems. Stay tuned. Now that we have everything set up, let's implement the initial steps of our neural network project. First, we will ensure that we have the necessary packages installed for our project, which include PyTorch, TorchVision, NumPy, and Matplotlib. We can easily install these packages via pip. Once installed, we can verify our PyTorch installation by importing the library and printing its version number to make sure everything is working correctly. Next, we will load the famous iris dataset using the datasets module from Sklearn. This dataset contains features of various iris plants which we can use for classification tasks. After loading it, we separate the data into inputs denoted as X and their corresponding labels denoted as Y. Then we utilize train test split to split our dataset into training and testing subsets, ensuring that we can evaluate our model later on unseen data. To enhance our model's performance, we standardize the features using standard scalar, which normalizes the input data. Finally, we convert these standardized NumPy arrays into PyTorch tensors so that we can effectively work with them in our neural network. Now let's see how we can implement our neural network architecture using PyTorch. We define a custom class called IrisNet, which inherits from NN module. Inside the init method, we instantiate our network layers. The first densely connected layer, self FC1, takes 4 input features and passes them to 5 neurons in the hidden layer. Next, self FC2 connects the hidden layer to the output layer, which has 3 neurons corresponding to the 3 classes of the iris dataset. To handle multi-class classification effectively, we include a softmax activation function, which converts the output scores into probabilities. Moving to the forward method, we define how data flows through our network. The input X passes through the first layer, where we apply the RayLU activation function, introducing nonlinearity before moving on to the output layer. After obtaining the raw outputs, we apply the softmax function to derive probabilities for each class. After defining our model architecture, we can then instantiate the model. This step essentially creates a blueprint for our neural network, ready to be trained on the iris dataset. The figure displays training and validation accuracy over 10 epochs for 5 different learning rates: 0.01, 0.005, 0.001, 0.0005, 0.0001. Each learning rate is represented by a pair of curves: solid lines with circular markers for training accuracy and dashed lines with X markers for validation accuracy, and a red dashed horizontal line marks the target accuracy of 0.9. Key patterns are evident. All curves trend upward across epochs, showing that accuracy improves with training time. Higher learning rates, the largest listed, exhibit the steepest early increases in training accuracy, achieving high training values sooner, while the smallest learning rates show much more gradual improvement. The gap between training and validation curves varies with learning rate. Larger gaps appear for some higher rates, indicating faster learning on the training set than on validation, a symptom suggesting potential overfitting or instability, whereas lower rates tend to produce training and validation curves that track more closely, reflecting steadier but slower generalization. Observing the target line, a subset of the higher learning rates approach or cross the 0.9 threshold within the 10 epochs shown, while the smallest rates frequently remain below that target by the final epoch. From these patterns, we can conclude that there is a trade-off. Larger learning rates speed initial convergence but may widen the train-validation gap, whereas smaller rates favor stability and closer alignment between training and validation but require more epochs to reach the same accuracy. This visualization supports choosing a moderate learning rate or using a scheduler that starts larger and decays to balance convergence speed and generalization. Now let's implement the training loop to refine our model. We'll begin by setting the number of epochs to 1000, allowing the model ample opportunity to learn from the training data. In this loop, for each epoch, we first set the model to training mode using model train, which is crucial for layers that behave differently during training and evaluation, like dropout or batch normalization. Next, we clear any gradients that were calculated in the previous iteration by calling optimizer 0grad, ensuring we start fresh with each epoch. We then conduct a forward pass by feeding our training data through the model to get the predicted outputs. The calculated outputs are then used to compute the loss against the true labels using our loss function criterion. With the loss calculated, we perform a backward pass using loss backward, which computes the gradients needed for optimization. Subsequently, we update the model weights with optimizer step, applying all the changes. To monitor the training progress and ensure our model is learning effectively, we print the current loss every 100 epochs, allowing us to see how it decreases over time. This training loop encapsulates the core learning process for our neural network. Now let's see how we can evaluate the performance of our trained model on the testing dataset. First, we set the model to evaluation mode using model eval, which signals to the layers like dropout or batch normalization to behave appropriately during inference. This is crucial as it ensures that the model does not perform operations like dropout, which would randomly deactivate certain neurons during training. Next, we use torch_no_grad to disable gradient calculations, reducing memory consumption and speeding up the computation since we don't need gradients during evaluation. Within this context, we conduct a forward pass using our test data by calling model xTest tensor, which generates output predictions. To determine which classes our model predicts, we employ torch.max to retrieve the indices of the maximum values from the output tensor, representing the predicted class for each input. Finally, we compute the model's accuracy by comparing these predicted classes to the true labels from our testing set, calculating the mean of correct predictions. This process culminates with printing the model's accuracy, providing a clear indication of how well our neural network generalizes to unseen data. Now let's implement an enhanced version of our neural network by adding complexity to our architecture. Here, we define a new class called IrisNet Enhanced. This class inherits from NN module, allowing us to create a custom neural network model in PyTorch. In the init method, we construct 3 layers. The first hidden layer contains 8 neurons, the second hidden layer has 4 neurons, and finally, there's the output layer, which is composed of 3 neurons to align with our classification task for the iris dataset. We use the RayLU activation function for both hidden layers, which helps introduce nonlinearity into the network, allowing it to learn more complex patterns. Subsequently, we apply a softmax activation function to the output layer to convert the raw outputs into probabilities that correspond to each of the 3 iris species. Finally, we instantiate the enhanced model. This structure enables us to experiment with different configurations of neurons and layers effectively, striking a balance between training time and model accuracy. After defining this enhanced model, we will proceed with the same training steps as we did previously, which may yield improved performance on the testing dataset. Now let's implement a learning rate scheduler to enhance our training process. This is crucial because the learning rate can significantly impact how effectively our model converges during training. In our example, we utilize PyTorch's StepLR scheduler, which systematically decreases the learning rate every specified number of epochs, allowing the model to adjust more finely as it approaches optimal weights. Next, we set the step size to 200 epochs and the gamma to 0.1, meaning the learning rate will be multiplied by 0.1 every 200 epochs. This helps ensure that as the training progresses, the learning rate diminishes, allowing for more stable convergence and potentially better overall performance. In the training loop, after calculating the loss and performing backpropagation, we call scheduler step to apply the learning rate change. This adjustment ensures that our model benefits from a higher learning rate early on for faster convergence while gradually decreasing to refine its weights as training continues. Additionally, by printing the current learning rate every 100 epochs, we can monitor how it changes over time, giving us insights into our training dynamics. This strategy can be particularly effective in preventing issues like overshooting the minimum loss during optimization. And there you have it. You've just gone from the very basics of understanding neural networks to implementing and training a neural network model in PyTorch. We've also covered hyperparameter tuning considerations to further enhance your model. Building neural networks using PyTorch is both powerful and fun. The ease of making modifications and running experiments allows for great flexibility in developing machine learning solutions. As you continue your journey, consider exploring deeper architectures, additional optimization techniques, and more complex datasets to push your skills further. Stay curious, keep experimenting, and enjoy the thrilling world of deep learning. Generative artificial intelligence is revolutionizing how we interact with technology, bringing forth an era of creativity and innovation in various fields. In this lesson, we will dive into the fascinating world of generative AI applications, exploring the capabilities unleashed by neural networks and how they empower us to create, analyze, and understand complex data like never before. So far, we've learned about implementing neural networks using PyTorch, focusing on fundamental concepts like feedforward processes, backpropagation, and the importance of learning rates. We prepared our data, defined a simple feedforward architecture for the iris dataset, and explored the training process with loss functions and optimizers. We also discussed enhancing our model through hyperparameter tuning and implementing a learning rate scheduler to optimize performance. Finally, we emphasized the value of experimentation and modifications in deep learning to refine our models. Now, we will talk about the exciting applications of generative AI, including image, text, and even music generation using neural networks. Now let's implement the generator and discriminator models for our GAN using PyTorch. The generator class takes 2 parameters, input size, which determines the dimension of the random noise input, and output size, which defines the dimension of the generated images. Inside the generator, we build a sequential model comprising fully connected linear layers followed by RayLU activation functions. This architecture enables the model to learn complex patterns from the noise input and ultimately produce an output image that adheres to the desired output size. Next, we will construct the discriminator class responsible for distinguishing real images from the fake ones generated by the generator. The discriminator also utilizes a sequential model of linear layers, but this time it ends with a sigmoid activation function to produce a probability score ranging from 0 to 1, indicating the likelihood that the input image is real. By training these two models simultaneously in a competitive setup, we can enhance their performance over time. Through this dual training approach, the generator learns to create ever more convincing images, while the discriminator becomes increasingly adept at identifying fakes, culminating in a well-tuned GAN system. The displayed figure, titled Impact of Generative AI Applications, is a bar chart that quantifies perceived impact levels on a 1-10 scale across 5 application categories: image generation 8, text generation 7, music generation 6, data augmentation 9, and model optimization 5. Key patterns are immediately clear. Data augmentation registers the highest impact level at 9, indicating it as the most influential area among those shown. Image generation follows closely at 8, reflecting strong practical and creative influence. Text and music generation occupy the mid-range with 7 and 6 respectively, showing solid but comparatively lower impact. Model optimization is the lowest at 5, suggesting this category contributes less directly to perceived application impact in this snapshot. A dashed trendline fitted across the category indices reveals a mild downward slope from left to right, but with a pronounced local peak at data augmentation, the 4th category, signaling that while there is slight overall decline across the ordered categories, the variability is meaningful and not monotonic. The vertical axis scale and horizontal grid lines confirm the range of values spans a limited band 5-9, highlighting moderate dispersion rather than extreme outliers. From these patterns, we can conclude prioritization insights. Investments and experiments targeting data augmentation and image generation are likely to yield higher immediate impact, while efforts in model optimization may require framing around longer-term infrastructure or efficiency gains rather than direct application impact. The color-differentiated bars make category comparisons straightforward and support the conclusion that generative AI's strongest short-term application effects, per this figure, are on augmenting data and producing images. Next, we will implement the training routine for our GAN model. In this function, we start by defining our loss function, BCE loss, which will help evaluate the performance of our discriminator and generator based on their predictions. We then set up 2 optimizers, one for the generator and one for the discriminator, using the Atom optimization algorithm tailored for our models. During each epoch, we take batches of real data from our data loader and assign labels to these and the fake data we will generate. Real images are labeled with 1s, while the fake ones are labeled with 0s. First, we train the discriminator by feeding it both real and generated images, calculating the loss for each and updating its parameters accordingly. After training the discriminator, we shift our focus to the generator. Here, we aim to improve its ability to fool the discriminator. By computing the generator's loss from how well it can convince the discriminator that its outputs are real, we update the generator's parameters using the same optimization strategy. This iterative process allows both models to learn from each other, enhancing their performance over time. Now let's implement a simple LSTM model using PyTorch for text generation tasks. We begin by defining a class, LSTM model, which inherits from NN module. In the constructor, we initialize several layers crucial for our model: an embedding layer that converts word indices into dense vector representations, an LSTM layer that processes these embeddings considering their sequential nature, and a fully connected layer that maps the LSTM's output to the vocabulary size for predicting the next word. The forward method outlines how data flows through the model. First, the input sequence is passed through the embedding layer, converting each word index into a dense vector. This output is then fed into the LSTM, which maintains context across the sequence. We are only interested in the output from the last time step as it carries the most relevant information for our prediction task. Hence, we index it with x-1. Finally, this output is processed by the fully connected layer, which generates scores for every word in the vocabulary, enabling the model to predict the next word based on the context learned from the sequence. Next, we will implement a training loop for our LSTM model that is designed for text generation. In this function, we use a structured approach to help our model learn effectively from the training data. For each epoch, which represents one complete pass through the dataset, the loop iterates over the batches of sequences and their corresponding target words. We start by zeroing the gradients of the optimizer. This step is crucial because, during each backward pass, gradients accumulate by default, so we need to clear them before calculating the new gradients for the current batch. The model then makes predictions using the input sequences by passing them through the LSTM. Once we have the outputs, we calculate the loss by comparing these predictions to the target words. This loss informs us how well the model is performing, allowing us to fine-tune its weight adjustments. We then call the backward method on the loss, which computes the gradients needed for backpropagation, and finally the optimizer updates the model's weights based on these gradients. By repeating this process, our LSTM will gradually improve its ability to predict the next word in sequences, ultimately enabling the generation of coherent and contextually relevant text. Now let's implement a function to generate music using our trained model. We begin by defining a function named GenerateMusic, which takes as inputs a model, a starting sequence of musical notes, and the number of additional notes we want to generate. The function initializes a list, generated sequence, with the provided starting sequence. As we loop through the specified number of notes to generate, we will prepare the input sequence by converting it into a tensor. This tensor is reshaped into a batch format suitable for the model. The model then predicts the next note in the sequence, which we retrieve by finding the index of the maximum output probability using argmax. After obtaining the predicted note, we append it to our generated sequence to keep track of the complete melody. Additionally, we create a Music21 stream object to encapsulate the generated notes, enabling us to prepare them for playback or to export them as a MIDI file. Finally, the function returns the fully generated sequence of notes, showcasing how we can seamlessly create music through AI by leveraging the learned patterns from training data. This implementation not only demonstrates generative capabilities, but also highlights the artistic potential of AI in music creation. As we look to the future, the implications of generative AI applications are boundless, transforming industries from entertainment to education and beyond. However, with these powers come responsibilities. We must address ethical considerations concerning AI-generated content, ensuring that it respects intellectual property rights and societal norms. The convergence of technology and ethics leads to a profound discussion on how we harness AI's potential while minimizing risks. As creators and technologists, it is prudent to engage in open dialogues, set standards, and create frameworks that guide us in the ethical deployment of generative models. In conclusion, we've traversed the dynamic landscape of generative AI applications, examining how neural networks facilitate groundbreaking advancements in image, text, and music generation. These capabilities not only enhance our creative processes but also challenge us to think critically about the implications of technology. So keep experimenting, stay curious, and who knows, you could be the next innovator in this exciting field. In today's lesson, we're diving into an essential aspect of neural networks optimization techniques. Specifically, we'll focus on gradient descent and how it helps us update weights to minimize errors during training. This topic lays the foundation for effective learning in artificial intelligence, enabling our models to reach their full potential. So far, we learned about the transformative potential of generative artificial intelligence, particularly in image, text, and music generation. We explored the fundamentals of neural networks through hands-on implementation using PyTorch, including GANs for image generation and LSTMs for text generation. We also highlighted the importance of experimentation, hyperparameter tuning, and ethical considerations in the deployment of generative models. Next, we will delve deeper into the real-world applications and challenges associated with these advanced technologies. Now let's see how we can implement the mean-squared error function, which is a common loss function used in regression tasks. The function takes two arguments, ypred, which represents the predicted values from our neural network, and ytrue, the actual target values. Inside the function, we utilize PyTorch's built-in operations to compute the mean-squared error. Specifically, we first calculate the difference between the predicted and true values, square this difference to ensure all errors are non-negative, and then compute the mean of these squared differences. This operation effectively summarizes how far off our predictions are from the actual values, providing a single metric that we can minimize during training. By using the mean-squared error as our loss function, we set the foundation to measure model performance objectively and guide our optimization process through gradient descent. This step is crucial as it directly influences how the model learns and adjusts its parameters throughout the training process. Now let's take a look at how we can implement a simple neural network using PyTorch, focusing on the essentials of setting up the model and the training loop with gradient descent. We begin by defining a class called SimpleNN, which inherits from NN module, making it compliant with PyTorch's model structure. Within this class, we initialize a linear layer that takes one input feature and produces one output feature. Next, we create an instance of our neural network model and select the mean squared error as our loss function, which is common for regression tasks. We also define the stochastic gradient descent optimizer to update the model's weights. After this, we initialize sample data in the form of input and target tensors. Now let's implement the training loop, which runs for 100 epochs. In each iteration, we first set the gradients to 0 to prevent accumulation from previous iterations. Then, we perform a forward pass by passing our input data through the model to obtain predictions. The loss is calculated by comparing these predictions to the actual target values. Subsequently, we invoke the backward method to compute the gradients, followed by optimizer step to adjust the model's weights based on these gradients. This process illustrates the vital elements of training a neural network through gradient descent. Now let's take a look at how we implement stochastic gradient descent (SGD) in our training loop. The loop iterates for a predefined number of epochs, allowing our model to progressively learn from the data. Within each epoch, we go through each training sample individually, which is one of the key characteristics of SGD. As we loop through the data, we first reset the gradients of our model's parameters to 0 using the optimizer S0grad method. This is crucial because in PyTorch, gradients accumulate by default. Resetting them ensures that each iteration computes the gradient for the current sample without interference from previous computations. Next, we extract each training sample xi and the corresponding target yi, reshaping them to maintain the expected dimensions for model input. We then perform a forward pass through the model to obtain predictions. The loss is computed using our defined criterion, quantifying how well the model's predictions align with the true values. After determining the loss, we call the backward method to calculate the gradients based on the loss, and finally, we invoke optimizer step to update the model's weights, moving them in the direction that reduces the loss. This process emphasizes the iterative and noisy nature of SGD, which can encourage better convergence in training. Now let's implement the momentum optimization technique to enhance our gradient descent. We begin by creating a momentum optimizer class that encapsulates the mechanics of this method. Inside the init method, we initialize the parameters of the model, set the learning rate and momentum coefficient, and prepare a list to hold velocity values for each parameter. This velocity will track the exponential decay of past gradients, allowing us to effectively build momentum as we update our weights. Next, we define the step method, which is the core of our optimizer. During each call to this method, we loop through each parameter of the model. For each parameter, we update its corresponding velocity by combining the previous velocity scaled by the momentum coefficient with the current gradient scaled by the learning rate. This step captures both the current motion and past trends. Finally, we subtract the updated velocity from the parameter data to adjust the model weights. This approach not only accelerates learning in the correct direction but also mitigates oscillations, leading to more stable convergence. By incorporating momentum, we're effectively boosting our optimizer's performance in navigating the error landscape. Next, we will write the following code to implement a step learning rate scheduler using PyTorch, which allows us to adjust the learning rate dynamically during training. In this example, we begin by importing the StepLR class from the Torch Optim LR scheduler module, which provides functionality for reducing the learning rate at specified intervals. We initialize the optimizer using stochastic gradient descent (SGD) and set the initial learning rate to 0.1. The scheduler is then created with a specified step size of 30 epochs and a gamma value of 0.1, which means the learning rate will be reduced to 10% of its current value every 30 epochs. After defining our optimizer and scheduler, we enter the training loop that runs for 100 epochs. Within this loop, the optimizer is updated to adjust the model's weights based on the computed gradients. Importantly, we also call scheduler step after each optimizer update, which applies the scheduled learning rate adjustment. This combination allows us to start with a larger learning rate for swift navigation through the loss landscape, gradually refining our learning as training progresses around the minima. Now let's see how we can utilize the Atom optimizer in our PyTorch implementation. The first line initiates the Atom optimizer and sets the learning rate to 0.001, which determines how much we adjust the weights during each iteration. This optimizer is particularly effective as it automatically adapts the learning rates for each parameter based on the first and second moments of the gradients, promoting more stable updates. Next, we enter the training loop that runs for a total of 100 epochs. At the beginning of each epoch, the optimizer's gradients are reset to 0 to prevent accumulation from previous iterations. After that, we perform a forward pass through the model to obtain predictions for the input data. The loss is then calculated using our defined criterion, which assesses how well our model's predictions match the true labels. Once we have the loss computed, we call the backward method to perform backpropagation, allowing the optimization algorithm to compute the gradients with respect to the model parameters. Finally, we invoke optimizer's step to update the model's weights based on the gradients. This approach simplifies weight adjustments and helps speed up convergence, making it a popular choice among practitioners in deep learning. The figure titled Impact of Optimization Techniques in Neural Networks displays a bar chart that quantifies the relative impact level on a 1-10 scale for 5 methods: gradient descent 8, stochastic gradient descent 7, momentum 9, learning rate scheduling 8, and atom 10. The most salient pattern is that atom reaches the highest impact value at 10, indicating it is represented as the most influential technique in this comparison. Momentum follows closely with a value of 9, showing it as a strong contributor to improved optimization behavior. Gradient descent and learning rate scheduling are tied at 8, which positions them as solid mid to high impact strategies. Their equal heights suggest they offer comparable benefit in practice. Stochastic gradient descent sits slightly lower at 7, indicating a modestly smaller measured impact relative to the other techniques shown. From these displayed values, one can conclude that adaptive and momentum-based methods, atom and momentum, are shown as having the greatest impact, while basic gradient-based approaches and scheduling still provide substantial benefits but slightly less so in this ranking. The chart therefore emphasizes prioritizing atom or momentum strategies when seeking the highest single-method impact, while acknowledging that gradient descent and learning rate schedules remain valuable components in an optimizer toolkit. Now let's implement the following procedure to monitor our model's validation loss during training and apply early stopping to prevent overfitting. We begin by initializing an empty list to store the validation losses for each epoch. As we enter the training loop, which we can set for a defined number of epochs, in this case 100, we will conduct the necessary training operations. Next, it's vital to assess the model's performance on the validation dataset after each epoch. To do this, we use the Torch NoGrad context manager, which disables gradient computation, allowing us to evaluate the model's performance without updating weights. We then make predictions on the validation inputs and compute the validation loss using our predefined loss criterion in conjunction with the actual validation outputs. The loss value is appended to our list of validation losses after converting it to a scalar. Finally, we check if the current validation loss is lower than the minimum observed loss. If it is, this indicates that the model is performing better than before, and we should proceed to save the model. This simple yet effective strategy helps us manage model performance while combating the risk of overfitting, ensuring we make the most of our training process. To sum things up, optimization techniques are the backbone of successful neural network training, enabling our models to learn from data efficiently. Understanding and effectively implementing gradient descent along with its various enhancements can significantly impact model performance. We covered basic gradient descent, stochastic gradient descent, momentum, learning rate schedules, adaptive learning rates with atom, and approaches to prevent overfitting. As you proceed on your machine learning journey, remember that the fundamentals of optimization aren't just about coding algorithms. They're about understanding how adjustments affect your network's learning and performance. Embrace the process and keep experimenting. Optimization is as much an art as it is a science. Add a sprinkle of creativity, and you'll impress even the most seasoned data scientists. Neural networks are powerful tools in machine learning, but understanding how to evaluate their performance is crucial for harnessing their full potential. Today, we're going to dive into the process of evaluating neural network performance, focusing specifically on how feedforward propagation and backpropagation work together to minimize loss during training. So far, we covered optimization techniques in neural networks, particularly gradient descent and its importance in weight updates to reduce errors. We even touched on various enhancements like stochastic gradient descent and adaptive learning rates using the atom optimizer. Now we will investigate how to evaluate the performance of these networks, ensuring that our models not only learn accurately but also generalize well to unseen data. Now let's see how we can implement the feedforward propagation in our neural network, focusing on the structure and functionality of the code. We start by importing the NumPy library, which is essential for handling arrays and performing mathematical operations efficiently. The ReLU function is defined next. It serves as our activation function, which transforms the input values, ensuring that only positive signals pass through to the next layer, thus introducing nonlinearity into our model. Next, we define the feedforward function, which takes the input data x and a list of weights for each layer as parameters. Inside this function, we first compute the output for the first hidden layer by performing a dot product between the input and the first layer's weights, followed by applying the ReLU activation. This output is then fed into the second hidden layer through another dot product and an activation function. Finally, the last layer produces the final output through a simple dot product, yielding predictions that represent our model's response to the input data. Following the feedforward function, we create a sample input array X representing binary combinations, and we initialize random weights for the 3 layers of the network. When we call the feedforward function with this input and the random weights, it computes and prints the predictions, allowing us to visualize the network's output based on the current weights. Now let's see how we can implement the mean squared error (MSE) loss function to evaluate our neural network's predictions. The first part of our code defines the mean squared error function, which takes 2 inputs, the true labels yTrue and the predicted values yPred. The function calculates the average of the squared differences between these 2 arrays, providing a numerical representation of how far off the predictions are from the actual values. This computation is crucial as it directly informs us of the model's performance. Next, we define our true labels as a NumPy array, representing a simple binary classification scenario. In this example, we have a set of 4 true labels for a binary classification problem involving a neural network that predicts outcomes based on input data. We then call the mean squared error function using our true labels and the output from our previously defined feedforward function. Finally, we print the calculated loss, which allows us to assess how well our model is doing in terms of prediction accuracy. A lower MSE value indicates a better fit of the model to the actual classes, guiding us on adjustments needed during training. Next, we will implement the backpropagation function, which is essential for training our neural network by updating the weights based on the computed gradients. In this function, we begin by calculating the output error, which is the difference between the predicted values and the true labels. This provides a measure of how far off our predictions are. Then we compute the gradient for the output layer, which we treat as linear here since we have a straightforward output prediction. The weight updates for this layer are derived from the error signal and adjusted using the learning rate. Following this, we proceed to calculate the error for the hidden layers using the derivative of the ReLU activation function, enabling us to backpropagate the gradients correctly. Each weight update for the hidden layers follows a similar logic. We calculate the gradient based on the respective errors and apply the learning rate to adjust the weights using the dot product of the input data and the errors. By chaining these operations, we allow the network to learn and improve the accuracy of its predictions with each iteration. Finally, we call this backpropagation function to update the weights in our neural network systematically. Now let's implement the early stopping mechanism to enhance our training process. Early stopping helps us monitor validation loss during training and halts the process when the model begins to overfit, which occurs when validation performance worsens as training continues. The function early stopping takes 3 parameters: training losses, validation losses, and patience. It checks if the length of validation losses exceeds the specified patience level. If so, it assesses whether the most recent validation loss is greater than the minimum validation loss recorded in the previous epochs, signaling potential overfitting. If this condition is met, the function prints a message indicating that early stopping is activated and returns true. Next, we set up placeholders to hold the losses incurred during training for both training and validation datasets. As we simulate the training loop for 100 epochs, we compute the output from our neural network with feedforward propagation, then calculate the training loss using the mean squared error function. The validation loss is also computed, introducing slight random variations to simulate real-world scenarios. After performing backpropagation to update the weights based on the computed gradients, we call the early stopping function to check if training should continue, preventing overfitting and maintaining model generalization. The plotted figure displays training and validation loss across 100 epochs, with the x-axis labeled epochs, ticks every 10 epochs, and the y-axis labeled loss range shown from 0 to 1. The blue curve represents training loss and the orange curve represents validation loss as identified in the legend. Key patterns are both curves exhibit a steep decline during the initial epochs, indicating rapid learning early in training. After this initial phase, they both transition to a slower decrease and eventually approach a low-loss plateau showing convergence of the model. The training loss curve is consistently smoother and generally lower than the validation loss curve. creating a visible gap that indicates the training set is fit more closely than the validation set. The validation loss shows larger short-term fluctuations, higher variance around its downward trend, and there are epochs where the validation loss temporarily increases while training loss continues to fall. These upward deviations in validation loss are the precise signals used to trigger early stopping, because they point to the model beginning to overfit the training data. From this plot, you can conclude when the model has reached its best generalization. Choose the epoch at which the validation loss attains its minimum before sustained rises. Monitor the training validation gap to assess generalization, and consider applying regularization or adjusting training duration if the validation curve remains noisy or diverges from the training curve. In this code, we run through 100 epochs of training, updating our loss values in arrays. The early stopping function checks if validation loss has started to rise after a specified number of epochs patience, and if it has, we stop training to save our model from overfitting. To conclude, evaluating neural network performance primarily revolves around calculating loss and adjusting weights accordingly through feedforward propagation and backpropagation. In this lesson, we learned how to set up both forward and backward passes, calculate mean squared error, and implement early stopping to prevent overfitting. We've covered the basics of performance evaluation, weight training, and ensuring our models generalize well. As we advance in our course, we'll explore more complex neural network architectures and additional techniques for evaluation and optimization, including performance metrics like accuracy, precision, recall, and F1 score, which are essential for model evaluation. Now go ahead and apply these concepts to your neural networks. Evaluate their performance, monitor loss, and remember that improvement is a continuous journey in the realm of machine learning. Until next time. Training a neural network effectively hinges on optimizing its weights through a cycle of forward propagation and backpropagation. In this session, we'll explore these core concepts in detail, equipping you with the knowledge needed to fine-tune your network's architecture for optimal performance. So far, we learned about the performance evaluation of neural networks, emphasizing the roles of feedforward propagation and backpropagation in minimizing loss. We discussed how to calculate mean squared error and implement early stopping to avoid overfitting, ensuring models generalize well to unseen data. Additionally, we explored optimization techniques and the significance of monitoring validation loss during training. Now, we will talk about the process of optimizing neural network weights in depth. When we talk about optimizing weights, we fundamentally refer to finding the best set of weights that minimize the loss function, ensuring our model performs effectively on predictions. To begin with, let's break down the two critical components of this process, forward propagation and backpropagation. We can think of forward propagation as the way we pass inputs through a network to generate outputs, while backpropagation is the feedback mechanism that enables the network to learn from its mistakes. Now let's take a look at the implementation of forward propagation in our neural network. We begin by defining the RayLU activation function, which introduces nonlinearity into our model by returning the maximum of 0 in the input value. This is crucial since, without nonlinearity, our network would behave like a linear model. Following that, we have the feedforward function, which takes in the input matrix and the weights for each layer. Inside this function, we compute the activation for each layer by taking the dot product of the inputs with the corresponding weights and then applying the RayLU function. The output of the first layer feeds into the second, and finally, we calculate the final output by performing another dot product for the output layer. To illustrate how this works, we generate a simple input array representing samples and features, alongside random weights for our three-layer architecture. After executing the feedforward function with these inputs, we print the resulting output, showcasing how the model processes the input data through its layers to produce predictions. This foundational element of forward propagation is essential for understanding how neural networks make predictions. Now let's implement the mean squared error (MSE) function, which is instrumental in evaluating the performance of our neural network. This function computes the average of the squared differences between the predicted outputs and the actual values, providing a quantitative measure of how well our model is performing. A lower MSE value indicates a better fit. Next, we define our function, mean squared error, which takes two inputs, ytrue and ypred. Inside the function, we calculate the squared differences by subtracting the predicted values from the actual values and squaring the result. We then take the mean of these squared differences to obtain the MSE. Once the function is defined, we create sample actual labels stored in ytrue, representing the ground truth for our predictions. Finally, we call the mean squared error function, passing our true labels and the predicted output obtained from the previous feedforward step. The computed MSE is then printed, showing its value to help us evaluate the model's performance. This step is vital as it informs us how well our model is adjusting its weights during training based on the feedback from this loss value. Now let's implement the backpropagation algorithm, a pivotal step in optimizing our neural network's weights. In this function, we start by calculating the output error, which represents the difference between the predicted values and the actual labels. This error is essential as it provides the basis for all subsequent weight adjustments. Next, we compute the gradient for the output layer, which gives us the direction and magnitude by which we should modify the weights to reduce this error. After calculating the output gradient, we proceed to update the weights of the output layer using the learning rate, a hyperparameter that controls the adjustment size. Moving backward through the network, we encounter the second hidden layer, where we derive its error using the weights from the output layer. This error is adjusted with respect to the ReLU activation function's derivative, ensuring proper gradient flow. We then update the weights of the second hidden layer similarly. Finally, we repeat this process for the first hidden layer, obtaining its error and adjusting its weights accordingly. This systematic approach allows the network to learn from its mistakes, fine-tuning its parameters to minimize the overall loss function. Each call to this function enhances our model's ability to generalize, paving the way for improved predictions. Now let's implement the process of tracking our model's training and validation loss over multiple epochs. We first import the matplotlib pyplot library to facilitate plotting. We initialize two empty lists, training losses and validation losses, to store the loss values for each epoch. Inside a loop that runs for 100 epochs, we begin by performing forward propagation with our input data, generating predictions from the neural network. We then calculate the training loss using the mean squared error function, appending this value to the training losses list. To mimic a real-world scenario, we also simulate a validation loss by adding some random variation to the training loss and store these values in the validation losses list. Following this, we call the backpropagation function to adjust the weights based on the output and true values. After completing the epoch loop, we will plot both the training and validation losses against the epoch count using matplotlib. This visualization will help us understand how well our model is learning over time by observing trends in the loss values. A declining loss indicates improvements in our neural network's performance. The displayed figure, titled Comparison of Training and Validation Loss Across Different Learning Rates, shows 6 curves grouped into 3 pairs, each pair corresponding to a single learning rate. Blue cyan for LR equals 0, 0, 1, orange coral for LR equals 0, 0, 0, 1, and green/light green for LR equals 0, 0, 0, 0, 1. The x-axis is epochs 0, 100, and the y-axis is loss 0, 1, with a grid and legend that make comparisons straightforward. Key patterns are evident. The LR equals 0, 0, 1 pair exhibits the fastest decline in loss during the early epochs, reaching low loss values much sooner than the other rates, but with visibly larger short-term fluctuations between the training and validation curves. The LR equals 0, 0, 0, 1 pair shows a steadier, smoother decrease in loss, achieving a balance between convergence speed and stability. The LR equals 0, 0, 0, 0, 1 pair declines most slowly and remains at higher loss values throughout the run, indicating much slower learning. Across all 3 rates, the validation curves generally mirror their corresponding training curves, but are slightly noisier and occasionally lie above the training curves, signaling the typical small generalization gap between training and validation performance. From this visualization, we can conclude that higher learning rates accelerate early convergence but can introduce more variability, while very small learning rates converge slowly. The middle learning rate here provides a compromise between speed and stability, illustrating the trade-offs to consider when selecting a learning rate and the importance of monitoring validation loss to choose the most appropriate setting. Now let's implement early stopping to enhance our model's ability to generalize. The function early stopping checks whether validation loss has improved over a specified number of epochs, referred to as patience. If the validation loss does not show improvement within this patience threshold, the function signals that early stopping should be activated, indicating that our model may be at risk of overfitting. In the training loop, we initiate training for up to 100 epochs. During each epoch, we first perform a feedforward step to compute the output. Next, we calculate the training loss using the mean squared error, followed by appending this loss to our training losses list. The validation loss is simulated to add some variability, and it is added to the validation losses list. After updating the weights through backpropagation, we call the early stopping function, passing in our training and validation loss histories alongside the defined patience. If early stopping is triggered, the loop breaks, preventing further unnecessary training and preserving the model's ability to generalize effectively. This implementation serves as a safeguard that carefully balances training and validation metrics for optimal performance. Now let's implement a snippet for the Atom Optimizer, which is renowned for its efficiency in training neural networks. The function begins by accepting weights, gradients, moment estimates m and v, a time step t, and hyperparameters for the learning rate, beta values, and an epsilon to prevent division by 0. As we iterate through each weight, we start by updating the moment m and velocity v estimates using exponential decay defined by beta 1 and beta 2. This helps accumulate gradients and provides momentum in the updates. After calculating m and v, we perform bias correction to obtain m hat and v hat, which counteract the initial bias towards 0. Finally, we update the weights based on the corrected moment and velocity, scaled by the learning rate. This formulation allows Atom to adjust the learning rate adaptively for each weight, enabling quicker convergence and providing stability to the training process. With this implementation, you can seamlessly integrate the Atom Optimizer into your training loop, enhancing the model's performance across various architectures. In conclusion, optimizing weights in a neural network is a meticulous process that involves understanding forward propagation and backpropagation, loss function computation, and the updates of weights based on gradients. We've covered how to implement these concepts in Python, ensuring that you have both the theoretical foundation and practical skills to handle weight optimization efficiently. As we refine our neural network skills, remember that the journey doesn't end here. Continually experiment with architectures, learning rates, regularization techniques, and performance metrics to enhance your models. Let's keep pushing the boundaries. Happy coding! Loss functions are critical components in the training of neural networks, serving as the guiding metrics that help to fine-tune model predictions. By optimizing these loss values, we can improve the performance of our models in tasks ranging from classification to regression. Today, we will delve deep into what loss functions are, why they matter, and how we can effectively implement them within our neural networks. Now let's implement the mean squared error (MSE) function in Python, which is a crucial loss function for regression tasks. In the code, we begin by importing the NumPy library, which is essential for efficient numerical computations. The mean squared error function takes two parameters, ytrue and ypred, representing the actual values and the predicted values respectively. Within the function, we compute the squared differences between these two arrays, which highlights the errors and predictions. By squaring the differences, we ensure that negative errors do not offset positive ones, and any larger error has a disproportionately greater impact on the overall loss. After calculating the squared differences, we use NumPy's mean function to compute the average of these squared errors, resulting in the MSE. This single value quantifies the model's performance. Smaller values indicate better model accuracy. To illustrate its application, we provide an example where we define two arrays, ytrue and ypred, containing known actual values and model predictions respectively. We then call the mean squared error function with these arrays and print the resulting MSE. This output allows us to assess how well our model is performing, guiding further optimization in our training process. Now let's implement binary cross-entropy in Python, which is particularly useful for binary classification tasks. The function begins by defining a very small epsilon value to prevent computational errors that can arise from taking the logarithm of 0. This ensures stability in our calculations as we work with predicted probabilities. Next, we apply the clipping operation to the predicted values ypred, constraining them within a range just above 0 and just below 1. This step prevents any values from reaching the extremes that could lead to undefined logarithm calculations. The core of the function calculates the binary cross-entropy loss using the standard formula. Here, we multiply the true labels by the logarithm of the predicted values, while the complement of the true labels is multiplied by the logarithm of the complementary predicted values. Finally, we compute the mean of these terms to average the loss across all samples. This implementation allows users to evaluate the performance of their binary classification models effectively. To illustrate the function in action, we provide an example with actual labels and predicted probabilities, followed by calculating and printing the resulting binary cross-entropy loss. Now let's implement the categorical cross-entropy function in Python. This function takes two inputs, the true label distribution ytrue and the predicted probabilities ypred. To ensure numerical stability during calculations, we first define a small constant epsilon, which is used to clip the predicted values. This prevents any zero values in ypred, which could lead to computational errors when taking the logarithm. Next, we apply this clipping to ypred, bounding it between epsilon and 1 epsilon. The core of the categorical cross-entropy calculation is then performed using the formula provided, which involves multiplying each true label by the logarithm of the corresponding predicted probability. The summation of these products across all classes measures the fit of the predicted distribution against the true distribution. Finally, we take the negative mean of this sum using NP, mean, which provides an average loss across all samples. To illustrate how this function works, we provide an example where ytrue is represented in a one-hot encoding format, indicating the true classes of samples, and ypred contains the predicted probabilities for each class. Running the function with these inputs results in a categorical cross-entropy value that quantifies the performance of the model's predictions, enabling us to understand how well it is learning. Now let's implement the Huber loss function in Python, a robust option that addresses the sensitivity to outliers in regression problems. The first step in our function is to calculate the error by subtracting predicted values from the actual values. We then assess whether this error is considered small by comparing its absolute value against a threshold defined by \\delta \. If the error is small, we use the squared loss formula to compute the loss, which helps when predictions are close to the true values. Conversely, if the error exceeds our threshold, we adopt a linear loss approach, which minimizes the impact of outliers by avoiding the squaring of larger errors. Another crucial point is that we make use of numpys in P, where a function to conditionally compute and return the appropriate loss value based on whether the errors are small or large. Finally, to ensure our function provides a meaningful output, we average the computed losses. We've also included an example usage where we define actual and predicted values before calling our Huber loss function. This succinctly demonstrates how to implement and evaluate Huber loss in practice, giving you a hands-on understanding of its application in dealing with outliers. The displayed figure, titled Loss Functions over Epochs, presents four labeled line plots, mean squared error, binary cross-entropy, categorical cross-entropy, and Huber loss, plotted against epochs on the x-axis and loss values on the y-axis. Each curve is marked at each epoch, and the legend identifies which curve corresponds to each loss function. Inspecting the curves, categorical cross-entropy consistently occupies the lowest position across most epochs, indicating lower loss values relative to the others in this run. Mean squared error appears at the higher end of the loss scale for most epochs, with Huber loss following closely behind MSE but generally showing slightly reduced peaks and troughs, which manifests as a tighter tracking to MSE with marginally lower variance. Binary cross-entropy sits between categorical cross-entropy and the MSE/Huber group, reflecting intermediate loss magnitudes. Across the 20 epochs, all four curves show modest fluctuations rather than a strictly monotonic decline, and there are a few short intervals where curves cross or approach one another, for example brief epochs where Huber and BCE values converge, signaling temporary shifts in relative performance. Overall, the chart conveys that, for this training trace, categorical cross-entropy yields the smallest loss values, MSE the largest, and Huber behaves as a compromise between sensitivity and robustness, while BCE remains intermediate. The modest vertical separation and absence of any runaway divergence suggests stable behavior among the compared loss functions over these epochs. Now let's implement a basic function to update the weights of our neural network using stochastic gradient descent. In this code, we start by calculating the error between the true labels and the predicted values, which gives us insight into how far off our predictions are. This error is crucial as it directly influences the adjustments we make to our weights. Next, we compute the gradient of the loss with respect to the weights by performing a dot product between the transposed input matrix and the error. This operation provides us with the direction and magnitude by which we need to adjust the weights to minimize the loss. By dividing by the number of samples, we ensure that our gradient computation remains consistent, reducing bias based on the batch size. Finally, we apply the learning rate to the gradient and then update the weights in the opposite direction. It's a step towards minimizing the loss. This update mechanism allows the model to converge toward a solution that fits the data better. Thus, this function encapsulates the core concept of weight adjustment in neural network training, demonstrating how to effectively steer our model towards improved performance. Now, as we wrap up, let's emphasize the importance of continuously evaluating and adjusting our choice of loss functions based on the model's performance. Training a model is often an iterative process, where we may find ourselves switching loss functions to achieve better results. Experimentation, validation, and a solid understanding of the underlying principles will lead us on the path to developing highly effective neural networks. Remember that loss functions are not just mathematical abstractions. They are the backbone to guiding your machine learning models toward improved accuracy and generalization. They are fundamentally tied to the goal of making our models better, so choose wisely, implement effectively, and watch as your models continuously improve. Thank you for joining today's discussion about loss functions. I hope you gained a better understanding of these concepts and how to effectively use them in your machine learning projects. Keep experimenting, keep learning, and I can't wait to see you in the next lesson. Optimizing learning rates for neural networks is a crucial topic that can significantly influence the efficiency and success of your training. The learning rate determines how much the weights of the model get updated during training, thereby building trust in the algorithm and its predictions. Today, we will dive deep into understanding how to effectively optimize learning rates, explore various strategies, and provide code examples to illustrate these concepts. So far, we learned about various loss functions used in neural networks, including mean-squared error, binary cross-entropy, categorical cross-entropy, and Huber loss. We explored how these functions can be implemented in Python, emphasizing their importance in minimizing prediction errors based on the specific task at hand. Additionally, we discussed the significance of selecting the appropriate loss function for model training and how it can affect the learning process. In the next lesson, we will cover the optimization of learning rates, a pivotal aspect that affects the model's learning dynamics and convergence. The learning rate is a hyperparameter that controls how much to change the model in response to the estimated error each time the model weights are updated. If the learning rate is too high, the model can overshoot the minimum of the loss function, leading to erratic jumps and potentially divergent behaviors. Conversely, if the learning rate is too low, the training process will take far too long to converge or may get stuck in local minima. Fine-tuning the learning rate is thus essential for training deep learning models effectively. The displayed figure, titled Impact of Learning Rates on Training Loss, shows loss values on the y-axis against epochs 1 through 20 on the x-axis for 3 labeled series: high learning rate, medium learning rate, and low learning rate. Each series is plotted with markers at every epoch and connected by lines, and a legend identifies each learning rate condition. The clear pattern is that the medium learning rate series consistently attains the lowest loss values across most epochs, clustering around a lower band, which indicates a faster and more stable approach toward minimizing loss. The low learning rate series occupies a middle band with slightly higher loss values and modest epoch-to-epoch variability, suggesting slower improvement but relative steadiness. The high learning rate series sits at the highest loss band and exhibits the largest fluctuations between consecutive epochs, indicating instability and likely overshooting during updates. Across the 20 epochs, the curves do not show dramatic monotonic decreases, but instead settle into distinct levels determined by the learning rate. This visual directly supports the conclusion that learning rate choice significantly influences both the final loss level achieved within these epochs and the stability of training dynamics. Now let's see how we can implement the mean-squared error function, which is essential for evaluating the performance of our linear regression model. We start by importing necessary libraries, specifically NumPy and Matplotlib for numerical operations and plotting, respectively. The mean-squared error function calculates the average of the squared differences between the true values and the predicted values, providing a straightforward metric for model accuracy. Next, we'll create a simple dataset that follows a linear pattern with some added noise to simulate real-world conditions. By setting a random seed for reproducibility, we ensure that the generated data remains consistent across different runs. The input variable x is created as a set of 100 points, while the output variable y follows the relationship defined by the equation y equals 4 plus 3x with random noise, which models how our data might behave in practice. Now let's implement the gradient descent algorithm, a crucial optimization method for fitting the linear model to our generated data. This function takes in the dataset and learning rate as parameters, initializes model coefficients randomly, and iteratively updates them by calculating gradients based on the loss function. Understanding this code will clarify how different learning rates influence the convergence of our model, thus bridging theory with practical application. Now let's implement a function for exponential decay of the learning rate. This function, exp_decay learning rate, takes 3 parameters: the initial learning rate, the decay rate, and the current iteration. As the iteration number increases, the function computes a new learning rate by applying an exponential decay formula. This approach gradually reduces the learning rate over time, allowing for larger adjustments when the model is far from the optimal solution and finer updates as it approaches convergence. Next, we will integrate this learning rate adjustment into our existing gradient descent function. The gradient descent with schedule function utilizes the exponential decay logic to modify the learning rate within a loop that iterates for a specified number of iterations. During each iteration, we've included a call to our decay function, which calculates the current learning rate based on the provided parameters. This updated learning rate is then used to adjust the model's weights, making the descent process more efficient. Finally, we can test this approach by running the gradient descent with a learning rate schedule, observing how the dynamic adjustment benefits the model training and improves parameter accuracy compared to using a fixed learning rate. Now let's implement a function for cyclical learning rates, which allows the learning rate to oscillate between a defined minimum and maximum value in a triangular waveform pattern. This approach can help the optimization algorithm escape local minima and potentially achieve better performance in complex datasets. In the cyclical learning rate function, we compute the current cycle and the position within that cycle using the iteration count in the specified step size. The resulting learning rate is then calculated, ensuring it varies smoothly between the base and maximum learning rates. Next, we will modify our gradient descent function to utilize these cyclical learning rates. In the gradient descent with cyclical LR function, we initialize parameters and set up our main loop for the specified number of iterations. For each iteration, we invoke the cyclical learning rate function to dynamically adjust the learning rate based on the current iteration. This allows the model to adapt its learning strategy throughout the training process, potentially leading to enhanced convergence in performance compared to a static learning rate. Finally, we will apply this cyclical learning rate in our training run, using reasonable parameters to observe its impact on the optimization. The results will demonstrate how this dynamic adjustment can effectively improve model training, showcasing the benefits of more sophisticated learning rate strategies. Now let's implement the Atom Optimizer, a popular method used for optimizing learning rates in machine learning. This function begins by initializing important parameters, including the number of samples, the model parameters, theta, and the input data matrix with a bias term. Two more variables, mt and vt, are introduced to hold the moving averages of the gradients and the squared gradients, respectively, starting from 0. In each iteration, the function calculates the gradients based on the current model parameters and the dataset. The moving averages are then updated using the beta values, which control the decay rates for the first and second moments. The algorithm incorporates bias correction to adjust these averages, preventing biases from initializing at 0. Finally, we update the model parameters using the computed moving averages. This adjustment is performed with a learning rate scaling based on the ratio of the bias-corrected averages. The ultimate goal is to improve convergence while adapting to the gradients dynamically. By running this optimizer, users can observe how effectively it fine-tunes the parameters for a linear regression model, showcasing the strength of the Atom optimization technique. In conclusion, we have traversed a rich landscape of learning rate optimization strategies, from fixed learning rates to advanced techniques like schedules, cyclic rates, and sophisticated optimizers like Atom. Each method serves its purpose and can be chosen based on the model, dataset, and task at hand. As we venture deeper into the realm of neural networks and machine learning, remember that a well-optimized learning rate is akin to fine-tuning an instrument. It can significantly impact the harmony of your model's performance. By understanding these concepts thoroughly, you equip yourself with the tools necessary to train models effectively, improve convergence times, and ultimately enhance their predictive capabilities. I hope this discussion of learning rates has been enlightening and encourages you to experiment with these approaches in your own projects. In our next lesson, we will further explore model evaluation techniques to understand how to assess the performance of our machine learning models effectively. Keep coding, keep learning, and I look forward to seeing you in the next session. Loss functions play a crucial role in training neural networks as they quantify how well the model's predictions align with the actual target values. Essentially, they help in understanding how far off our neural network is during training, providing a necessary signal for optimization. Today, we will explore various loss functions, their types, and how to implement them effectively in Python. Now let's implement the mean squared error (MSE) function in Python, which is a fundamental loss function for regression tasks. We start by importing the NumPy library, a powerful tool for numerical calculations in Python. The MSE function takes two arguments: yTrue, the actual target values, and ypred, the values predicted by our model. Within the function, we calculate the difference between the predicted values and the actual values, square these differences, and then compute the mean of these squared values using NumPy's mean function. This process gives us the average squared difference, which represents the MSE. To illustrate the use of this function, we create two NumPy arrays, ytrue with the actual values and ypred with the predicted values made by our model. By calling the mean squared error function with these arrays, we can compute the MSE and output the result. This practical implementation helps to firmly grasp the concept of measuring prediction accuracy in regression tasks, where lower MSE values indicate a better fit of the model to the data. Now let's implement the binary cross-entropy loss function. The function binary cross-entropy takes two parameters, ytrue, which consists of the actual class labels either 1 or 0, and ypred, which represents the predicted probabilities generated by the model. To prevent issues with logarithmic calculations, particularly when predictions are exactly 0 or 1, we apply clipping using np-clip. This ensures ypred values are bounded between a small value epsilon and \1 epsilon where epsilon is set to a very small number \1e12 . This step is crucial as it avoids taking the logarithm of 0, which would result in undefined values. The function then computes the binary cross-entropy loss using the standard formula, which assesses the divergence between the true and predicted distributions. The final output is the average of the computed loss values across all samples, where a lower result indicates better model performance. In the example usage provided, we define ytrue and ypred as NumPy arrays representing actual and predicted outcomes, respectively. By calling the binary cross-entropy function and printing the result, we evaluate the effectiveness of our classification predictions, allowing us to gauge how well the model aligns with actual class labels. Now let's implement categorical cross-entropy, a vital loss function for multi-class classification tasks. First, we define the function categorical cross-entropy, which takes two arguments, ytrue, representing the actual class labels in a one-hot encoded format, and ypred, which holds the predicted probabilities for each class. Inside the function, we introduce a small constant called epsilon to prevent numerical instability during logarithmic calculations. We then use np-clip to ensure that the predicted probabilities remain within a safe range, avoiding the possibility of taking the logarithm of 0. This stabilization helps maintain accuracy and prevents errors during computation. The core of the function calculates the loss by using the negative sum of the product of ytrue and the logarithm of ypred. We divide this sum by the number of samples, ytrue shape 0, to average the loss across all instances. A key takeaway is that a lower cross-entropy loss indicates that the model's predictions are closer to the actual labels. Finally, we demonstrate the function with an example that includes a one-hot encoded target array and corresponding predicted probabilities, showcasing how to obtain the categorical cross-entropy value for these predictions. Now let's see how we can implement focal loss, a modification of standard cross-entropy specifically designed to address class imbalance in tasks like image segmentation. In the code, we define a function named focal loss that takes the true labels ytrue, predicted probabilities ypred, and two hyperparameters, gamma and alpha. The parameter gamma controls the downweighting of easy examples, with higher values focusing more on difficult cases, while alpha balances the importance between classes. To ensure numerical stability and avoid log 0, we clip the predicted probabilities to a small range defined by epsilon. The core of the function calculates the loss using the formula that penalizes easy-to-classify samples less and emphasizes harder examples. This is achieved by multiplying the loss by 1 ypred gamma and adjusting the contribution using alpha. Finally, the function returns the average loss computed by summing all individual losses and dividing by the number of examples. Lastly, the code includes an example of using the focal loss function on a single sample, demonstrating its functionality by calculating and printing the resulting focal loss. This practical implementation showcases how focal loss can enhance model training, particularly in imbalanced scenarios. The displayed figure plots four loss functions, mean squared error, binary cross-entropy, categorical cross-entropy, and focal loss, across 20 epochs with per epoch markers. On the horizontal axis, epochs are labeled 120 and the vertical axis spans loss values from 0 to 1 in increments of 0.1. Each loss curve is shown with circular markers at every epoch and is identified in the legend. Key patterns visible in the data are: 1. Focal loss consistently registers the lowest loss values across nearly all epochs, remaining around the lower end of the 0-1 scale. 2. Categorical cross-entropy follows as the next lowest, with values consistently below those of MSE and BCE. 3. Mean squared error occupies a middle position, showing higher values than CCE but lower or comparable to BCE in many epochs. 4. Binary cross-entropy exhibits the highest average loss values across epochs. The perepic markers reveal small fluctuations for each loss, but no sustained large upward trends. The grid and tick spacing make the relative differences clear at each epoch. From this representation, we can conclude that, for these plotted runs, focal loss achieves the lowest and most stable loss trajectory, suggesting stronger optimization performance in scenarios emphasizing hard examples or class imbalance, while categorical cross-entropy is preferable to MSE or BCE when comparing multi-class classification behavior. These comparative rankings directly support choosing loss functions aligned with the task, focal approaches for imbalanced or hard example-focused problems, and categorical cross-entropy for multi-class classification. Now let's see how we can implement a simple feed-forward neural network using TensorFlow and Keras. We start by importing the necessary libraries, specifically TensorFlow and the Keras components. Next, we construct our model as a sequential stack of layers. This model includes a densely connected layer with 32 units and a ReLU activation function which introduces nonlinearity, allowing the network to learn complex patterns. The input shape parameter is defined to specify the expected input dimensions. The output layer is also a dense layer, but it has 3 units with a softmax activation function. This is particularly suited for multi-class classification tasks, as it outputs probabilities for each class, allowing us to assign the highest probability class as our prediction. Now let's configure the model by compiling it, specifying the optimizer and the loss function. We utilize the atom optimizer known for its efficiency and set categorical cross-entropy as the loss function, which is optimal for our multi-class classification scenario. Finally, we proceed to train our model using the fit method, passing in our training data, adjusting the model parameters over 10 epochs with a batch size of 32, which helps in minimizing the loss over time by updating weights based on the gradients derived from the loss function. Now, while selecting the loss function, it's also vital to consider the model and the dataset at hand. Different tasks, such as regression versus classification or dealing with imbalanced classes, require different strategies. Evaluating your model using these loss functions can also provide insights into how your model is performing under different conditions. So we discussed a variety of loss functions tailored for different types of tasks. We started with the basics, covering mean squared error for regression, and moved on to binary and categorical cross-entropy for classification. Then we examined focal loss for handling imbalanced datasets and ended with a practical implementation of a neural network where we integrated these loss functions. In conclusion, understanding and implementing the appropriate loss function is fundamental to successfully training machine learning models. Selecting the right loss function can significantly impact your model's learning trajectory, guiding it toward better performance. Now that we've delved into loss functions, in the upcoming lesson, we will shift our focus to model evaluation techniques to effectively assess our machine learning models and their performances. Stay tuned. Training a neural network is a fascinating journey that involves iteratively improving the neural network's weights to achieve optimal performance. This process hinges primarily on 2 fundamental operations: forward propagation and backpropagation. In this lesson, we will delve into how these 2 processes work together, all while using Python to illustrate key concepts with code examples. Now let's see how we can implement a simple neural network using Python and NumPy to understand forward propagation better. We begin by creating a simple neural network class that initializes the network's architecture, including input, hidden, and output layers. In the constructor, we are assigning random weights to the connections between the layers, which are crucial for learning. We also set a learning rate parameter that will guide how much we adjust the weights during training. Next, we define the forward method responsible for processing input data. When we pass an input vector through this method, it calculates the activation of the hidden layer by taking the dot product of the input data and the input to hidden layer weights. We then apply the sigmoid activation function to introduce nonlinearity, followed by computing the final output by again taking a dot product with the weights connecting the hidden layer to the output layer. Finally, we see an example of how to use the neural network by instantiating it with defined sizes for its layers and performing a forward pass using dummy data. This step illustrates how the model generates predictions, which we will further evaluate against actual targets in subsequent steps. Now let's explore how to calculate the mean squared error MSE to evaluate the performance of our neural network. We start by defining a function called mean squared error, which takes in 2 parameters, the actual target values ytrue and the predicted outputs from our model ypred. Inside this function, we compute the difference between the predicted values and the actual values, square those differences, and then calculate the mean of all squared values. This gives us a single MSE value that quantifies how far off our predictions are from the reality. Next, we need to provide the actual target output for our neural network, which in this case is set to 0.7. We create a NumPy array containing this value and assign it to yTrue. With both our actual output and the model's predicted output from the forward pass, we can calculate the MSE using our defined function. The resulting MSE variable stores the calculated error, which we then print out. This gives us a clear indicator of how well our model is performing, essential for understanding and refining our training process. This assessment of performance is pivotal in guiding our adjustments during the backpropagation process that follows. Now let's implement the backpropagation method, which is crucial for updating our neural network's weights based on the calculated loss. This method begins by calculating the output loss, which is the difference between the predicted outputs and the actual target values. By determining this loss, we can understand how far off our predictions are from the true values. Next, we calculate the gradients for the weights connecting the hidden layer to the output layer using the dot product of the hidden layer's outputs and the output loss. This helps us understand how adjustments in weights can minimize the output error. Moving backward into the hidden layer, we compute the hidden layer gradient, which incorporates the output loss, weights, and the derivative of the hidden layer's activation function. This tells us how much each hidden node contributed to the error. Once we have our gradient values, we proceed to update the weights by subtracting a fraction of the gradient scaled by the learning rate, which determines the step size for weight updates. This iterative process lets the neural network learn and refine its predictions with each training epoch, thereby minimizing the loss and improving performance. Now let's implement the training loop that allows our neural network to learn from the data over multiple epochs. In this section, we will simulate the training process for 100 epochs, ensuring that the model has ample opportunity to adjust its weights and improve its predictions. We start a loop that iterates through the specified number of epochs. For each epoch, we first call the forward method on our neural network, which processes the input data and generates predictions. This is followed by a call to the backpropagation method, where we provide the original input data and the true target values. In this method, the network calculates the error and adjusts the weights accordingly, enabling the model to learn from its mistakes. To monitor the model's progress, we include a conditional statement that checks if the current epoch number is a multiple of 10. If it is, we compute the mean squared error MSE between the predicted output and the true values, providing valuable feedback on the model's performance at regular intervals. By printing the MSE every 10 epochs, we can track how effectively our neural network is improving over time, which is essential for evaluating the success of our training process. The accompanying figure, titled Training and Validation Loss over Epochs, displays two clearly labeled curves with markers, a blue series for training loss and an orange series for validation loss, plotted across epochs 1 through 20 with a y-axis spanning losses from 0 to 1. Both curves start at higher loss values and exhibit a downward trend during the early epochs before flattening out, indicating that the model is converging. Consistently, the training loss lies below the validation loss by a modest margin, which reveals a small generalization gap. The model fits the training data slightly better than the validation data. The validation curve shows intermittent small upward fluctuations, while the training curve is comparatively smoother. These brief upticks on the validation line point to variance in validation performance, likely due to data noise or limited validation set size, and are the primary signal to monitor for potential overfitting. The minimum validation loss is reached in the mid to late epochs, after which both curves stabilize, suggesting an epoch range where early stopping could preserve the best generalization. Overall, the figure communicates that the model achieves low loss values approximately in the 0.304 range, is converging reliably, and should be monitored for minor validation fluctuations that could be mitigated with regularization or by selecting the epoch with lowest validation loss. Apart from monitoring accuracy through metrics like mean squared error, one can also utilize other metrics as needed, depending on the type of problem you're tackling. The beauty of the training process lies in tuning, experimenting, and optimizing. Upon refining hyperparameters like learning rates, batch sizes, and even architectures, it can feel a bit similar to fine-tuning a musical instrument for harmonious output. In conclusion, the training process of a neural network is an interplay between forward propagation to generate predictions, loss calculation to evaluate performance, and backpropagation to adjust weights based on this feedback. It's a cyclical process that continues iteratively until we reach a satisfactory level of accuracy or convergence. Understanding this process is fundamental for mastering neural networks and effectively utilizing them in practical applications. Now that we've woven through how neural networks learn, our next session will navigate the waters of model evaluation techniques. These techniques will help us measure how effectively our trained models perform and how we can leverage metrics to gauge their success at a granular level. Stay tuned. Welcome to today's lesson. We're diving deep into the fascinating world of neural networks by discussing a fundamental concept, implementing feedforward propagation. This is an essential process in training neural networks, and to keep things clear and relatable, we'll walk through a simple toy example where the input is 1, 1 and the expected output is 0. By the end of this lesson, you'll have a solid grasp of how feedforward propagation works in practice. Now let's see how we can implement the foundational components of our neural network in Python. First, we import NumPy, a powerful library for numerical computations. We define the sigmoid activation function, which will transform our input values and map them to the range between 0 and 1, facilitating easier interpretation of outputs. Alongside this, we also define the derivative of the sigmoid function, which we'll use later during backpropagation to adjust weights based on the error. Next, we set the seed for random number generation to ensure our results are reproducible. This consistency is crucial when debugging and testing our model. We then specify the sizes of the input layer, hidden layer, and output layer, which form the architecture of our neural network. The core of this implementation involves initializing the weights connecting the input to the hidden layer and the hidden layer to the output layer. We use np-random rand to assign these weights randomly, which is common practice in neural networks to break symmetry. Each weight will influence how inputs are transformed as they propagate through the network, playing a critical role in learning. Now let's see how we can implement the calculations for our neural network's feedforward propagation. We start by defining our input values, which are set to 1, 1 in this case, and we represent them in a 2D NumPy array. This format will allow us to perform matrix operations essential for our network's calculations. Next, we calculate the input to the hidden layer by performing a matrix multiplication of the weights connecting the input layer to the hidden layer and our input values. This step transforms the raw input data into hidden layer inputs. Once we have these input values, we apply the sigmoid activation function to them, resulting in the hidden layer output. This activation introduces nonlinearity to our model, allowing it to learn more complex relationships. Moving forward, we calculate the inputs for the output layer using a similar approach. We again use matrix multiplication, this time between the weights leading from the hidden layer to the output layer and the hidden layer output we just computed. Finally, we apply the sigmoid function to these output layer inputs to obtain the final output from our neural network. This entire process, layer by layer, showcases how information is transformed and propagated through the network, paving the way for making predictions based on our input data. Now let's take a look at how we can compute the mean squared error MSE to evaluate our neural network's predictions. First, we define the expected output as an array containing the target value of 0, representing our desired outcome for the input of 1, 1. This sets the benchmark for our model's performance. Next, we calculate the error by subtracting the model's output from this expected output. This gives us the difference between what we predicted and what we aim to achieve, indicating how far off our prediction is. To quantify this error further, we then square the differences. This step is essential because it ensures that both underestimations and overestimations contribute positively to the error metric. Finally, we compute the MSE by taking the mean of these squared errors, which provides a single numerical value representing the average error across predictions. This MSE value is crucial as it will guide us in the backpropagation step, helping to adjust the model's weights to improve future predictions. Thus, computing the MSE is a fundamental step in assessing the model's accuracy in this regression context. Before we conclude this section, let's talk about why it's important to visualize these processes. Understanding what happens during feedforward propagation gives insight not just for debugging purposes, but also for enhancing the network architecture and tuning hyperparameters down the line. Visualizations can simplify complicated processes, letting you as a learner see the internal workings of neural networks without getting lost in code. To visualize this feedforward propagation, consider using libraries like matplotlib to plot the layers and their connections. Making these abstractions visible can greatly enhance comprehension, especially when dealing with complex models. For instance, after each prediction, plotting the predicted output against the expected output can help in identifying trends. To wrap this up, let's revisit what we've covered. We began with an introduction to feedforward propagation, setting up a simple neural network with one hidden layer. Then we proceeded with the calculations involved in the feedforward step, moving from the input layer through the hidden layer to the output layer while applying the sigmoid activation function. Lastly, we looked at how to compute the mean squared error to assess our predictions. As we continue our learning journey, we will soon cover backpropagation, where we will take the error calculated from feedforward propagation and adjust our weights accordingly. This iteration process is key to refining our neural network and improving predictions over multiple training cycles. Thanks for watching, and I hope you found this explanation of feedforward propagation engaging and helpful. Don't forget to practice by implementing this in your own code and experimenting with different architectures or data inputs. See you in the next lesson. Backpropagation is a pivotal algorithm that helps optimize the weights in neural networks, playing a crucial role in reducing the error or loss value. In this lesson, we'll explore how backpropagation works and how it adjusts weights to enhance the overall performance of a neural network. So far, we learned about the implementation of feedforward propagation in neural networks, including the setup of a simple architecture with input, hidden, and output layers. We explored how to compute activations using weighted connections and the sigmoid activation function, along with the importance of monitoring and calculating the mean squared error to evaluate predictions. This sets the stage for understanding how to refine our model through backpropagation. Our journey emphasized not only the mechanics of forward propagation, but also the value of visualizing these processes for better comprehension. Now we will talk about backpropagation, focusing on how it minimizes the loss by adjusting weights in a way that leads to improved predictions. Now let's see how we can calculate the error between our predicted output and the expected output of the neural network. The first line of code performs this calculation by subtracting our predicted output from the expected output. This difference, stored in the variable error, quantifies how far off our predictions are from the actual values we desired. Next, we will compute the output gradient using the calculated error to inform us about the necessary adjustments. The second line of code applies the derivative of the sigmoid function to the predicted output, which captures how sensitive the output is to changes in the input. By multiplying this with the error, we obtain the output gradient, which tells us how much we need to adjust the weights connecting the hidden layer to the output layer. This output gradient will drive the weight updates during backpropagation, helping to minimize the overall loss based on how much each neuron in the hidden layer contributed to the output error. Together, these steps are integral to refining our model and enhancing its predictive accuracy as we move forward in our training process. Now that we've calculated the output gradient, let's move on to updating the weights between the hidden layer and the output layer. We can implement this by adding the product of the transposed hidden layer output and the output gradient to the weights connecting these two layers. This matrix multiplication is efficient and ensures that each neuron's contribution is accurately aligned with the adjustments required for the output, effectively fine-tuning our model based on its performance. Next, we need to analyze how the error from the output impacts the hidden layer. To achieve this, we will propagate the output gradient back to the hidden layer to calculate the hidden layer error. This is done through another matrix multiplication between the output gradient and the transposed weights connecting the hidden layer to the output layer. Subsequently, we apply the sigmoid derivative to the hidden layer output to compute the hidden layer gradient. This gradient indicates how much to adjust the weights leading to the hidden layer, giving us the insights needed to optimize this portion of the network further. By following these steps, we effectively refine the performance of our neural network through backpropagation. Now let's see how we can implement the adjustment of weights connecting the input layer to the hidden layer. In this step, we utilize the logical structure we've established in backpropagation. We will update the weights by taking the product of the inputs and the gradients we computed for the hidden layer. This operation ensures that each input neuron's contribution to the hidden layer's output is accurately reflected in our weight adjustments. The expression weights input hidden plus equals inputs at hidden layer gradient accomplishes this by making use of matrix multiplication, denoted by the operator. By multiplying the inputs with the gradient of the hidden layer, we effectively calculate the necessary weight updates that depend on how strongly each input influenced the hidden layer's output. Through this process, we ensure that the optimization considers the impact of each input systematically, enhancing the overall learning capability of our neural network. This step is crucial to iteratively refining the model, enabling the network to learn from the data more effectively as it progresses through multiple cycles of forward propagation and backpropagation. Now, let's implement the following function that brings together both the feedforward and backpropagation processes into a single streamlined training method for our neural network. The trained neural network function starts by calculating the hidden layer's inputs via matrix multiplication of the input weights and the actual inputs. After determining the hidden layer outputs using the sigmoid activation function, the process continues by calculating the predicted outputs from the output layer. Next, we assess the performance of the model by computing the error, which informs us about the difference between the expected and predicted outputs. This discrepancy is crucial as it drives the adjustments we need to make during backpropagation. We proceed by calculating the output gradient, applying the sigmoid derivative to the predicted outputs, thus setting the stage for updating our output layer weights. Subsequently, we backtrack to the hidden layer, determining how much each neuron contributed to the error and applying the chain rule to calculate the hidden layer gradients. Finally, we update both sets of weights, those connecting inputs to hidden neurons and hidden neurons to outputs, by incorporating the learning rate, ensuring controlled weight adjustments. This comprehensive approach enables our neural network to learn iteratively, refining its predictions with each iteration. Now let's implement a basic test to see how our neural network performs with a simple set of inputs. We start by defining our input data and the expected output. In this case, we use two input neurons, both taking the value 1, and we expect the output to be 0. To ensure reproducibility, we set a random seed. This allows us to initialize the weights, controlling the connections between the layers consistently. Next, we generate random weights for the connections between the input and hidden layers, as well as between the hidden and output layers. These weights will be updated as the network trains. The training process runs over 10,000 epochs, where in each epoch we call the defined trained neural network function. This function takes the current input's expected output and the weights along with a specified learning rate, allowing the network to learn from the data incrementally. After each training cycle, the weights are adjusted based on the gradients calculated during backpropagation. Once training is complete, we print the final output produced by the network. This output reflects how well the network has learned to predict based on the provided inputs, giving us insight into its performance and efficacy. The figure titled Mean Squared Error (MSE) during backpropagation displays a line plot of MSE values across 10 epochs. On the horizontal axis are epoch numbers 1 through 10, and on the vertical axis the MSE values range from 0 to 0.6, with grid lines to aid reading. Each epoch is marked with a circular marker and annotated with its exact MSE value: 0.5, 0.4, 0.3, 0.2, 0.15, 0.1, 0.05, 0.02, 0.01, and 0.005. The curve shows a clear monotonic decrease in training error across epochs. With relatively large reductions in the earliest epochs, each of the first few steps drops by about 0.1, and progressively smaller improvements in later epochs. For example, reductions shrink from 0.05 to 0.02, then to 0.01 and 0.005. This pattern indicates rapid early learning followed by diminishing returns as the network approaches convergence. From these values and annotations, we can conclude that the backpropagation updates effectively reduce the loss, with most of the error eliminated within the first several epochs and fine-tuning happening thereafter. The steep early descent suggests the learning rate and weight updates were sufficient to make significant early progress, while the tapering of the curve implies gradients, and therefore weight updates, become smaller as the model nears a low error state, signaling convergence toward a stable set of weights. As a refresher, backpropagation allows us to fine-tune the weights within our neural networks by evaluating the gradients of the loss function, informing weight adjustments that minimize error. This technique harnesses the powerful chain rule from calculus, making it efficient to process multi-layered networks. Combining feedforward and backpropagation into a cohesive function streamlines the training process and allows for rapid experimentation with different datasets or architectures. Understanding the intricacies of backpropagation equips you with a powerful tool for optimizing neural networks, setting the foundation for more advanced concepts such as convolutional neural networks, recurrent neural networks, and parameter tuning. Now let's talk about some best practices when training neural networks through backpropagation. One crucial practice is to monitor the training process closely for any signs of overfitting or underfitting. Overfitting occurs when the model learns the training data too well, capturing noise and outliers instead of the underlying data pattern. It often leads to poor performance on unseen data. To mitigate overfitting, techniques such as dropout, regularization, and early stopping can be incredibly effective. Dropout randomly omits a proportion of neurons during each training epoch, promoting independence and diversity, which reinforces generalization across different datasets. Underfitting, on the other hand, occurs when the model is too simple to capture the complexity of the data. This can usually be resolved by adding more layers or increasing the number of neurons per layer. Another critical aspect when utilizing backpropagation effectively is batching your data for training. Instead of using the entire dataset in one go, splitting it into smaller batches can enhance training efficiency while ensuring that more updates are conducted based on varied samples. This technique is known as mini-batch gradient descent, combining the benefits of both stochastic and batch gradient descent. By using mini-batches, we introduce a smoothing effect that allows for more accurate gradient estimates while maintaining the speed of updates that comes with smaller batches. This technique can improve convergence rates significantly and lead to better overall training dynamics. As we wrap up our discussion on backpropagation, remember that fine-tuning your neural network's weights is an iterative and ongoing process. Whether you are training a simple feed-forward network or a complex deep learning architecture, understanding backpropagation will empower you to find the optimal weights and improve your predictions. In conclusion, backpropagation is at the heart of building effective neural networks, striking the balance between learning from data and refining predictions. We combine theoretical concepts with practical coding examples to illustrate the process in detail, ensuring you gain both knowledge and hands-on experience. Going forward, we will delve into advanced techniques, additional types of layers, and how various neural network architectures can be constructed for specific applications. Keeping the principles of feed-forward propagation and backpropagation in mind will serve as your stepping stone as we embark on even more exciting topics in the world of artificial intelligence. Thank you for joining me today, and I hope you found this exploration of backpropagation both informative and illuminating. Happy coding! Let's dive into the fascinating world of gradient ascent, a method that, although often overshadowed by gradient descent, plays a crucial role in optimization, particularly in machine learning. Gradient ascent, as the name implies, is about moving upwards, literally increasing our function value by adjusting parameters. If you've ever found yourself at the bottom of a hill and wanted to reach the summit, gradient ascent is like finding the steepest path to the top. So far, we learned about backpropagation, a critical algorithm in optimizing neural networks by minimizing loss through weight adjustments. We explored how to calculate gradients using the chain rule of calculus, enabling efficient updates for each layer. This process involves executing feed-forward and backpropagation in a single cohesive function, allowing for iterative training and fine-tuning of network weights. Additionally, we discussed best practices such as monitoring for overfitting and underfitting, and the advantages of using mini-batch gradient descent to improve training efficiency. Now we will cover the concept of gradient ascent, where the aim is to maximize a function, a technique utilized in various applications, including reinforcement learning and maximizing the likelihood in statistical models. The figure titled Gradient Ascent Scenarios displays function value versus iterations and includes three labeled curves for different learning rate scenarios. Learning rate equals 0.1, 0.05, 0.01. All three curves overlap exactly, forming a single downward opening parabola with a clear single peak at iteration 2 where the function value reaches 4. The x-axis runs from 0 to 30 with ticks every 2 iterations, and the y-axis spans roughly from -10 to 10 with ticks every 2 units, which makes the early sharp rise and the subsequent symmetric decline easy to read. Key patterns visible are 1. A very early maximum reached at iteration 2, 2. Symmetric decay in function value as iterations move away from that peak, and 3. Identical trajectories for all labeled learning rate scenarios, which in this visualization emphasize the objective's shape rather than distinct optimization paths. From this display, we can conclude that the objective has a single, well-defined maximum located at iteration 2 with magnitude 4, and that any meaningful comparison of learning rate effects would require differences to be reflected in the plotted values. As shown, the figure highlights the importance of where the peak lies and how rapidly the value falls off on either side. Now let's see how we can implement gradient ascent in Python. We start by defining a function to maximize, which takes an input \x_ and computes the value of the quadratic function \x2 plus 4x \. Next, we define its gradient captured in the gradient function, which calculates the derivative of our function and returns the slope at any given \x\. For the actual optimization process, we create the gradient descent function. This function accepts a starting point, a learning rate, and the number of iterations as parameters. Inside the function, we initialize \x_ at the starting point and loop through the specified number of iterations. During each iteration, we compute the gradient at the current \x_, using our gradient function and then update \x by moving in the direction of the gradient scaled by the learning rate. The idea here is to incrementally push \x towards the maximum value of our function. After defining our Ascent algorithm, we set the parameters, an initial starting point of 0, a learning rate of 0.1, and we plan to take 20 steps. Finally, we call our gradient ascent function to find \x at its maximum and compute the corresponding function value, printing the results to observe the outcome of our optimization process. Now let's see how we can implement gradient ascent in 2 dimensions, a step beyond our previous one-dimensional example. We begin by defining a function called function to maximize 2D, which models a concave function centered around the point 2, 3. Our goal is to find the maximum of this function. Next, we create a gradient function 2D that calculates the partial derivatives of our function with respect to both variables \x and \y. This is crucial as it tells us how to adjust our parameters in order to ascend towards the maximum. Then we define the main method, gradient ascent 2D, where the actual ascent takes place. We start at an initial point and iteratively update both \x and \y according to their respective gradients scaled by a specified learning rate. This allows the method to adjust the parameters simultaneously in each iteration, making our ascent more efficient. After setting the parameters, such as the starting points and the number of iterations, we call our ascent function and capture the resulting maximum coordinates. Finally, we calculate the maximum value of the function at those coordinates and print the results, illustrating the effective application of gradient ascent in a multidimensional context. Next, we will implement a learning rate schedule in our 2D gradient ascent example. In the function gradient ascent 2D with schedule, we start by initializing our parameters, the starting coordinates start point x and start point y, and the initial learning rate, which allows us to adjust how quickly we ascend. Within a loop that runs for a defined number of iterations, we compute the gradients using the gradient function 2D, which tells us the direction in which our function increases most steeply. After updating our coordinates by moving in the direction of the gradient scaled by our current learning rate, we then modify the learning rate itself for the next iteration. This adjustment involves reducing the learning rate over time, specifically by dividing the initial learning rate by 1 plus the iteration count divided by 10. This strategy enables a more pronounced exploration at the beginning of the ascent, allowing you to quickly gather information about the function's landscape. As the optimization progresses, the fine-tuning becomes more precise with smaller learning rates, promoting convergence towards the maximum efficiently. Finally, we conclude by returning our optimized coordinates and calculating the maximum function value at those coordinates, which is printed out for verification. Next, we will write the following implementation for gradient ascent utilizing momentum to enhance our convergence rate. In the function gradient ascent with momentum, we initialize our starting parameters along with a velocity vector for both dimensions vx and vy. This velocity helps track the past gradients, which smooths out our updates. During each iteration, we compute the gradients using gradient function 2D, which returns the necessary slope to ascend the function. The core of the momentum technique lies in updating the velocity. We retain a portion of the previous velocity while adding a fraction of the current gradient. This weighted approach reduces oscillations and propels us in directions where the gradients remain consistent. Following the velocity update, we adjust our parameters x and y by scaling the velocities with the learning rate. This ultimately moves our position closer to the optimum. Lastly, we call the function with our defined starting points and learning parameters, storing the results in maxx and maxy. By employing momentum, we can achieve smoother trajectory paths toward the peak, allowing for faster and more effective optimization. Now let's see how we can implement a stopping criterion in our gradient ascent algorithm to enhance efficiency. The function begins by accepting the starting coordinates, an initial learning rate, the maximum number of iterations, and a tolerance level for the gradient's magnitude. It initializes the variables for coordinates to the starting points and enters a loop that runs for the specified number of iterations. Inside the loop, we compute the gradient at the current coordinates to determine the direction of ascent. Crucially, we check if the magnitude of the gradient calculated using the Euclidean norm falls below the predefined tolerance. If this condition is met, it indicates that further updates would yield minimal changes, so we break out of the iteration, saving unnecessary computations. If the gradient is still significant, we apply the learning rate to update the coordinates. This process repeats until either convergence is achieved or the maximum number of iterations is reached. Ultimately, the function returns the coordinates of the maximum found. We then utilize this function to obtain the maximum values and print the results, emphasizing both the computed coordinates and the function value at that point. So now we've covered quite a lot about gradient ascent, including its basic mechanism, application in multivariable scenarios, learning rate schedules, momentum, and stopping criteria. This breadth of understanding enables you to apply gradient ascent effectively in various optimization tasks, especially in machine learning contexts like maximizing performance metrics. As a quick recap, we started by defining gradient ascent, exploring its function maximization principles with code examples. We then moved into higher dimensions and learning rate schedules to enhance learning strategies before addressing momentum and convergence criteria. Each element discussed allows for a more robust approach to optimization. Moving forward, it's exciting to think about how these concepts will enhance your understanding of neural networks and complex optimization problems. By mastering gradient ascent and its variations, you're well on your way to creating more efficient and high-performing models. In the next session, we will discuss gradient descent's cousins, which are algorithms like ADAM and RMS-prop, designed to address some of the intricacies we've touched on today. Let's keep building on our knowledge and stride forward in the realm of machine learning. In this lesson, we'll dive into the architecture of neural networks and explore the essential concept of feedforward propagation. This process is fundamental for estimating the loss or error in a neural network's architecture. Understanding how these components work together will set a strong foundation for more advanced topics down the line. So far, we learned about the concept of gradient ascent, a crucial optimization method that aims to maximize function values through directional adjustments of parameters, akin to climbing a hill towards a peak. We discussed the mathematical foundation of updating parameters using the gradient and explored its application in both single and multidimensional functions. Additionally, we examined strategies like learning rate schedules, momentum, and convergence criteria to enhance the efficiency and effectiveness of the ascent process. This comprehensive understanding sets the stage for applying gradient ascent in various optimization tasks, particularly in machine learning. Now we will talk about how neural network architecture is designed with a focus on feedforward propagation. To begin our exploration of neural networks, let's clarify what we mean by architecture. Think of a neural network architecture as the blueprint for a building. It defines how neurons, the building blocks, are connected. Architecturally, we typically have an input layer, one or more hidden layers, and an output layer. Each layer consists of a number of neurons, which can be thought of as individual units that receive input, perform computations, and pass their output on to the next layer. The input layer takes in the input data, which can be anything from images to text. The hidden layers, which can vary in number and size depending on the complexity we're dealing with, are where the magic happens. These layers transform the inputs into something the network can use to make predictions or classifications. Lastly, the output layer delivers the final result. For instance, in a classification problem, it might output the probability that a given input belongs to a specific category. Now let's see how we can implement the feedforward propagation process in our neural network using Python. We start by importing NumPy, a powerful library for numerical computations. The first function we define is the sigmoid activation function, which will help us introduce nonlinearity into our model. This function takes an input and applies the sigmoid formula, outputting values between 0 and 1, which is critical for our neural network's operations. Next, we outline the architecture of our neural network. We define the input layer to receive two-dimensional data, specifying an example input. The weights connecting the input layer to the three neurons in the hidden layer are initialized as a 2D array, while each neuron is assigned a bias. Following this setup, we compute the activations for the hidden layer. This is achieved by calculating the dot product of the weights and the input data, adding the biases, and then applying the sigmoid function to obtain the hidden layer's output. Finally, we utilize a print statement to display the results of the hidden layer output, which will be subsequently fed into the output layer in our complete neural network model. Next, we will write the code to add the output layer to our neural network, which is crucial for transforming the hidden layer outputs into final predictions. In this code, we first define the weights that connect the hidden layer to the output layer and set a bias for the output layer. The weights, represented as a NumPy array, are crucial as they influence how the output layer treats the data coming from the hidden layer. Once we have our weights and bias defined, we calculate the input to the output layer by performing a dot product between the hidden layer outputs and the weights. This computes a weighted sum of the hidden layer's activations. Afterward, we add the bias to this sum and apply an activation function to determine the final output. Here we utilize the sigmoid function, although in some cases, particularly for multi-class classification tasks, the softmax function may be more suitable. Finally, we print the output from the output layer, revealing the result after passing through the neural network's architecture. This output provides the probabilistic scores for each class, guiding the model's predictions. Now let's take a look at how we can calculate the mean squared error, MSE, to evaluate our network's output against the expected value. We begin by defining the actual output as a NumPy array, which in this case represents the value we expect from the network. In this example, we assume it to be 1. This setup is crucial because it serves as the benchmark against which we will compare our network's predictions. Next, we compute the loss using the MSE formula, which involves taking the difference between the predicted output from the output layer and our actual expected output. We then square this difference to ensure that our losses are non-negative, following which we calculate the average of these squared differences using NP-mean. The resulting value provides a quantification of the error in our network's predictions, indicating how close or far off the output layer's predictions are from the actual output. Finally, we print this loss value, allowing us to visualize the performance of the neural network. This metric will be crucial in our subsequent backpropagation steps, as it informs how to adjust the weights to enhance the network's accuracy in future iterations. Understanding this loss is pivotal in guiding the training process effectively. The figure displays loss values over 10 epochs for two neural network architectures labeled Model A convolutional blue line with circular markers and Model B vanilla orange line with square markers. The x-axis enumerates epochs 1 through 10 and the y-axis shows loss values from 0 up to 1. Key patterns are both models reduce loss monotonically across epochs, indicating learning, but Model A consistently attains lower loss than Model B at every epoch. Quantitatively, Model A starts at 0.8 and declines in even steps to 0.3 by epoch 10, showing a steady decrease of about 0.05 per epoch. Model B starts higher at 0.9, drops more sharply early to 0.75 by epoch 3, but then slows, reaching 0.55 by epoch 10. The gap between the models widens over training, about 0.1 at epoch 1, growing to by epoch 10, which suggests the convolutional architecture both converges faster and reaches a lower final loss than the vanilla architecture for this task. From this visualization, we can conclude that, for the same training schedule and measured by loss over epochs, the convolutional design offers a consistent advantage in both convergence speed and final performance, while the vanilla model shows diminishing returns after early improvements. As we delve deeper into neural network architectures, we can also discuss the role of hyperparameters in our designs. Hyperparameters are settings or configurations used to optimize the learning process of a neural network. Examples include the number of hidden layers, the number of neurons in each layer, the learning rate, and the types of activation functions. Choosing the right hyperparameters can significantly affect the performance of your neural network. However, the process can be somewhat like cooking. There's no one-size-fits-all recipe. You often have to experiment to find a mixture that works best for your particular problem. For instance, consider a neural network with an excess number of hidden layers or neurons, leading to overfitting. This is when the network learns the training data too well, capturing noise rather than the underlying distribution. On the other hand, having too few layers or neurons might lead to underfitting, where the model fails to learn the data adequately. Regularization techniques and cross-validation strategies play an essential role in managing these hyperparameters effectively. Now let's implement the following code to build a simple convolutional neural network, CNN, using Keras. We begin by importing the necessary modules, sequential for our model structure and layers such as conv2d, flatten, dense, and dropout that will form the architecture of our network. We create a sequential model which allows us to stack layers linearly. First, we add a conv2d layer with 32 filters and a kernel size of 3 by 3. This layer acts as the input layer designed to process 28 by 28 pixel images in grayscale, using the RayLU activation function to introduce nonlinearity, essential for learning complex patterns in the data. Following the convolutional layer, we add a flatten layer, which transforms the 2D outputs into a 1D vector. This flattened output is then passed to a dense layer with 128 neurons and RayLU activation, serving as our hidden layer. To combat overfitting, we incorporate a dropout layer that randomly drops 50% of the neurons during training. Finally, the output layer is composed of another dense layer with 10 neurons and a softmax activation function to produce probabilities for multi-class classification. Lastly, the model compiles using the Atom optimizer and categorical cross-entropy loss, making it ready for training on a dataset for image classification tasks. Next, we will write the following code to evaluate the performance of our trained neural network model using our test dataset. This evaluation process is critical as it gauges how well the model has learned to generalize from the training data to unseen data, which is vital for real-world applications. In the code, we begin by assuming that xtest holds the test data and ytest contains the expected output labels. By calling the evaluate method on our model, we can compute both the loss and accuracy metrics based on the test dataset. The verbose equals 0 option runs the evaluation quietly, without displaying detailed logging information during the calculation. After the evaluation, we capture the results in the variables loss and accuracy. Finally, we print these metrics to the console, allowing us to see the test loss and accuracy scores. By analyzing these results, we can determine if the model's current architecture and training approach deliver satisfactory performance, or if we need to revisit our design choices or hyperparameters for improvement. As we wrap up our discussion on neural network architecture design, we've covered a variety of essential topics. From the foundational building blocks of neural networks and the feedforward propagation process to the roles of hyperparameters and model evaluation. This understanding creates a solid groundwork for delving into more advanced topics like backpropagation and optimization techniques in the future. Neural network architecture design is a blend of art and science, where intuition and experimentation come together to produce effective models. The process often involves tweaking various components, assessing model performance, and iterating, learning from the results to build a better structure. In our next lesson, we'll transition from feedforward propagation to backpropagation, the method that allows us to compute gradients for optimally adjusting weights within our network. This will take our understanding of neural networks to the next level, providing us with the tools needed to improve model performance significantly. Through this journey of exploration in neural networks, remember that every design decision and learning process you encounter contributes to your growth as a data scientist or machine learning practitioner. So stay curious, give experiments a shot, and happy coding. An artificial neural network, ANN, is a fascinating computational model that is designed to loosely mimic how the human brain operates. Essentially, ANNs consist of collections of tensors or weights arranged through mathematical operations. This architecture enables them to learn from data, make complex decisions, and even exhibit behaviors such as pattern recognition. So far, we covered the architecture of neural networks, discussing the interaction among input, hidden, and output layers. We explored feedforward propagation, the significance of weighted sums, activation functions, and how they translate inputs into predictions. Additionally, we discussed loss functions that assess prediction accuracy and touched on hyperparameters that help optimize the network's performance. Now we will cover backpropagation, a crucial technique that improves our ability to tweak weights based on the errors encountered during predictions, ultimately enhancing the model's output. Now let's implement a simple artificial neural network, ANN, using NumPy that encompasses the core functionality of backpropagation covered earlier. We begin with the definition of the simple ANN class, where we initialize critical parameters such as the size of the input, hidden, and output layers, along with a learning rate that dictates how much we adjust the weights during training. The weights are initialized randomly to break symmetry and allow for learning. Next, we incorporate the sigmoid activation function, which squashes the output to a range between 0 and 1, and its derivative essential for backpropagation. The heart of the training process is encapsulated in the train method, where we execute both the forward pass and backpropagation. The forward pass involves calculating the hidden and final outputs by applying the weighted sums and activation function. Following this, we compute the error by comparing the predicted and actual target values. Now we derive the necessary gradients to adjust the weights during backpropagation. We calculate the derivative of the hidden and output layers, allowing us to update the weights accordingly. Finally, we track progress by outputting the error every 1,000 epochs, reinforcing the concept that patience is key in training neural networks as they refine their predictions over many iterations. The figure titled Training Loss of Discriminator and Generator over Epochs displays epochwise loss traces for two models across 100 epochs, a blue line with circle markers for the discriminator loss, and a red line with X markers for the generator loss. The x-axis enumerates epochs from 1 to 100 while the y-axis shows loss values. Quantitatively, the plotted trends reflect a roughly linear change driven by plus or minus 0.005 per epoch. The discriminator curve trends downward by about 0.5 over the full run, and the generator curve trends upward by about 0.5. Visually, the discriminator loss starts higher, around 0.5 on average, and steadily decreases with small epoch-to-epoch fluctuations, indicating that the discriminator's predictions are improving over training. Conversely, the generator loss begins lower, around 0.3 on average, and steadily increases with similar fluctuations, indicating that the generator is becoming less effective at fooling the discriminator as training progresses. The consistent divergence between the two curves, decreasing blue versus increasing red, points to an imbalance emerging during training. The discriminator gains strength while the generator struggles to keep up. The marker-by-marker plotting makes it clear that these are per-epoch measurements, not smoothed averages, so the small ups and downs correspond to stochastic updates. From these displayed patterns, we can conclude that under the current training regime, the two components are moving in opposite directions, which suggests a need to rebalance training dynamics, for example, by adjusting relative learning rates, update frequency, or loss formulation, if the goal is to achieve convergence where both losses stabilize rather than diverge. Now let's take a look at how we can implement the ReLU activation function in our artificial neural network. We begin by defining the ReLU method, which applies the ReLU transformation by returning the maximum value between 0 and the input. This nonlinear transformation is pivotal in enabling the network to learn complex patterns. Next, we include the ReLU derivative method, which calculates the derivative of the ReLU function. It returns 1 for inputs greater than 0 and 0 otherwise, crucial for the backpropagation step, allowing us to update the weights effectively based on the hidden layer's output. Moving on to the train with ReLU method, we alter the training process to utilize the ReLU activation for the hidden layer. During each epoch, inputs are multiplied by the weights, passed through the ReLU function to obtain the hidden layer's output, then processed through the output layer, which still uses the sigmoid function for binary classification compatibility. We calculate the output error and employ the ReLU's derivative for adjusting the weights in the hidden layer. This systematic approach not only enhances learning efficiency, but also addresses the vanishing gradient issue, allowing the network to better navigate complex datasets while maintaining efficacy in binary classification tasks. Now let's see how we can implement L2 regularization in our training method to enhance the performance of our neural network. The method train with regularization takes the inputs, targets, number of epochs, and a regularization parameter L2 lambda, which controls the strength of the penalty. As we progress through each epoch, we still perform a forward pass to calculate the hidden and final outputs just as before. After computing the error between the target and final output, we derive the gradient necessary for backpropagation. However, what sets this method apart is the incorporation of the L2 penalty, which we apply to the weights after their updates. Specifically, we subtract the product of L2 lambda and the current weights from the updated weights of both the output layer and the input to hidden layer. This additional step discourages the model from fitting the noise in the training data, promoting a simpler model that generalizes better to unseen data. Finally, we can use this method by calling and train with regularization with our training and target data. This allows the network to learn effectively while minimizing overfitting through regularization. As we conclude this section on building and enhancing neural network architecture, remember that the model's design and training dictate its performance. Understanding the trade-offs with activation functions, mastering backpropagation, and employing regularization techniques will significantly benefit you as you explore machine learning and deep learning. So far, we've covered the foundational elements required for building neural networks, the intricacies of architecture, the importance of activation functions, the mechanics of backpropagation, and the necessity for regularization. Armed with this knowledge, you are now ready to tackle the next challenges in the world of neural networks and indeed artificial intelligence itself. Happy coding, and may your models always converge. Training a neural network involves coming up with optimal weights for its architecture using iterative processes like forward propagation and backpropagation, combined with a specified learning rate. In this tutorial, we'll dive deep into the world of neural network optimization techniques, which are crucial for enhancing the performance of your models. So far, we learned the fundamentals of neural networks, including their architecture and the roles of input, hidden, and output layers. we discussed key processes such as feedforward propagation, backpropagation, and the significance of activation functions in transforming inputs into meaningful outputs. Additionally, we introduced regularization techniques to combat overfitting, ensuring that our models generalize well to new data. This foundational understanding prepares us for more advanced topics in machine learning and artificial intelligence. Now, we will cover optimization techniques that will not only speed up the training process, but also improve the convergence of our neural network models. Now let's see how we can implement the gradient descent process in our neural network training. The function gradient descent takes three parameters: weights, learning rate, and gradients. Here, the weights represent the current values assigned to each parameter in the neural network that we want to optimize. The learning rate controls how large the weight updates will be. In essence, it determines the step size in our search for the minimum of the loss function. The gradients parameter contains the values computed during backpropagation, which indicate the direction and magnitude of change needed for each weight to reduce the loss. The function works by adjusting the weights in the direction opposite to the gradient, which is a core principle of gradient descent. The line of code does this by subtracting the product of the learning rate and gradients from the current weights. This adjustment is critical as it moves the weights closer to optimal values, which ultimately helps in training the neural network more effectively. This simple yet powerful update rule is foundational for building more sophisticated optimization techniques that we will explore later. Next, we will implement stochastic gradient descent (SGD), a powerful optimization technique designed to enhance the training process of neural networks by updating weights incrementally based on a small number of training samples. In the function, we iterate through each input-target pair, allowing the model to perform a forward pass where it predicts the output based on the current weights. Following the prediction, we calculate the loss, which quantifies the difference between the predicted output and the actual target. Understanding this loss is crucial as it drives the necessary adjustments to the weights. After computing the loss, we move into the backward pass where gradients are calculated through backpropagation. These gradients indicate the direction and magnitude needed to adjust the weights to minimize the loss effectively. Finally, we apply the gradient descent method, adjusting the weights by moving them in the direction that reduces the loss based on the calculated gradients and the specified learning rate. By updating weights after each training example, we enable the model to learn dynamically, leading to potentially faster convergence compared to traditional batch methods. This implementation captures the essence of SGD, making it a vital technique in optimizing neural networks. Now let's implement the minibatch gradient descent technique to enhance our optimization process. This function starts by iterating through the training inputs in chunks or batches defined by the batch size. By dividing the dataset into smaller subsets, we can perform more frequent updates to the weights during training, which often leads to faster convergence. Within the loop, we extract the specific batch inputs and batch targets for each iteration. After that, the forward pass is executed for the minibatch, generating predictions from the current weights. We then calculate the loss associated with these predictions versus the true targets. This loss measurement drives our model's adjustments. Next, we compute the gradients using backpropagation based on the calculated losses, which informs how to adjust the weights. Finally, we update the network's weights using the standard gradient descent method, leveraging the learning rate to control the size of each update. By processing the data in minibatches, this approach strikes a balance between convergent stability and computational efficiency, allowing the model to learn more dynamically compared to traditional methods. The figure titled Loss of Generator and Discriminator over Epochs with Learning Rates displays two filled area series across 100 epochs, a red area for generator loss and a blue area for discriminator loss, with the x-axis labeled epochs and the y-axis labeled loss. Visually, the red generator area sits consistently above the blue discriminator area for most of the epoch range, indicating that the generator's loss values are generally higher than the discriminators. Across epochs, there is a subtle downward trend in the generator loss. The red area narrows slightly from left to right, while the discriminator loss blue area shows a mild upward trend. Together, these trends create a narrowing gap between the two areas in portions of the plot. The shading and overlap make it clear where losses diverge or converge. Areas of larger vertical separation indicate stronger relative performance difference between the two networks, whereas epochs where the shaded regions approach each other signal closer loss magnitudes. The chart also shows variability fluctuations in both losses across epochs rather than a perfectly smooth line, highlighting stochastic changes during training. From this visualization, we can conclude that over the shown epochs, the generator appears to be improving loss decreasing, while the discriminator's loss is increasing slightly, suggesting a shifting balance between the two. The changes are gradual rather than abrupt, and the overall magnitude of loss fluctuations is an important factor to monitor when deciding whether to adjust learning rates, use adaptive optimizers, or apply scheduling to restore or maintain training equilibrium. Now let's take a look at the implementation of the ADAM optimizer, a well-known adaptive learning rate method that builds on ideas from both AdaGrad and RM-Sprop. In this code, we begin by updating the biased first moment estimate, which is essentially the moving average of the gradients. This is done using the parameters beta1, which controls the decay rate of these moments. Next, we update the biased second moment estimate, which tracks the moving average of the squared gradients, using a similar approach with beta2. These moments allow the optimizer to adaptively adjust the learning rates for each parameter based on the gradients observed thus far. To counteract the bias introduced in the initial moments due to the initialization of M and V, we compute bias-corrected estimates for both moments. This ensures that the current estimates are more accurately reflective of the true moments as training progresses. Finally, we update the weights by applying the computed moment estimates, scaled by the learning rate and adjusted for numerical stability using epsilon. This systematic approach enables stable and efficient training, significantly influencing convergence speed and performance in neural networks. Now let's implement a step decay function that adjusts the learning rate based on the training epoch. This function takes 4 parameters: the current epoch number, the initial learning rate, the drop epoch interval, and the drop factor. It checks whether the current epoch is a multiple of the specified drop epoch and ensures that it's greater than 0. If both conditions are met, the learning rate is multiplied by the drop factor, effectively reducing it. This approach helps prevent overshooting the minimum during training by allowing the model to take smaller steps as it approaches the optimal solution. If the epoch does not meet the criteria for decay, the function simply returns the initial learning rate. Understanding how to manage the learning rate is crucial for optimizing neural network training, as it can greatly influence the convergence process. By strategically adjusting this parameter, we can enhance the performance of our model and fine-tune its learning capabilities, ensuring that it adapts more effectively as training progresses. As we wrap up our discussion on optimization techniques in neural networks, it is crucial to remember that these strategies are not one-size-fits-all. They must be adapted based on the specific problem, dataset, and network architecture. Understanding how to manipulate learning rates, leverage adaptive methods, and implement effective scheduling can drastically alter the efficiency and results of your training process. By continuously iterating and experimenting with these techniques, you can shape a powerful neural network capable of incredible feats in machine learning and artificial intelligence. So there you have it. By mastering these optimization techniques, you're not just going through the motions, you're equipping yourself with skills that can translate into practical solutions across various domains. Keep experimenting, stay curious, and happy coding. Let's dive into the world of neural networks, focusing on their architectures and crucial components, especially feed-forward propagation. Understanding these concepts is vital as they form the backbone of deep learning, and they play a pivotal role in how neural networks learn and make predictions. So far, we learned about the importance of optimization techniques in training neural networks, focusing on methods to minimize the loss function effectively. We explored gradient descent and its variants, including stochastic gradient descent and minibatch gradient descent, to enhance convergence rates during training. Additionally, we discussed adaptive learning rates and learning rate scheduling as strategies to improve performance and training efficiency. This knowledge sets the stage for further exploration of neural network optimization in practical applications. Now, we will cover the architecture of neural networks, particularly focusing on feed-forward propagation and its role in estimating loss. Neural networks are structured like a series of layers, each containing a set of nodes or neurons. The simplest architecture consists of 3 types of layers: the input layer, the hidden layer, and the output layer. Each layer has its unique role. The input layer receives the data, the hidden layers process this data through weighted connections, and the output layer provides the final predictions. Think of it like an assembly line. Each step transforms the data a little more until you receive the finished product at the end. The displayed bar chart titled Neural Network Layer Activations shows activation outputs for 4 successive layers. Input layer 0.2, hidden layer 1 0.5, hidden layer 2 0.8, and output layer 0.9. The vertical axis ranges from 0 to 1, so all activations lie within the normalized output range typical of sigmoid-like activations. Key patterns are a clear monotonic increase in activation magnitude from the input through the hidden layers to the output, with the most substantial jump occurring between hidden layer 1 0.5 and hidden layer 2 0.8. This progression indicates that as the signal is propagated forward, the intermediate representations become increasingly activated. Hidden layers are amplifying feature responses, and the network is producing a strongly activated final output, 0.9, suggesting high confidence toward a particular prediction. The grid on the y-axis and labeled layers make these numeric differences easy to read. From a model behavior perspective, the pattern suggests healthy signal propagation without collapse to near zero values, while the near saturation at the output, close to 1, implies the final activation is strongly decisive and would produce a low cross-entropy loss if the true label aligns with this high activation. Now let's see how we can implement a simple neural network in Python that demonstrates feedforward propagation. We start by importing the necessary library NumPy, which is vital for numerical operations. The neural network class is initialized with 3 parameters: input size, hidden size, and output size. These parameters dictate the configuration of our neural network structure, determining how many neurons are present in each of the input, hidden, and output layers. Within the constructor, we initialize the weights that connect these layers using random values. This randomness is crucial since it sets the initial conditions for our learning process. Next, we define an activate method that uses the sigmoid function as an activation mechanism. This function squashes input values to a range between 0 and 1, introducing nonlinearity essential for the neural network's ability to learn complex patterns. Now let's implement the feedforward method, where the magic happens. Inputs are processed through the network. We calculate the inputs to the hidden layer using a dot product with the corresponding weights, apply the activation function to get the hidden layer output, and repeat this process for the output layer. Ultimately, the output from this method gives us the predicted result based on the provided input data, showcasing how our basic neural network operates through feedforward propagation. Now let's see how we can test our neural network implementation with some example input data. First, we define a binary input array input data with values 1, 0, which represents a simple input to the network. Next, we create an instance of our neural network class specifying the dimensions of our layers: 2 neurons in the input layer, 2 in the hidden layer, and 1 in the output layer. This configuration allows the network to process the binary input through its layers. After setting up the neural network, we perform a forward pass by calling the feedforward method with our input data. This method executes the calculations we previously established, processing the input through the hidden layer and finally producing an output from the output layer. The output generated by this operation will be the result of passing the binary input through the network, showcasing its capacity to predict or classify based on the current architecture and randomly initialized weights. Finally, we print the output, allowing us to observe how the neural network interprets the provided input after the feedforward operation. Next, we will implement the binary cross-entropy loss function, which is pivotal for measuring the performance of our neural network during training. This function quantifies the dissimilarity between the true labels and the predicted outputs, helping us to understand how well our model is performing. Now let's examine the implementation of the binary cross-entropy function. It takes 2 arguments: yTrue, representing the actual labels, and ypred, which contains the predictions made by the neural network. The core of the function calculates the average of the negative log probability of the predicted values, adjusted slightly with a small constant, 1e12. This adjustment is crucial. Without it, if ypred approaches 0 or 1, the logarithm could produce undefined results, leading to catastrophic errors. The calculation combines the 2 scenarios of true positives and false positives to return a mean value that reflects the overall loss across all instances. By evaluating this loss, we can derive insights into how effectively our model is learning, guiding the optimization process as we adjust weights in subsequent training iterations. This function is an essential tool for tuning the neural network, ensuring that the predictions move closer to the actual labels through iterative adjustments based on calculated loss. Now let's take a look at how we can compute the loss for our binary classification scenario using the binary cross-entropy function. The code begins with defining the actual label, yTrue, which represents the ground truth outcome for our model in this case, indicating that the input indeed contains a cat. With this known, we then calculate the loss by invoking the binary cross-entropy function, providing it with the true label and the predicted output from the earlier feedforward pass. This function evaluates how accurately our model's prediction aligns with the actual label by quantifying the discrepancy between them. Essentially, it performs calculations using logarithmic functions, which are sensitive to differences between the predicted probabilities and the actual labels. A lower loss value indicates that the model's prediction closely matches the true label, signaling improved performance. As we run this code, the printed loss serves as a critical metric that guides us in assessing how well the network has learned from the training data, setting the stage for future adjustments through backpropagation to refine our neural network's capabilities. Now let's implement the update weights method, which plays a crucial role in backpropagation and weight adjustment. In this method, we begin by calculating the error at the output layer by subtracting the actual labels from the predicted outputs. This output error is essential, as it helps us determine how far off our predictions are. We then apply the derivative of the activation function, specifically the sigmoid function in our case, to compute the output delta, which signifies how much we need to adjust our weights for the output layer. Next, we propagate this error backward to the hidden layer by taking the dot product of the output delta and the transpose of the weights connecting to the output layer. This calculation gives us the hidden error, which we again pass through the derivative of the sigmoid function to calculate the hidden delta, indicating how much to adjust the hidden layer's weights. Finally, the method updates the weights for both the output and the input hidden layers. By using the learning rate, we multiply the gradients derived from our deltas and adjust the weights accordingly. This adjustment process is vital for minimizing the loss and allowing the network to learn from its errors over successive iterations. With every training iteration, you'll typically want to repeat the steps of feedforward propagation, loss calculation, and backpropagation until your model converges, resulting in satisfactory accuracy. It's an iterative process where the neural network continually refines its weights based on feedback. To summarize, the architecture of neural networks, which includes layers, neurons, and connections, is essential for data processing. Understanding feedforward propagation allows us to see how inputs are transformed into outputs. We also explored the importance of accurately calculating loss and how backpropagation adjusts weights to optimize the model continually. As we move forward in this course, we will integrate these concepts into more complex environments, evolving our understanding of deep learning further. Get ready to dive deeper into advanced architectures and their applications in real-world scenarios. Keep those neurons firing, and I'll see you in the next lesson. Neural networks are a fascinating area of artificial intelligence, reminiscent of how our own brains function, designed to recognize patterns and make predictions in complex data. In this lesson, we will delve deeper into how these networks operate and what goes on behind the scenes as we set up our own neural network using PyTorch. So far, we've learned about the foundational concepts of neural networks, focusing on their architecture, including the roles of input, hidden, and output layers, and the essential process of feedforward propagation for making predictions. We covered the importance of optimization techniques for training networks, including the use of loss functions, particularly binary cross-entropy, to measure prediction accuracy. Additionally, we explored how backpropagation works to adjust weights based on errors, enhancing the model's ability to learn over time. This sets the stage for delving deeper into advanced neural network applications in future lessons. Now let's implement the necessary imports to set up our neural network environment in PyTorch. We'll begin by importing the main library, Torch, which is the foundation for all operations related to tensors and neural networks. Next, we include Torch, NN, which provides essential components for building our network architecture like layers and activation functions. Additionally, we'll import Torch Optim, a module that aids in optimizing model parameters during the training process. To work with datasets and transformations, we bring in Torch Vision, which provides ready-to-use datasets including the classic MNIST dataset as well as utilities to preprocess the data efficiently. Finally, we utilize Torch Utils Data, which will help us create data loader instances for managing our datasets conveniently. This foundational setup is critical, enabling us to build, train, and evaluate our neural network seamlessly. With these components in place, we can move forward to define our model architecture and move into the training phase. Next, we will write the following code to define our neural network architecture using PyTorch's NN module. This class named SimpleNN begins with an init method that initializes the network's layers. The input layer is created with NN linear, taking an input size of 784, which corresponds to the flattened size of 28x 28 pixel images, and outputs 128 features. Subsequently, the hidden layer compresses this further to 64 features, while the output layer produces 10 outputs, representing the class probabilities for digit recognition. Next, we will focus on the forward function, which defines how the input data flows through the network. Here, we apply the RayLU activation function after each linear transformation to introduce nonlinearity into the model's behavior. Specifically, as the data is transformed through the input and hidden layers, the RayLU function ensures that the network can learn complex patterns by allowing only positive values to pass through. This structure lays the groundwork for our feedforward neural network, serving as a fundamental building block for future enhancements or more complex network architectures. Now that we have defined our neural network, it's essential to prepare our dataset for training. Next, we will write the code to set up the transformations needed for the MNIST dataset, which comprises handwritten digits. We start by creating a composite transform that includes two operations. The first converts the images into PyTorch tensors, which are essential for processing in the network, while the second normalizes the pixel values. Normalization adjusts input values to have a mean of 0.5 and a standard deviation of 0.5, which helps the model converge during training. Moving on, we load the MNIST dataset from the specified directory, setting the train parameter to true to indicate that we want the training portion. By setting download equals true, we ensure that the dataset is downloaded automatically if it isn't already present. Finally, we create a data loader, which efficiently batches the dataset in sizes of 64 and shuffles the order of the data. This makes it easier for our model to learn and generalize better from the training data, preparing us for the next steps in the training process. Now let's implement the loss function and optimizer needed for our training phase. First, we initialize our neural network model by creating an instance of the SimpleNN class we previously defined. This sets up the architecture with the designated layers and activation functions. Next, we need to specify our criterion, which is the loss function that measures how well our model's predictions align with the actual labels. For this classification task, we will use the NN cross-entropy loss, a common choice for multi-class classification problems. It computes the difference between the predicted and actual outputs, guiding the model's learning process. Now let's configure our optimizer, which is essential for updating the model's parameters as training progresses. We opt for the Atom optimizer provided by OptimAtom, known for its efficiency and effectiveness in handling sparse gradients. The learning rate is set to 0.001, determining the size of the weight updates during optimization. This combination of loss function and optimizer provides a robust framework for training our model, addressing performance and convergence effectively. Now let's implement the training loop to refine our model's performance based on the data we've prepared. We start by defining the number of epochs, which determines how many full passes we'll make over our training dataset. Inside the loop, we iterate over the train loader, which provides batches of images and their corresponding labels. Next, we clear any accumulated gradients with optimizer 0grad, ensuring that our updates during each iteration only consider the current batch's gradients. We then flatten our input images from a shape of 28 by 28 pixels into 784-dimensional vector to feed into the neural network. This reshaping is essential as our model expects a one-dimensional input. Once we obtain the model's output, we calculate the loss using our defined criterion, which measures how far the predictions are from the actual labels. After computing the loss, we apply backpropagation via loss backward, which computes the gradients of the loss with respect to the model's parameters. Finally, we update the model's weights with optimizer step, applying our learned gradients to improve performance. At the end of each epoch, we print the current loss to monitor how well the training is progressing. The displayed figure plots training loss left y-axis and validation accuracy right y-axis across 5 epochs x-axis with a clear epoch trace of learning progress. The training loss falls steadily from 2.5 at epoch 1 to 0.2 at epoch 5, with the largest absolute decrease occurring between epochs 1 and 2, a drop of 1, then smaller but consistent reductions thereafter 0.5, 0.5, and 0.3. In parallel, validation accuracy rises from 10% to 90% in even 20 percentage point increments each epoch, 10 right arrow, 30 right arrow, 50 right arrow, 70 right arrow, 90. This juxtaposition shows a strong inverse relationship over these epochs. As loss decreases, accuracy increases, indicating effective learning during the training window. The distinct markers at each epoch make it easy to read discrete improvements per epoch, and the title and dual-axis labels clarify that the blue trace corresponds to loss, while the orange trace corresponds to accuracy. From these patterns, we can conclude that the model is consistently improving on the validation set throughout these 5 epochs, with the biggest gain in loss occurring early and steady accuracy gains across all epochs. There is no sign here of validation accuracy degrading while loss continues to fall, i.e., no evidence of overfitting within this range. Although the diminishing magnitudes in loss reduction suggest that subsequent epochs might yield smaller incremental improvements unless hyperparameters or model capacity are changed. Now let's implement the evaluation phase of our model training process. We begin by loading the MNIST test dataset, which consists of unseen handwritten digits, using a similar approach as we did during training. The test data is encapsulated in a data loader for efficient batching. Next, we set the model to evaluation mode with model eval, preparing it for inference rather than training. To assess the model's performance, we need to compute the accuracy of its predictions without requiring gradients, so we wrap our evaluation code in a Torch no-grad context. This significantly reduces memory usage and speeds up computation during the evaluation phase. As we iterate through the test loader, we run the model on each batch of images, reshaping the data to fit the expected input format. We then use torch.max to extract the predicted classes from the output probabilities. Finally, we keep track of how many predictions were correct by comparing the predicted classes to the actual labels. By aggregating these results, we compute the accuracy percentage, which provides a clear metric of how well our trained model is performing on unseen data. This step is crucial for understanding the model's effectiveness and potential areas for improvement. What we've just accomplished is a fundamental implementation of a neural network in PyTorch. This gives you a taste of how these advanced models are constructed. We can now explore more advanced features like tweaking hyperparameters, adding more complex layers, and experimenting with different activation functions. Hyperparameters control various aspects of our model, such as learning rate, number of hidden layers, number of neurons per layer, batch size, and more. By adjusting these parameters, we can significantly impact the performance of our model. For example, increasing the number of hidden layers might improve the network's ability to learn complex functions, but it might also lead to overfitting if not managed correctly. Now let's implement the following structure for a convolutional neural network CNN in PyTorch, which is well suited for processing image data. In this code, we define a class CNN that inherits from NN module, allowing us to create a custom neural network model. Within the init method, we initialize two primary components, the convolutional layer and the fully connected layers. The first layer, NN-convtd, takes a single-channel input grayscale image and applies 32 filters of size 3x3 to detect basic features like edges and textures. The pooling layer, defined as NN. MaxPoolTD helps simplify the data by reducing its dimensionality, allowing the model to focus on the most significant information gathered by the convolutional layer. In the forward method, we pass the input tensor through the convolution layer followed by the RayLU activation function, promoting nonlinearity. We then apply the pooling layer to downsample the feature maps. Next, we flatten the output from the pooling layer before passing it into two fully connected layers. The first fully connected layer reduces the feature dimensions down to 128 units, which is then followed by a final output layer that produces class probabilities for 10 different classes. This structure effectively combines feature extraction and classification within the CNN. In conclusion, we've covered a lot of ground in understanding how neural networks operate, implementing one using PyTorch, and recognizing the importance of tweaking hyperparameters to improve performance. As we continue our journey into the world of neural networks, be excited to explore even more advanced techniques such as convolutional layers, recurrent layers for sequential data, and different optimization strategies. The world of neural networks is vast, but by grasping the fundamentals we've outlined today, you have a solid foundation upon which to build. Remember, the magic of neural networks lies not just in their design, but also in how you understand and manipulate their components to solve real-world problems creatively. Thank you for joining this adventure into neural networks, and I can't wait to see what you'll create next. Training a neural network is an essential process that helps optimize its weights to make accurate predictions. This involves a systematic workflow of two main steps: forward propagation and backpropagation, guided by a defined learning rate. So far, we covered the foundational concepts of neural networks, including the architecture with input, hidden, and output layers, and the predictions made through feedforward propagation. We implemented a simple feedforward neural network using PyTorch, prepared the MNIST dataset, and defined the necessary loss function and optimizer. Additionally, we explored the training process and evaluated the model's performance on unseen data, reinforcing the importance of hyperparameter tuning and advanced structures like convolutional neural networks. Now, we will talk about the detailed training process of neural networks, focusing on how forward and backward propagation works harmoniously to optimize learning. Now let's see how we can implement forward propagation in a simple neural network using PyTorch. We begin by defining a class named SimpleNN, which extends from NN module, forming the foundation of our model. Within the constructor, we set up our network layers, a hidden layer and an output layer. The hidden layer is created using NN linear, where we specify the size of the input and hidden layers, allowing it to learn appropriate weights for the connections. Additionally, we initialize the RayLU activation function to introduce nonlinearity into our model, enhancing its capability to learn complex patterns. The forward method is where the magic of forward propagation happens. Here, we pass the input through the hidden layer, applying the RayLU activation after the transformation. The resulting output then flows into the output layer, producing the final predictions for the inputs. This method encapsulates the mathematical computations we discussed earlier, effectively transforming input data to generate outputs, making it crucial for the training process in neural networks. The figure titled Loss During Training, Forward versus Backward Propagation shows the loss values plotted across epochs 1 through 10 on the x-axis, with the y-axis representing loss magnitude. Two series are displayed, forward propagation loss marked with circles and backward propagation loss marked with crosses. Both are labeled in the legend, and the plot grid and epoch tick marks 110 highlight the discrete updates per epoch. The dominant pattern is a clear, progressive decrease in loss for both series over the 10 epochs, with the steepest declines occurring in the early epochs and a slower, asymptotic reduction toward later epochs. Importantly, the two curves closely track each other at every epoch, indicating that the loss computed after the forward pass and the values tied to the backward pass, i.e., the quantities used to compute gradients, are consistent and aligned. This reflects correct gradient computation and an optimizer that updates weights in a direction that consistently reduces loss. Small local fluctuations between consecutive epochs appear as minor deviations between the two markers. These are consistent with stochastic effects from batch sampling or simulated noise, but do not disrupt the overall downward trend. By epoch 810, the losses approach a low, stable region, suggesting that the model is converging under the current learning rate and optimizer settings. From this visualization, one can conclude that training is proceeding effectively. Loss is decreasing, forward and backward signals agree, and there is no sign of divergence or growing instability, conditions that would prompt checking the learning rate or optimizer configuration if present. Now let's implement the following training function that encapsulates the essential steps for training our neural network. The train function begins by iterating over a specified number of epochs, allowing the model to learn from the data multiple times. Within each epoch, we loop through batches of inputs and corresponding labels retrieved from the data loader. The first crucial step in the loop is resetting the gradients using optimizer 0grad. This is important because, by default, gradients accumulate in PyTorch. Hence, we need to reset them to 0 before each backward pass to ensure that we only compute gradients for the current batch. Next, we perform a forward pass by passing the inputs through the model to obtain the outputs. The loss is then calculated using the defined criterion, which, as we've discussed, is typically cross-entropy loss for classification tasks. With the loss computed, we call loss backward, which triggers the backpropagation process to compute the gradients of the loss with respect to each weight in the network. Finally, we update the model's weights by invoking optimizer step. This whole loop is executed for each batch in every epoch, ensuring that the model progressively learns and refines its predictions over time. After completing each epoch, we print out the loss to monitor the model's performance as training progresses. Now let's implement a learning rate scheduler in our training process to enhance our model's convergence. We begin by importing the StepLR class from the Torch Optim LR scheduler module, which facilitates dynamic adjustments to the learning rate during training. This is crucial because the learning rate can be pivotal in determining how quickly our model learns optimal weights. Next, we assume that an optimizer has already been defined, which is responsible for updating the model's parameters based on the computed gradients. We create an instance of StepLR specifying parameters such as step size and gamma. The step size indicates how many epochs will pass before reducing the learning rate, while gamma determines the factor by which the learning rate will be multiplied. These values can significantly influence how smoothly the training process unfolds. Inside our training loop, we call the train function for one epoch and then invoke scheduler step to update the learning rate based on the current epoch. This approach allows the learning rate to adapt over time, reducing it after a set number of epochs, which often leads to better convergence behavior and helps avoid overshooting the optimal weights during training. Now let's implement the evaluate function, which is crucial for assessing the performance of our trained model. This function begins by setting the model to evaluation mode using model eval. a significant step that deactivates components like dropout layers and batch normalization, ensuring consistency during evaluation. Next, we initialize counters for correct predictions and the total number of samples. This allows us to calculate accuracy later on. As we process the validation data, we utilize a context manager with Torch NoGrad, which disables gradient tracking for this phase, effectively saving memory and computational resources. Within the evaluation loop, we iterate over the input data and true labels provided by the data loader. For each batch, the model generates outputs, from which we extract the predicted class using torch.max. This method identifies the index of the highest prediction score, indicating the model's predicted class. We then accumulate the correct predictions and total samples across batches. Finally, the accuracy is computed as the ratio of correct predictions to the total number of samples, and we print this metric, giving us insight into how well our model performs on unseen data. Another important aspect of training is the concept of epochs and batches. The dataset may be too large to move through in one single pass. Instead, we break the data into smaller batches that our model can process iteratively. This not only helps in memory management, but also in updating the weights more frequently, leading to a more stable and optimized approach. Let's place our training process in context. For instance, if you have a dataset containing 60,000 samples, training on the dataset in batches of 256 will mean that you need to perform about 234 updates, 60,000/256 for each epoch. This iterative process is integral to converging towards optimal weights in neural networks, and it's often advisable to shuffle your data at the beginning of each epoch to ensure that the model experiences the dataset in a different order. Now let's see how we can implement dropout in our neural network to enhance its robustness against overfitting. We begin by modifying our SimpleNN class to include a dropout layer, which is an essential feature when training deep learning models. In the constructor, we add a parameter called dropout rate that defines the fraction of neurons to randomly deactivate during training, typically set to 0.5. This dropout layer is instantiated alongside the hidden layer, allowing us to effectively incorporate regularization into our model. During the forward propagation phase, after the activation function is applied to the hidden layer's output, we invoke the dropout layer by passing this value through it. This process randomly sets a subset of the activations to 0, forcing the network to learn more generalized features rather than over-relying on any single feature. The output from the dropout layer is then passed on to the output layer of the neural network. This strategic use of dropout encourages the model to maintain its performance even when exposed to varying subsets of data, ultimately leading to better generalization on unseen data. In summary, we've delved deep into the training process of neural networks, focusing on the pivotal roles of forward propagation and backpropagation. We discussed how to optimize weights through the iterative application of these processes while tuning hyperparameters such as learning rates and employing strategies to prevent overfitting. We explored how to implement these concepts using PyTorch, applying practical coding examples to reinforce the theoretical understanding of training neural networks. From moving weights in a direction that minimizes loss to handling large datasets via batching, we've laid the groundwork for building powerful models capable of solving complex problems. As we continue our journey in this field, the next steps will involve exploring more intricate architectures, optimization algorithms, and advanced techniques like transfer learning and ensemble methods. The more tools you equip yourself with, the better your machine learning models will become, making them not just good, they can be extraordinary. Thank you for joining me today, and let's get ready to train even more powerful networks in our next lesson. Now let's dive into understanding neural network architecture and training processes, the heart of deep learning. We'll explore how these fascinating systems are structured, the many components involved in their design, and the methodologies we use to train them effectively. So far, we learned the essential processes of training neural networks, focusing on forward and backward propagation to optimize weights for accurate predictions. We implemented a basic feedforward neural network in PyTorch, discussed training techniques including learning rates and performance evaluation, and explored strategies to prevent overfitting such as dropout. Additionally, we emphasized the importance of batching during training for effective weight updates. Moving forward, we will explore more complex architectures and advanced optimization methods. Now let's implement a simple feedforward neural network class in PyTorch, which will serve as the fundamental building block for our deep learning model. We start by importing the necessary libraries including Torch and Torch NN to leverage PyTorch's functionalities. Next, we define our neural network class SimpleNN, which inherits from NN module. Inside the initialization method, we configure the layers by creating fully connected layers using NN linear. This includes setting up the first hidden layer, second hidden layer, and output layer, ensuring that each layer receives the correct size based on the specified parameters. This structure reflects the common practice of progressively transforming input features through multiple layers. Following the initialization, we define the forward method, which outlines how data will flow through the network. In this method, we apply the ReLU activation function after each of the hidden layers to introduce nonlinearity, allowing the network to learn complex representations. The final layer outputs the predictions before returning the result. This design sets the stage for training the network using backpropagation, optimizing its weights based on the input data and corresponding labels. The accompanying figure titled Neural Network Architecture visualizes this exact layer configuration. The x-axis lists the layers as input layer, hidden layer 1, hidden layer 2, and output layer, and the y-axis quantifies the number of neurons in each. Numeric labels are displayed on each bar showing the precise neuron counts: 10 for the input layer, 20 for hidden layer 1, 10 for hidden layer 2, and 2 for the output layer. The bars make the most salient pattern immediately clear. The network expands from 10 neurons at the input to a peak of 20 neurons in the first hidden layer, then contracts back to 10 in the second hidden layer and sharply to 2 at the output. This expansion then compression pattern suggests an intermediate feature expansion, increasing representational capacity, followed by dimensionality reduction toward the output, which is consistent with a design that extracts and transforms features before mapping them to a low-dimensional decision space, here matching a binary output of size 2. The equal heights of the input layer and hidden layer 2, both 10, indicate symmetry around the central bottleneck at the output, and the labeled Y-grid helps quantify these relationships and compare layer capacities directly. From an architectural perspective, this distribution highlights where most of the model's capacity resides, hidden layer 1, and where potential bottlenecks or constraints occur, the small output layer, and it directly corresponds to the earlier code parameters: input size equals 10, hidden size 1 equals 20, hidden size 2 equals 10, output size equals 2, reinforcing how numeric design choices manifest as layer widths in a network diagram. Now let's implement the training phase for our neural network. We start by defining our model parameters, including the input size and the sizes of the hidden and output layers. This step is crucial as it determines how our network will process the data, setting up a structure capable of handling our binary classification task. Next, we configure the loss function using cross-entropy loss, suitable for classification tasks, and initialize the stochastic gradient descent (SGD) optimizer to update our model's parameters. The optimizer is set with a learning rate that controls how aggressively the model updates weights based on the calculated gradients. Now, as we enter the training loop for 100 epochs, we clear the gradients at the beginning of each epoch to ensure that we don't accumulate gradients from previous steps. With dummy inputs and labels, we perform a forward pass of our model to obtain output predictions. Following this, we compute the loss by comparing the model's predictions with the actual labels. The magic happens when we call loss backward, which computes the gradients of the loss with respect to the model parameters through backpropagation. Finally, we call the optimizer's step function to update the weights, effectively teaching our model to minimize the loss. This process repeats for each epoch, allowing the model to iteratively learn from the provided data. Now let's implement a learning rate scheduler to optimize our training process. In the provided code, we create a scheduler using Torch Optim LR Scheduler Step LR, which adjusts the learning rate based on our defined criteria. Specifically, the learning rate will decrease every 30 epochs by a factor of 0.1, allowing the model to refine its learning as it progresses through training. As we enter the training loop, we start by zeroing the gradients of the optimizer to prevent accumulation from previous iterations. We then generate a random input tensor and a corresponding label for training purposes. The model makes a forward pass using the input, producing output predictions. We calculate the loss by comparing these predictions with the actual labels using our defined criterion. After obtaining the loss, we invoke loss backward, which computes the gradients for each parameter through backpropagation. The optimizer updates the weights accordingly. Crucially, we call scheduler step after each optimizer step to adjust the learning rate based on the schedule. This strategy not only stabilizes the training process, but also allows us to monitor the learning rate dynamically in the output every 10 epochs, providing insight into how our adjustments contribute to model performance. Now let's implement an advanced neural network architecture that incorporates dropout to mitigate overfitting. We define a class named AdvancedNN which inherits from NN module. In the initialization method, we set up the layers of the network, beginning with the first fully connected layer, FC1, followed by a dropout layer that randomly sets 50% of the neurons to 0 during training. This functionality is crucial as it prevents the model from overly depending on any particular feature during the learning process. Next, we define the subsequent layers of the network, the second fully connected layer, FC2, and finally the output layer, FC3. In the forward method, we process the input data through these layers. We apply the RayLU activation function on the output of the first layer, then immediately follow this with the dropout layer, effectively applying dropout. Afterward, the data is passed through the second layer and output layer without additional activation. This setup ensures that the model retains the ability to learn complex representations while also maintaining a degree of robustness against overfitting, making it a more generalizable model. This example illustrates how adding dropout can effectively enhance our network's performance and generalization capabilities. Now let's implement a hyperparameter optimization technique using the Optuna library to enhance our neural network's performance. We begin by importing the Optuna package and defining an objective function which will be the core of our optimization process. Within this function, we utilize trial, suggest log uniform to suggest a logarithmically spaced range of learning rates, allowing us to explore a wide span effectively. Similarly, trial suggest uniform is employed for determining a dropout rate between 0.1 and 0.5, which helps in managing overfitting. Next, we instantiate our advanced neural network model, passing in the parameters for input size, hidden layers, output size, and the suggested dropout rate. An optimizer is then created using stochastic gradient descent (SGD) with the selected learning rate, linking the optimizer to the model's parameters for training. While the training loop is mentioned as a placeholder, this is the part where we would typically iterate through our dataset, conducting forward passes, loss calculations, and backpropagation to fine-tune the model. Finally, the objective function returns the loss, guiding the optimization process. To wrap it up, we create a study to run the optimization over 100 trials, ultimately aiming to minimize the loss and identify the most effective hyperparameter settings. As we wrap up our discussion, remember that neural networks are a powerful tool that, when structured and trained correctly, can handle complex tasks across diverse domains. We have covered crucial elements of understanding the architecture, training processes, hyperparameter tuning, and methods to improve generalization. The world of deep learning is vast and exciting, and we've only scratched the surface. With the knowledge gained, you are now ready to implement and experiment with your own neural networks using PyTorch. Whether you aim to design a network for image recognition, natural language processing, or any other machine learning task, keep iterating, learning from outcomes, and fine-tuning your approach. The power of neural networks is in your hands. Training a neural network is an intricate dance of mathematics, algorithms, and a dash of intuition. In essence, it involves finding the optimal weights for a neural network architecture, repeating the essential processes of forward propagation and backpropagation under a fixed learning rate. Get ready to explore this fascinating world, where we will deep dive into the nitty-gritty of training and optimization techniques, making neural networks not just smarter but wiser. Now let's take a look at how we can implement a simple feedforward neural network using PyTorch. We begin by importing the necessary libraries, specifically PyTorch and its neural network module. The SimpleNN class inherits from NN module, which is a fundamental building block in PyTorch for creating neural network models. In the constructor init method, we initialize two fully connected layers, the first layer with 10 input features and 5 hidden units, and the second layer transforming 5 hidden units to a single output. We also define a RayLU activation function to introduce nonlinearity between these layers. Next, we define the forward method, which outlines how data flows through the network during forward propagation. This method takes input data, processes it through the first linear layer, applies the activation function, and then passes the result to the second linear layer, ultimately returning the final output. After defining the model, we generate a random input tensor to simulate a single sample with 10 features. Finally, we execute the model with this input to observe the network's predictions, illustrating the forward propagation process that we previously discussed. Now let's explore the code that implements backpropagation in our neural network. We begin by creating a sample dataset with random inputs and corresponding targets, simulating a simple training scenario. Next, we initialize our model, the mean squared error loss function, and the stochastic gradient descent optimizer. This setup is crucial as it establishes the components needed for training the model. Next, we implement a training loop that runs for 100 epochs. Within this loop, we set the model to training mode and first clear any existing gradients to ensure fresh updates. A forward pass is performed where the model generates predictions based on the input data. The loss is then calculated by comparing the model's predictions with the actual targets, quantifying how well the model is performing. Now let's see how we handle the backward pass. By calling the loss backward function, we compute the gradients needed for each weight in the model. This step is vital as it essentially informs the model how to adjust its parameters to minimize the error. Afterward, we use the optimizer to adjust the weights based on these calculated gradients. Finally, we display the loss at intervals, allowing us to observe the model's progress over the epochs. This cyclical process of forward propagation followed by backpropagation is what continually refines the model's predictions. Now let's explore how we can implement a training loop that varies learning rates to observe their impact on model performance. In this code, we define a list of different learning rates and initialize a results dictionary to store the loss values corresponding to each learning rate. For each learning rate in our list, we reinitialize the model to start fresh and set up the stochastic gradient descent optimizer with the current learning rate. Inside the training loop, we execute a series of epochs where the model is trained on the input data. At each epoch, the model processes the data, computes the loss using the specified loss criterion, and then performs backpropagation to update the weights. Throughout the 100 epochs, we collect the loss values after each complete pass through the dataset into the losses list. Once all epochs are completed for a particular learning rate, we store the losses associated with that learning rate in the results dictionary. Finally, we visualize the gathered loss data for all learning rates on a plot, allowing us to compare how the choice of learning rate affects the convergence behavior of the model over time. This hands-on approach not only illustrates the nuances of learning rates, but also reinforces the importance of hyperparameter tuning in the optimization process. The figure displays training loss across 100 epochs for 3 learning rates, with epochs on the x-axis 100 and loss on the y-axis. Each curve is labeled in the legend. Blue corresponds to LR equals 0.01, orange to LR equals 0.1, and green to LR equals 0.001. Key patterns are immediately visible. The orange curve, LR equals 0.1, shows the steepest early decline in loss, dropping rapidly during the initial epochs and reaching a low-loss plateau much earlier than the others. However, it also exhibits the largest short-term fluctuations, small jitter around that plateau, indicating more variability in updates. The blue curve, LR equals 0.01, follows a smoother, steadier exponential-like decay. It converges more gradually than the orange curve but with fewer oscillations, reaching a comparable low-loss region later in training. The green curve, LR equals 0.001, decreases the slowest, maintaining the highest loss values for most of the run and showing the least variability, which demonstrates slow but stable progress. From these visual patterns, we draw the practical conclusions highlighted in the lesson. A larger learning rate accelerates early convergence at the cost of increased update variance, risking instability. A moderate learning rate balances speed and stability, and a very small learning rate produces slow but stable improvement that may require many more epochs to reach similar loss levels. Now let's see how we can implement the ATOM optimizer in our neural network training routine. By replacing the traditional stochastic gradient descent (SGD) with the ATOM optimizer, we gain significant advantages in terms of convergence speed and stability. In this code snippet, we initialize the optimizer by calling optim_atom, passing in the model parameters we want to optimize and setting the learning rate to 0.001. The ATOM optimizer works by maintaining 2 moving averages, one for the gradients and another for the squared gradients. This allows it to adaptively adjust the learning rate for each parameter based on their historical behavior. With ATOM, the optimization process is typically more efficient, often leading to faster convergence and enhanced robustness against issues like vanishing or exploding gradients. This choice is particularly advantageous in deep learning scenarios, where the layers and complexity of the model increase the potential for such issues. By integrating this advanced optimizer, we set ourselves up for improved performance in training deep learning models, enabling them to learn more effectively from the data at hand. Now let's see how we can implement a training process that examines the effects of different batch sizes on model performance. We begin by defining a list of batch sizes to experiment with, which range from smaller sizes like 1 to larger sizes like 64. For each batch size, we initialize a new instance of our neural network model and the optimizer, in this case, stochastic gradient descent (SGD) with a fixed learning rate. As we prepare the dataset for training, we use PyTorch's data loader to create batches of our input and target data. This allows the model to process batches of samples instead of the entire dataset at once, In the training loop, we run through a specified number of epochs, updating the model weights based on the average loss calculated from each mini-batch. This iterative process of adjusting weights helps the model learn effectively. By the end of the training, we record the loss associated with each batch size, allowing us to compare how different sizes impact the training process. Finally, we visualize the results by plotting the loss curves for each batch size, helping us observe the convergence behavior and effectiveness of various batch sizes in optimizing our model's performance. Now let's see how we can implement dropout in our neural network to enhance generalization and prevent overfitting. In the code, we define a new class named SimpleNN with dropout, which inherits from NN module, marking it as a PyTorch neural network model. Within the constructor, the first layer defined is a fully connected layer, FC1, that transforms the input from 10 to 5 neurons. Following this, we introduce the dropout layer with a probability of 0.5, meaning that during training, 50% of the inputs to this layer will be randomly set to 0. This stochastic behavior helps the model become less reliant on any specific set of neurons, encouraging it to learn more robust features. After the dropout layer, we define a second fully connected layer, FC2, which maps the 5 neurons back down to a single output. In the forward method, we detail how data flows through the network. The input is first passed through FC1, then subjected to dropout, and finally sent through FC2 to produce the output. By instantiating the simple NN with dropout model, we can leverage the dropout technique during the training process to enhance the model's ability to generalize to new data. By integrating these various training and optimization techniques, you are now equipped to take your first steps into a more advanced, deeper exploration of neural networks. We have covered the essential processes of forward propagation and backpropagation, the significance of learning rates, the exploration of sophisticated optimization algorithms, the effect of batch size, and strategies to prevent overfitting. As you embark on your journey with neural networks, remember that the rapid pace of advancements in deep learning means there is always something new to learn. Each experiment brings insights and improvements. Stay curious and keep coding. The fascinating world of neural networks is built upon several fundamental building blocks that resemble the workings of the human brain. In this session, we will dissect these components by understanding how artificial neural networks, or ANNs, are structured and how they function. This exploration will not only deepen our understanding of neural networks, but also enhance our capability to create and implement them effectively. So far, we learned the essential concepts of training neural networks, including forward and backward propagation, hyperparameter tuning, and optimization techniques. We implemented a simple neural network model using PyTorch and examined the impacts of learning rate and batch size on training performance. Additionally, we explored advanced optimizers like atom regularization techniques to prevent overfitting, and the importance of tuning these aspects to enhance model effectiveness. Our journey into optimizing training methodologies has equipped us with insights into building more robust neural networks. Now, we will talk about the fundamental components of neural networks known as building blocks. Now let's take a look at the implementation of a simple artificial neuron in Python. This neuron class initializes with a set of weights and a bias, crucial parameters that influence the neuron's output. In the activate method, we calculate the total input by taking the dot product of the inputs and weights, adding the bias to this sum, and then passing the result through the sigmoid activation function. The sigmoid function plays a vital role in introducing nonlinearity to our model, allowing the neuron to learn complex patterns by determining when it should fire or produce an output. This method not only computes the neuron's output based on the inputs it receives, but also illustrates the core operational principles of artificial neurons, combining input signals with learned weights, applying a bias, and using an activation function. As we build more complex structures like layers of neurons, this foundational code exemplifies how each neuron processes information, akin to a biological neuron in the human brain. By mastering this implementation, you'll better understand how to construct and optimize neural networks for various applications. Now let's take a look at the implementation of our simple neural network. In this code, we define a class called neural network, which initializes 2 layers, a hidden layer and an output layer. The input size, hidden layer size, and output size are specified when creating an instance of this class. Each layer is implemented using the neuron class we defined earlier. This structure allows for a seamless flow of data from one layer to the next. The init method initializes the weights and biases of both layers randomly, ensuring that the model starts with a unique configuration each time. This randomness is vital for breaking symmetries and enabling effective learning. Next, we define the forward method, which performs the forward pass through the network. Here, input data is passed first to the hidden layer where the output is generated, and then this hidden output is fed into the output layer to produce the final prediction. By following this sequential processing, the neural network mimics the information flows similar to how biological neurons interact, setting a solid foundation for building more complex architectures. The displayed horizontal bar chart titled Key Concepts of Neural Network Building Blocks ranks 7 components by an importance level scale. The bars and their annotated values show that optimizers has the highest importance at 50, followed by weights at 40, hidden layers at 35, biases at 30, output layer at 25, regularization at 20, and input layer at 10. From these values, we can conclude a clear emphasis on training mechanics. Optimizers are shown as the most critical single element, indicating that how we update parameters has the largest perceived impact. Weights also score high, underscoring that learned parameters are central to model behavior. Hidden layers rank just below weights, highlighting architectural depth and representational capacity as important but secondary to parameter optimization. Biases occupy a moderate position, reflecting their role in shifting activations without dominating learning priorities. Regularization appears lower but non-zero, signaling it is necessary for generalization though less immediately influential than optimizer choice or raw parameter values. The input layer's relatively low score suggests the chart treats raw inputs as foundational but less decisive than how the network processes and updates internal parameters. Overall, the chart presents a prioritization. Focus first on optimizer strategy and parameter management weights, then on network capacity, hidden layers and biases, and finally on regularization and input handling. Now let's take a look at how we can implement a simple training routine for our neural network using the mean squared error MSE loss function. In the train method, we first perform a forward pass through the network to obtain the output predictions. This is accomplished by calling the forward method, which processes the input data through the hidden layer and then the output layer. Next, we calculate the loss using the predicted output and the expected values. The loss gives us a quantitative measure of how far off our predictions are, guiding us in adjusting the model's weights. We compute the gradients based on this loss to determine how much the weights should be modified to reduce the error in the next prediction. To update the weights, we apply a learning rate which controls the magnitude of the adjustments made. By subtracting the calculated gradients scaled by the learning rate from the weights, we ensure they reflect the direction needed to minimize the loss. This iterative weight adjustment is at the heart of how our model learns over multiple epochs, ultimately improving its prediction accuracy with each training iteration. Now let's take a look at how we can enhance the functionality of our neuron by incorporating biases. In this implementation, we define a neuron class that not only includes weights for each input, but also a bias that gives the neuron extra flexibility. The constructor initializes both weights and the bias, enabling each neuron to learn more complex patterns in the data. Next, we will examine the activate method, which performs the critical task of calculating the neuron's output. This method computes the total input to the neuron by taking a weighted sum of the inputs, using the dot product of the inputs and weights, then adding the bias. This adjustment ensures that even when all inputs are zero, the bias allows for a non-zero output, reflecting how biases function in real-world decision-making scenarios. Finally, the activation of the total input is passed through a sigmoid function, which introduces nonlinearity to the model, an essential aspect for any neural network. By effectively combining weights and biases, this implementation illustrates how each neuron can contribute significantly to the overall learning process, leading to improved prediction capabilities in our neural network. Now let's implement the Atom Optimizer, a powerful algorithm that allows for dynamic adjustment of learning rates based on the gradients. We start by defining the Atom Optimizer class, where we initialize it with parameters such as learning rate, beta values for moment estimation, and a small epsilon to prevent division by zero. The beta values control the decay rates for the moving averages of the gradients in their squares. In the update method, we increase the time step with each call, signaling progression through the training steps. We check if the moving averages for the gradients in their squares are initialized. If not, we create them. The formulae then update these moving averages using the current gradients, weighted by their respective beta values. Next, we compute the bias-corrected estimates for these moving averages, which helps in stabilizing the optimizer's learning process. Finally, the weights are updated using the Atom optimization formula, incorporating the adjusted learning rates and the estimated moments. This method promotes more effective training, especially for deep networks, as it allows us to fine-tune how we adjust weights based on the complexity of the gradients. Now let's implement L2 regularization, a technique that helps mitigate overfitting by adding a penalty to our loss function based on the magnitude of the weights. In this function, we take the weights of our model and a regularization parameter, often denoted as lambda. The function computes the penalty by squaring each weight to ensure that larger weights contribute more significantly to the penalty and summing these squared values together. By applying L2 regularization, we effectively encourage the model to keep the weights smaller, which often leads to better generalization on unseen data. Incorporating this regularization term into the loss calculation is essential, as it will incentivize the optimization process to avoid excessively large weight values that may cause the model to perform well on training data but poorly on new unseen examples. It's crucial to find an appropriate balance. Too high a penalty can lead to underfitting, while a penalty that is too low might not adequately combat overfitting. Therefore, careful tuning of the lambda parameter is necessary for optimal performance, making regularization a vital aspect of training robust neural networks. In conclusion, we've covered the essential building blocks of artificial neural networks, from neurons and layers to weights, biases, optimizers, and regularization techniques. These concepts are vital for building and training effective neural networks. Understanding how these components interact paves the way for building models that can learn from data and make predictions while closely mimicking the learning patterns of the human brain. As you progress in your journey with neural networks, remember that the architecture you choose, the regularization methods, and the optimization strategies can significantly influence your model's performance. Keep experimenting with different configurations, and who knows, you might just create the next breakthrough in AI. Thank you for joining me today, and happy coding. In this final section, we will do a project challenge to apply what we have learned so far. The challenge is to build and deploy a computer vision model that allows users to upload images and receive predictions from a trained deep learning model. You'll begin by selecting a relevant dataset, such as the surface defect dataset or an image classification dataset, and pre-process this data using PyTorch. Next, you will develop a convolutional neural network (CNN) model, training it and experimenting with different architectures and hyperparameters to achieve the best performance. Once your model is ready, you'll set up a web API using FastAPI that accepts image uploads and returns predictions, ensuring to incorporate validation and error handling for robustness. The next step is to containerize your application using Docker, allowing you to encapsulate all dependencies and test it locally. Finally, deploy your Docker container to a cloud service like Oz or Heroku, making sure that your API is accessible over the internet. Don't forget to document your processes comprehensively, including installation, usage, and deployment instructions, with clear code snippets to guide others through replicating your setup. For further details and resources, you can find the final project in the GitHub repository linked in the description.